Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TrueSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve, o mundo merece sua ideia, a sua ideia merece a TwoSolve.
Professor Oscar, pode começar. Obrigado.
Bom dia a todos. Meu nome é Oscar Rodrigues, da Escola de Engenharia de São Carlos, da Universidade de São Paulo. I think I will switch to English. Good morning, everybody. I'm Professor Oscar Rodrigues from the University of São Paulo, campus São Carlos. It's my great pleasure to be here today, this morning, to be part of this sixth multiphase flow journeys, an event that's very important for our community, for our fluid mechanics community devoted to multiphase flow problems, which are very important for many industrial aspects. Today we're going to have a keynote speaker, which Luiz Otávio Vieira Pereira, who is an engineer of Petrobras, the biggest Brazilian company. Luiz Otávio, he took his master's degree at the Catholic University of Rio de Janeiro, PUC-Rio. He's a chemical engineer. He's a researcher from the research center of Petrobras. He's leading research projects between the research center and many Brazilian universities for so many years already. And he's being in charge also of some of development of some regulations for multiphase flow measurements, which is very important for the Brazilian standards and regulations and regulatory bureaus. Okay, among many other things. So it's a great pleasure to have here Master Luiz Otávio Vieira Pereira, who is going to talk about multiphase flow measurement for oil and gas allocations, measurements in Brazilian oil and gas industry. So we're going to have some overview of the Brazilian current scenario regarding multiphase flow measurement. So, Luiz Otávio, please, the audience is yours.
Thank you for inviting me, Professor Oscar and Master Martins. It's a pleasure to be here to share a part of my job. I'm going to share my screen. Please, please inform me if you can see my screen, my presentation, please.
Sim, professor. Sim, Luiz, tá tranquilo.
Thank you. Okay, I'm going to talk a part of my job in Petrobras Research Center is a multiphase flow measurement for oil gas allocation measurement in Brazil oil and gas industry. That's an important point, a hot point nowadays in oil and gas industry in Brazil. Okay, I'm going to talk because my approach here is a measurement, fluid measurement. That is my my job in research center. Okay, my studies in this part of that's I'm going to talking about the importance of measurement for oil and gas industry. That we had to. I'm going to try to use a pointer here. Okay. We have to monitor the operational process and control, okay? So the measurement is important to inventory determination, balance sheet closing, okay? We have one law that you have to attend the SOX, okay, Sarbanes-Oxley Act, leakage detection and product teeth, legal contractual obligations, government stakes, royalties, okay, that's the main parts, okay, taxes, custody transfers. That's important to say that our industry is going through the one journey in digital transformation. That data is really important. So the measurement is enable that's digital transformation because produce data. We need a data. That's data needs to transform information. Okay. So if you can't measure it, you can't manage it. It's a damning a sentence that's important to measure, to manage our process. That's the value of the measurement. When you're talking about the oil gas industry, talking about the reservoir, it's important to show that always we are going to have oil and water and gas in reservoir. So when you produce the main product is oil, okay, has the main value for oil gas industry, okay, this commodity oil. But when you produce oil, the most of time you are going to produce gas and water. So if I produce, okay, we have here some wells that if you produce this part of the reservoir, we are going to produce only water, okay. Here only gas, okay, because in the free gas cap part. But if you produce here is the better position for put your well, okay, hole. Here we are going to produce oil, but in this moment inside of the reservoir, this oil, it's always oil. But when you go up, okay, the pressure go down, decrease, and part of oil turn gas, okay, and water going to, okay, drive to the hole and produce water too. We are going to show that. Because that we are going to have a multi-phase flow, okay? So oil gas industry always need to handle multi-phase flow. It's turned a lot of complex, the fluid process control and you have to manage some phenomena like corrosion. So you have to measure this well, okay, because you need to control and you need to attend a requirement, okay, that you are going to talk after. So if I have, okay, in production, multi-phase flow, for me it's important to the oil only, okay, and the gas we have some value in the market, but less value than oil, but is important too, okay. And the water is a problem for me. I have to handle it, okay, and you have to attend the environment requirement too, okay, for water. I have a requirement if I go overboard in the sea, okay, I'm talking about in the FPSO production, okay, the platform that in offshore environment, that I can't overboard the water without, okay, take care about the requirement of this water quality, okay. So I can to reinject this water too, okay. So here we can see one process, okay, that's the well fluids go to the separators, the main equipment is separators, okay, that you have a residence time to separate gas, oil, and water, okay. So is different stages of separation, different equipments. Sometimes, okay, the most of them use the gravitational energy, okay, for separation, but we have equipment that's used to electrostatic energy too, okay, electrostatic field. So it's only for have idea. When I separate the fluids, I can measure, okay, in fiscal environment for pay royalties and attend the royalties requirement too. Looking for and talking about the multi-phase flow meterings, I'm going to talk the main operational principles and the equipment. The multi-phase flow metering developed in 18th, okay, it was a demand of oil gas industry. The broad definition is the equipment that allows the flow measurement into each individual phase of the multi-phase flow. So it's equipment that can measure the each phase of the multi-phase flow. Here we can see one commercial multi-phase flow metering that's a really compact equipment. Here we can see a one manifold, subsea manifold that you have multi-phase flow metering in the triable skids, okay, that with multi-phase flow metering here. Talking about the classification of multi-phase flow meter, we have two classifications, okay, one API or another from Norwegian oil gas. So I'm going to talk in the API classification. Okay, the multi-phase flow meter type 1 is a one separator, okay, the conventional equipment for separation or for measure the oil, the well production. So it's the conventional. The API call is type 1 multi-phase flow metering. The type 2 is a partial separator, is one equipment that separates the fluids, but is not a full separation that we have a wet gas here, okay, above, up, and go down a multi-phase flow meter that has low gas volume fraction. And type 3 is an inline meter. That's the main multi-phase flow meter that we talking about. Is an equipment that can measure all the flow, without separation. Okay, we can measure this equipment can measure the different phases without separation. Another classification from a Norwegian society, okay, is the oil gas measurement. That is an inline meter, okay, and partial separation meter, and the wet gas, okay. And the wet gas is one specific meter that for this part of the multi-phase flow that's called wet gas, that has a high gas volume fraction, so above to 95% of gas. Talking about the theoretical measurement problem that you have to solve to measure the multi-phase flow, okay, is a paper, okay, for Thorn here that you can have to measure the phase fraction, okay, the phase velocity, the phase density, so a multi-phase flow, okay, and alpha, beta in X here is a gas, water, and cross-section fraction, okay, of this fluid, okay, oil, water, and gas. Phase velocity of oil, gas, and water, okay, and the density of oil, gas, and water, okay. So when you have, okay, the velocity and the phase fraction, cross-section fraction here, and we have the pipe area here, and you can get the total volumetric flow. And this cross-section fraction into each phase is equal 1. So the most of equipment can measure, okay, the gas volume, velocity, and the water velocity and fraction. So we can substitute this equation here, okay. And if you put the density of the fluids, you can have the mass, total mass flow, okay. So it's the simple and the the problem that we have to solve, okay? We have to measure the phase fraction, the phase velocity, and the phase density. I'm gonna talk more about these techniques, the main techniques, okay, that multi-phase flow metering applying in this technology, okay, the commercial ones. For velocity and flow measurement, the most of use cross correlation or Venturi. Okay, for density measurement, gamma densitometer or Coriolis. The phase fraction measurement, capacitive inductive microwave sensors, and radioactive attenuation tool, okay? Venturi is talking about the Venturi is a pressure difference is created by reducing the diameter, okay, of the pipe, so causing the fluid to flow faster. The fast moving fluid has a lower pressure, so we have a differential pressure here, okay, that's proportional to rate, okay, the mass flow rate. So this type of equipment is used a lot in the commercials multi-phase flow metering, okay, for measure the mass flow, total mass flow rate. Another technique that we can use for velocity is a cross correlation, okay, is a upflow, and the most of multi-phase flow meters upflow. So when you have one phenomenon that pass here, okay, one bubble of gas or water pass here, and we have the distance between the two pair of sensors. So when it passes another pair of sensor, we have one signal that is here and here. We have the time of this signal, we have the distance, we can have the velocity, okay? The distance above to time. One technique for phase fraction, the same sensor that's used in cross correlation is used to phase fraction measurement, okay, capacitive inductive sensors. Okay, when you have oil continuous phases, when you have a low BSW, low water cut, we use a capacitive, okay, capacitive principle. When you have water continuous phase in high water cut, okay, above to 6% or 70%, we are going to use inductive sensor. The same sensor can use the same physical equipment can use the two principles, capacitive and inductive. So the signal is proportional amount of oil and water, okay, in the system, in the multi-phase flow. Another type of technique is a microwave sensor, okay, is a tomography. We have some commercial equipment that use a tomography by microwave that you can see, or you can measure the bubbles inside of the multi-phase flow. Is a really fast, rapid signal measurement, okay, inside of this tomography. The technique for density measurement is a gamma densitometer, okay, and this technique can use for phase fraction measurement. For density measurement, you use the attenuation of the signal of the gamma dense, the radioactive source, okay, we have one radioactive source. That's the signal here is attenuated by the density of the multi-phase flow. So it's proportional. How the higher the density, higher the attenuation of the signal here. And another technique for our phase fraction is a dual gamma. There are some sources that produce two energies, one source and two energy. So it's a low energy and a high energy. The equipment, the multiphase flow meter software produces this triangle here. That's here we have a position of the density of gas, density of the water and the oil. So we have to know, okay, the density of these fluids, and by the attenuation signal, we can have the information about the position or the operational point of the gas volume fraction percentage and water liquid ratio percentage, okay, of the multiphase flow. Okay, for flow velocity and density, we can use the Coriolis, okay. The Coriolis is a common equipment for mass flow measurement, okay, for monophase flow, but you can use this technology for multiphase flow too, okay, for measure the mass flow rates, okay. The multiphase flow pass through the tubes, okay. We have to have this multiphase flow mix. One fluid pass through the tube, the mass flow momentum will cause the change in the tube vibration, and the tube will twist, resulting in the phase shift. This phase shift can be measured in a linear output derivative of proportional flow. So we can measure the mass flow rate by the phase shift case from the density between the fluids. The practical calculation of multiphase flow metering that I'm talking here is we talked about the velocity flow measurement, the density measurement, the phase fraction measurement. The multiphase flow meter have to pressure and temperature, okay. The equipment use the phase models, the fraction models, sorry, and the flow models for getting, okay, that you getting oil flow rate, water flow rate, and gas flow rate, and temperature and pressure conditions of the installation, okay, in the operational conditions. But okay, for attend okay, sometimes a control room necessities or requirement from regulators, you need to have the at reference condition. I mean, temperature and pressure. Pressure 1 atmosphere, okay, the temperature 20 degrees, I have to bring it for this condition. For it, I have to use the PVT model, okay, of the equipment, the pressure, volume, temperature, okay, we have to inform the equipment the oil shrinkage factor, okay, and the gas compressibility and the gas solubility ratio for getting this information, okay. I can show you that if I have the oil, gas, and water, okay, we have a multiphase flow in meters location. When you bring it for another condition, okay, when the pressure reduce, we are going to have a expansion of the gas, okay, the flash and expansion of the gas, the flash of the oil, so part of the oil turn gas, okay, and the oil is shrinkage, okay, and so it's important to have this model inside of the equipment for correct it, okay. Not only is the equipment have to measure well in the meter's location, the equipment software needs to handle well this transformation for the reference condition. So in practical way, we can see that the equipment, okay, we have to provide for the equipment in the most of cases the density of the oil, gas, and water. Okay. We have a PVT curve that I get the multiphase flow at the conditional, okay, or the operational condition, pressure and temperature of the multiphase flow. In the lab, I put it in a pressure and temperature and going to expanding and reduce the pressure and having the volume of the oil, water, and gas, okay, in different pressure and temperature. This data is inputting the equipment for having this information, for getting the information in reference condition. Another thing that I have, okay, the differential pressure from the Venturi, the most of case, okay, the volume fraction of the oil, water, and gas, okay, by the techniques I showed, and the pressure and temperature. So I can have here the density of the mystery, the multiphase flow, okay? We have the mass flow rate and the mass flow rate of the oil, water, and gas, and after the volume flow rate on the mass flow rate at reference condition, okay? I'm going to talk about the regulatory context for fluid management in Brazil, okay? We have a long time of the regulation that in 1998 was created the ANP, okay, Brazilian Agency of Petroleum, Natural Gas, and Biofuels. In 2000, we have the ordinance number 1, the technical regulation oil gas measurement. This regulation was reviewed, okay, in 2013, okay. And 2015, we had one specific regulation for applying multiphase flow metering in allocation measurement, okay, or in well tests, okay, tests of the wells. That's okay. Before 2015, I can't use this technology, okay, multiphase flow metering for well tests, okay. Nowadays, I have this regulation for it. If talking about the type of measurement that we have to handle, or you can handle in the oil gas industry, we can handle, okay, the operational measurement that it's related to monitoring and control process, okay. We can have the fiscal measurement. It's a basis for payment of government, shareholders, and other taxes, daily volume products. So I have to measure the oil, gas, okay, the oil and gas in fiscal environment for pay taxes, okay. Allocation, this is the well test, okay, the test of the well for, we have this requirement too, okay. We have to measure fiscal, okay, amount of the government royalties is coming from fiscal measurement, but I have to allocate it for well, okay, because different wells has different ownership. So I have to show for the regulatory agency how much of the fiscal oil is coming from one well. The custody transference is the sale of the product, okay, regulated transfer of the product, the fluids, the products, okay, the transfer of the ownership. It has tax and requirements. So when I sell the product, the oil and the gas, I do a transfer, a custody transfer. So only for good have one example, okay? Here we have one platform, okay? We have this platform produces 2 fields, okay? Each field has 2 wells, okay? 2 wells producing for the platform. Here we have a header there, okay? each well has one line that's produced for this header, and the production go to the process, okay, for separation oil, water, and gas. Okay, after the separation, the gas and oil will go to the physical measurement, okay, the physical measure for oil, physical measure for water. But I have to, okay, in 42 days, I have to align each well for, okay, allocation measurement here, okay, for attain one requirement from the RTM or requirement from the regulation, okay. I have to align each well here for allocation measurement for know how much this well is producing, okay. In the most of time, okay, I don't know how much one well produces, but because I measure all production of the platform, but I need to know it for requirement, okay. I have to align each well for allocation measurement. Okay, what I mean that I have one process here, okay, the well is coming from the header. I can see here, we can see here the equipments, the main equipment, the separator, okay, the gas separator, the gas separated come from, go to the physical metering here, okay, the oil pass through the two stages for reducing the water content and go to the physical oil measurement, and the water go to the operational measurement, okay. So, like I said, I have to drive this each well to the test separator, okay, for allocation measurement. It's a separator for only one well, okay, for giving the potential of the production of each well to do the allocation of this physical royalty for each well. Okay, now I'm going to talk about the benefits of applying the multiphase flow metering in production of the oil gas industry. Why I'm going to use the multiphase flow meter if I can use this type of design, okay? When I use one design that I can measure in this type of way, maybe I don't need the multiphase flow meter, but I have some opportunities that I'm going to show. There's opportunity for multiphase for me or for oil gas industry applying multiphase flow metering. When you compare, okay, the multiphase flow metering here and the test separator, you can see the difference between the size, okay, the huge difference, okay, and the complexity too, okay. You imagine how many equipments or the instruments that we need to handle or you need to control for operate this type of equipment, the test separator, and here multiphase flow metering, okay. So when you apply the multiphase flow metering, we have one OPEX and CAPEX reduction, okay, the operational cost reduction and the investment reduction, okay, of the well test in relation to conventional system. That's the test separator, okay. Shorter stabilization time, okay. This equipment has a huge capacity, so need a long time for stabilization. When I align one test for them, I have to wait 1 hour, 2 hours for starting the measurement, because I have to achieve the steady state condition. Here, it's faster to get it, okay, steady state condition. No problem with foam and emulsion, okay. So we have less problem to pressure drop, okay. It's produce less pressure drop than here, okay. So emulsional too, okay, because here we need to separate the fluid. So if I produce emulsion, if I produce foam, I have to inject chemicals to stabilize the process. And here sometimes I don't have the good separation, okay? So I'm going to measure the gas with oil, okay, and water, and the oil, I'm going to measure oil with water, okay? And we are going to have a monophase equipment handle or working with multiphase fluids that it gives us uncertainty in measurement, okay, when I apply this equipment. But I need to say that it's the main opportunity that I have to reference for the multiphase flow, okay? In the field, it's difficult to have reference for it. It's the main challenge for applying multiphase flow meter. How I can verify the performance, I'm going to talk more about it. And the multiphase flow meter, if I have one multiphase flow meter for well, I have an opportunity to monitor, okay, the well in real time, okay? So I have an opportunity to see this equipment, that to see the well in the all time and getting good information, like I said about the digital transformation that oil gas industry is looking for. It's important to have instrumentation, good instrumentation in your field for getting information that it's important for getting value in your process. One thing that I have online measurement that I said, one multiphase flow meter for well, I can improve my reservoir measurement, okay? I can improve my monitoring optimization of lifting and flow, okay? Lifting the fluids. I can optimization my primary process too, okay? My process. I can increase the operational safety, okay? Because the well can produce a lot of gas one time. It's important to monitor it. When is see the onshore field reality, okay? We have onshore field in Brazil and then the world. In Brazil reality, I can show you that the multiphase flow meter give you one good opportunity for onshore fields, because when you see here, okay, the onshore field, one photograph by satellite here, you can see these dots here. Each dot is a one well. So in the onshore environment, it's cheap to do well, okay, to drilling wells. So I have a lot of wells, but small production sometimes, okay. So if I have well, I have to attend the requirement of the test, okay. I have to test the well in 42 days. It's hard to do that, okay. So the multiphase flow metering, gives us one opportunity to do this test, the well test, faster, okay, and attain the requirement deadline. So the reality is that many production well difficult meeting the requirement, okay, for well test deadline, low oil production, okay, for well, operational at the limit of the profitability. So I have one problem here, okay, the low production, we have problem to attend the cost requirement. So I have to reduce the costs, okay. The high oil viscosity, high temperature, okay, operational risk, okay, in tanks. The most of wells in onshore we test with tanks, okay. We align the well to the tank to measure the production, attend the the agency requirements of the well test. So if I use the multiphase for metering, I can have more security, because when you have a high temperature, is a problem to use. It's danger to use tanks, okay, or separators. Sometimes we send the gas to atmospheres, okay? When you use tanks, you don't measure the gas, okay? You send the gas to atmosphere. When we use the multiphase for metering, we don't send the gas to atmosphere, and you do the test faster, okay? It's the most benefits. You do test faster and attend the requirement. You have an opportunity to attend the deadline of the requirement, okay? Here we can see one example of it, okay? We can have a one multiphase for meter, one header, and test header. Okay, we have different wells here. When you produce the well, we send to production header, okay, one pipe here. When I have to test the well, I align to test header and pass to the multiphase for metering, okay, and come back to the header, production header. So another opportunity is a mobile multiphase for metering, okay? It's a project that we had in Petrobras. Is we developed with the national company, okay, Brazilian company, one mobile multiphase for metering, okay, inside of the truck, okay. We have so this equipment go to the well and testing the production of each well, okay. Então reduz the main work, increase the well test productivity, prevents the natural gas emission, okay, to the atmosphere, perform tests even in high temperatures and high viscosity, okay. In this case, in this field, we had a high viscosity and high temperature, okay. So it's a more safe than using a separator that when you work above 100 degrees, it's dangerous to use a separator, because if I have reduce the pressure, the water can expand. It's really dangerous. Here, only to show this mobile system of multiphase for metering, we can see here the power generator, okay, the control room, the cleaning system, because the oil was heavy oil, so we had heavy oil in this project, so I need to clean the system. When I finish the test, the well test, I have to clean all the meter, okay. So the multiphase flow meter is a small part here, okay. I can see here it's based on Coriolis, Venturi, okay, water cut measurement, and one electronic, okay. Is 15 meters for 2.5 meters, okay, the truck here. Okay, it's now I'm going to talk to the offshore reality, okay. In the offshore, it's Petrobras is looking for a lot of projects, is designing and developing a lot of projects in the offshore environment. So the multiphase for metering can enable application of subsea projects optimizing CapEx, okay. Subsea design more optimized. Like here, okay, when I have a satellite well, okay, that's each well, I have one line to produce the platform, okay, in this type of project. This project is interesting for when I have a high production, when I need to put the well in the right place for a reservoir, measurement like that, or to getting the right position. It's a good project, okay. When I have one reservoir that I'm going to produce a lot of oil, it's a good opportunity. But I have some projects, we have some projects that I need to reduce the investment, if I don't reduce the investment, I can't provide this production development. So I need to reduce the capex. In this case, before reduce the capex, I need to reduce the lines. Okay, the subsea line is really expensive. So I have one type here, the trunk line or daisy chain project or manifold project, that I commingle the production as in subsea environment and go to the platform, the 2 and 3 well productions. In this case, I need to the multiphase flow meter, subsea multiphase flow meter, okay, for doing the allocation measurement, a well test. I need to put each well, like I can show here, the yellow box here is a multiphase flow metering. So in Christmas tree, okay, subsea Christmas tree here, okay, is a valve system that control the production of the well, okay. It's a Christmas tree that I need to have a multiphase flow meter too, okay, for doing the well test, okay, to attain the requirement. In this case, the manifold, the same thing. So in offshore environment, the multiphase flow meter enable this type of design, okay, optimized design. When I need to use a subsea boosting, okay, the subsea multiphase pump for increase the production, the multiphase pump can reduce the back pressure, okay, in the wellhead and increase the production of the well. The most of case, I put more than one well aligned in this multiphase pump, okay, in subsea environment. So in this case, I need to apply the multiphase flow metering for doing the allocation measurement. And the process control too, okay, the multiphase flow meter can provide the process control for this multiphase pump. Another application is subsea processing, okay. That's one hot topic for Petrobras and our oil gas industry in offshore environment to do separation subsea environment, okay. We have different motivation for it, okay. One that is reduce the water, okay. We have well here. We have when you have mature fields, okay, brown fields, and we have high water cut. So it's important for me sometimes to don't lifting a lot of water, okay. Don't handle this water in the platform. So when you have one subsea separation, subsea system, process system for separation, I can separate the water, inject the water in the reservoir, okay, here, and go to with the production with less water, okay. So it's a good opportunity. In this case, I need to the multiphase flow meter here, okay, for a location measurement, okay, for well test. I need to the multiphase flow metering for control and monitor this system. Okay, I'm going to put here, okay, multiphase flow. I can put here, I can put here for a location, okay. So it's a good opportunity. And another motivation for it is to reduce the gas in the top side, okay. It's a reality in pre-salt fields. We have a lot of gas, okay, high gas oil ratio. So in this reservoir of pre-salt, so it's important to reduce the gas. So this separator separates gas here and reinject the gas. The gas in subsea environment is a fluid, okay, is a density fluid, okay, high density fluid. It can pump it for the reservoir and go up with the production with less gas. Looking overview of the resolution ENP 44, okay, is an MPFM for location measurement, okay, for well test. Okay, this regulation that we showed this regulation is for applying the multiphase format for a location. Is based on the plans. Okay, the operator must have to describe and submit the project plans through ANP. Okay, the regulatory agency, Brazilian regulatory agency. We have to report the measurement performance of the MPFM in operational condition of the field. I have, before they start the production, I have to show the ANP that multiphase format can attend this field, okay, that I want to install. I have to show then one plan for field configuration, one plan for performance verification. How can prove that the equipment is working well in metrological approach, okay? That's how the equipment is operating well. It's a challenge, okay, because when equipment, a complex equipment, how can see if this equipment is operating well in the field, and the action and contingency plan. When an equipment have one problem, when I have one contingency, what are you going to do? So I have to write it and send it to NP, and the NP have to approve these plans for starting to operate with the multiphase format. When you see the American Petroleum Institute, they talking that we have 3 technical challenges that we need to overcome and justify to cost and risk of applying multiphase formatting. Okay, we have to select and qualify the multiphase format for each application. Multiphase formatting is a specific equipment that you need to be designed for a specific application. And we have to get approval for national regulator. And we have to evaluate the performance after installation. So it's a challenge for us to evaluate the multiphase formatting in the field. So we did some tests in the platform that I'm going to show some results, okay, for testing the platform that we tested the multiphase formatting against to the separator. We tested the multiphase formatting here in bypass, okay, upstream to the separator. So we test the multiphase formatting against the test separator, okay? So we have gas, water, and oil. I'm sorry, here in Portuguese. And the wells, okay? This platform produced 7 wells, okay? The liquid flow rate is 175, okay, meter cube for hours. Okay, we have oil flow rate here, and it's important to show the water cut, okay, the BSW, the percentage of the water in the wells. We're talking about the brown fields, okay, the fields that you have a lot of water, okay, in the liquid phase. So it's a huge, it's a tough environment for multiphase formatting for oil measurement that I'm going to show. And the gas is 750 and 2,000 meter cube per hours. So here we can see, I'm sorry, here we can see the reference of this test, okay? Turbine flow meter for oil, magnetic water meter for water, okay? Orifice plate for gas. It's the instruments from test separator, okay? That's test separator measurement was correct, okay, for the reference, okay, by here the measurement, okay, the volume measurement of oil, but we need to, in the oil current, I need to take out the water, okay? 1 minus BSW is, we take off the water, okay, percentage of this oil, and the shrinkage factor, okay, for shrinkage of the oil for the reference condition. And the water, I have to, it's a measurement of the water, okay, for the metering, plus, okay, the amount of water can stay here, okay? So this amount of water in the oil phase go to here to correct the water flow rates. And the gas and the orifice plate, okay, I have to discount here the steam percentage of the water, okay, because part of the gas has water, steam water, so I discount here, and I put part of the gas, plus here part of the gas inside of this oil here, so this part of the gas go to the gas. So if the oil is shrinkage, part of the oil turning gas, so plus here. So if you see here, you can see here the petroleum flow rate, okay, and the gas flow rate. We can see that in blue, the multiphase flow metering, okay, and the orange, we can see the test separator results, okay. So we can see the repeatability of the multiphase flow metering is better or smaller than test separator, and but the average is the same, okay, for gas. And for the gas, the same thing happen, okay. The multiphase flow metering is more stable than the test separator measurement. It's because the process, okay, the separation process has this instability. When you can see here, okay, the test separator results against the multiphase flow metering, okay. So here we can see, okay, the systematic error between the multiphase flow metering and separator is less than 10%. Okay. Here we can see the BSW, absolute error of BSW. Okay, so we can see here the absolute error, the BSW, the multiphase flow metering. Okay, compared to the test separator. Okay. So we can see that most of the result is below to 8%. Okay, we can see here. Okay, here is the oil flow rate. Okay, the multiphase flow meter against the test separator. If you can see the relationship between the BSW error and the oil gas uncertainty, okay, oil gas systematic error, okay. This well here, okay, each dot here is one well, okay. This well here, you can see this well is the most error in BSW, the most error in systematic error in oil flow rate too, okay. Because the multiphase flow meter measure the liquid flow rate, the BSW percentage, and the gas flow rate. The oil flow rate is coming from coming from liquid flow rate and the BSW percentage. So the error between liquid flow rate and the BSW percentage is here, okay. We can see the most error in BSW is the most error in the oil flow rate, okay. It's a combination of the uncertainties. So the wells that has the less error in BSW, the less error in oil flow rate too, okay? It's important to see. And the gas flow rate, our wells, the systematic error less than 25%. Now I'm going to talk about the challenge and opportunity for research and development innovation in multi-phase flow measurement area. Okay, it's I'm going to talk about we are studying in this case. I think it's important to show for this community, okay, that what the industry is looking for, what the industry is claim about, okay, multi-phase flow meeting, for inspiring you to study these topics, okay. We have one pre-salt scenario in Brazil, okay, that's a good opportunity for oil and gas industry. We have a field with a lot of oil, okay, oil properties in ranging 28 and 32 API, okay, gas oil ratio between 200 and 400 millicube for millicube. 40% in mole CO2, okay, percentage of CO2. This is a challenge for us, okay. That's 6,000 well depth, pressure 300 bar, and temperature 80 degrees. When you're talking about to the pre-salt scenario, that we talking about high total flow rates, volume flow rates. That's a high flow rate. Okay, we have 58,000 barrels, a very high formation water salinity. Okay, in the variable water salinity, because we are going to inject seawater, so the water salinity will go down, and the high CO2, and we are going to separate the CO2 and topside and inject CO2, so the percentage of CO2 in reservoirs go up. For multi-phase format, we talking about the high challenges. Okay, we need to because the high flow rate, we need a high large high bore multi-phase format. The high salinity give us high attenuation for a lot of sensors. The variable water salinity is a problem for oil measurement, a lot of things. The CO2 will be a supercritical fluid, okay, in the subsea environment. So nobody knows how the multi-phase flow meter will handle the multi-phase flow with CO2, high CO2s, because CO2, we are going to have a low viscosity like a gas, but a high density like a liquid, okay? So we have to validate the state of equations, uncertainties about the prediction of fluid properties. So it's a challenge, okay? We have to study to Ventura and Vicont how these equipment can be calibrated, okay, in this environment. So we have to study a lot of, we have to study methodology to performance verification of the multi-phase flow meter in the field, okay. We have to prove that it works well in subsea environment. One thing is we can use a reconciliation factor. We can use a sensor redundancy, okay. We can use a virtual metering, virtual flow metering, okay, for performance verification or contingency, okay, based from physical model or data-driven. Okay, you can use it to digital twin for performance verification, failure detection and prediction and detection of multiphase flow measurement deviation. So it's we looking for to produce this solution for applying this technology. So about the conclusion, okay, the multiphase flow metering, I'm gonna pass through this part because I wrote a lot in it, but we consider the ultra deep water environment the return on investment in use of multiphase flow metering for a location may in fact high in Brazil in some scenarios, okay? So it's important to apply multiphase flow metering for oil gas industry. So I'd like to finish here to listen you and answer questions. I'm really pleasure and glad to be here and to discuss with you this and stay with you for answer the question. Thank you.
Thank you very much, Luis Otávio, for this very nice presentation. It's really a huge problem and a lot of opportunities for us researchers, of course. And also thank you for being so on time. Excellent. So we have 20 minutes for questions now. We have some questions selected here from the YouTube's web chat, okay? I will start with this question from Bruno Portato de Moura. What is the perspective of adopting new types of flow measurements by Petrobras, especially those without radiation? And also the question of André Quintino, following Bruno's questions, specifically about virtual flow metering using machine learning approaches. What's the perspective of using this technology in production wells?
Yeah, it's a reality nowadays. Okay, we use for predict virtual metering. Okay, we are applying it because the most of our fields is satellite wells that we don't measure the well all time. We don't have instrumentation, multiphase flow metering for all wells that we have. So nowadays we applying virtual metering, okay, in some wells for monitoring and optimize this production. Okay, we understand that we can space for improve our algorithms that we had, okay, by machine learning, by physical models. So it's a good opportunity, I guess, okay, it's a good opportunity to invest in it and study this topic. Is mute, Professor Oscar, is mute you use mute.
Oh, we never learned this stuff. Sorry about that. Luis Otávio, following Bruno's and André's questions, one of the issues about using this kind of machine learning tools, flow measurement, is that you need data, because these techniques, they cannot interpolate anything. They just extrapolate, sorry, they can't extrapolate anything. They just interpolate. So you need actually data from labs or from production fields in order to train these machine learning tools. So my question is, does Petrobras or does the oil industry have enough data available to share with the universities that might help in this development?
Yes, of course. Nowadays we have this data, okay, storage. That's we have it. We have an opportunity to study this topic. I think, and sometimes, in my opinion, okay, we can't stay out of the multiphase flow metering for some application. Okay, we need the instrumentation for allocation measurement. Okay, it's a requirement. But I understand that virtual metering is important because some fields don't need the multiphase flow meter, but need to monitor the well. We have a lot of data, but I understand that we need to understand how more instrumentation that I need to put in the well for getting the best or the best result of the virtual metering. Sometimes only the pressure and temperature in the bottom hole, the pressure, the temperature in top side, and the choke position like that is not enough for getting a good algorithm. So it's important to know how the instrumentation that we need more for getting the most system. Okay.
Yeah, quite a challenge. There is another question here from Lydia Gaider Franco. In new installations, is the cost of installing a multiphase flow meter higher or lower than the cost of a test separator with all the measurements instruments? So what's more expensive?
Okay. If you put the same sides, okay, the same place, okay, the multiphase flow meter, the separator, the multiphase flow meter is cheaper, okay, the capex, the opex. But I need to say that we can't be out of we need the test separator, okay? If I have the multiphase flow meter, I need the test separator because the test separator have some utilities, okay? Sometimes I have to optimize some chemicals, something I need. And one problem that we had, the test separator is the main reference for testing the multiphase flow metering, okay, nowadays. Because that, I show you some methodologies that we study for, don't need the test separator for performance verification of multiphase flow metering, okay?
Okay, there's another question here from Marcielo Oliveira. I think he got that one when you were presenting, it was at the beginning, when you were presenting the separators, you know, the separators you have in the platform. Which is the point of separating the phases in such multiphase flow meter?
I'm sorry, I didn't understand that.
Yeah, which is the point of separate the phases in such multiphase flow meter? Which is the point of separating the phases? What do you do with that? I mean, in the platform.
What I separate the phase? Okay, only the residence time and the gravitational force, okay? When I put the oil, gas, and the water inside of the separator, okay, we reduce the pressure, okay, and we have the water, the oil. The water has more density than oil, so the water go down, okay, and the oil in above, and the gas, because the pressure reduced, the gas go out of the liquid. It's only that. It's simple.
Mr. Otávio, I have a question myself about exactly about Marcelo Oliveira's question. That's we know that sometimes the gas comes together with the oil, dissolved in the oil, right? So you told us that in the separator, okay, there is a pressure reduction. Then the gas actually separates from the liquids. I mean, from water and oil, because of the density difference, of course, and because of the thermodynamic states of these matters, right, in the separator. But how can you assure that you still don't have a good percentage of gas still in the oil, dissolved in the oil?
Yeah, it's one because that I have different stages, okay? The first stage, one pressure. The second stage is less pressure, until to have one oil that I can send to the tank, okay? Imagine the tank of the platform can't receive oil with gas, because when you put it in the atmosphere, okay, pressure, if you have gas, we have one is dangerous. So I have different stage for getting one oil a death oil, or that we say the oil without gas, okay, in the atmosphere pressure.
Okay, very good. We have here in the room alive, we have some presenters of our measurement and instrumentation session. Does anyone would like to make any question to our presenter? Okay. So, well, I have another question regarding the multi-phase flow meters. We know that we have some products in the market you have shown us that use many different measurement principles. I mean, aspects. Like we have radioactive thermographers, or we have electrical impedance, and we have some kind of, we can even have Venturi pipes there all together to give us the information. However, I remember that some time ago, I was talking to some Petrobras colleagues, and one of the matters is that by that time, at least, there was no multi-phase flow meter that could actually handle all kinds of flow patterns, all kinds of volumetric fractions that we actually have in practice. And you have actually presented us that there are so many challenges, like the salinity of the water that comes together with oil and gas, and many other issues like the CO2, the supercritical CO2. So can you tell us if there is any kind of product in the market that actually, regardless the price, can solve the problems, or we still have a gap there for research, for development of a multi-phase flow meter that would be more efficient, I mean, and economic?
Yes, nowadays we understand that we are not right that in the market can solve all the challenges that we have in pre-salt. Okay, we had presented we have presented this challenge for the market. Okay, nobody can show us about, okay, if it's possible to handle that we have. So I understand that the CO2 and the high salinity is really a problem that sometimes I need to only qualify, okay, one equipment the market. Sometimes I have to develop some solution, okay, or mathematical model. Sometimes it's only mathematical model, okay. We have to calibrate the state of equations of states, okay, that's for handle it. Sometimes I have to improve the instrumentation, okay, for measurement. But I'm not right that the market can solve this problem nowadays.
Okay, there's another question here from, I think we still have time for one or two questions more. This is from Eduardo Santos. How close we are to the reality of having one multi-phase flow meter per well? How Petrobras is dealing with the new field developments in the pre-salt?
It's the connection failed. I lose part of the question.
I'll try again. So Eduardo Santos, okay. He's asking, two questions actually from him. How close we are to the reality of having one multi-phase flow meter per well, okay. the smart well issue. And the second, how Petrobras is dealing with the new field developments in the pre-salt.
Yeah, the first question is, I think we are going to, the oil gas industry is discussing to reduce the people offshore, okay, reducing it's POB 0, is no people offshore, is our target in the future. So I understand that for it we need to increase a lot the sensors, okay, the instrumentation. And you need to, you need to increase it to the everything, okay, we need to turn better, okay, our equipment, but you need to increase the sensor. So I think we are going to walking for having multiphase for meeting for each well, okay, but it's not a drive nowadays. Our drive nowadays is only for I show the subsea environment when I have optimized design like manifold, okay, in trunk line. But I think the oil guys industry is going to reduce people offshore. I need to increase the sensors. How about the pre-salt project? We have some projects in pre-salt nowadays that we studying to improve our projects with new technologies. The multiphase for metering is in discussion to put in some projects for attain the requirements sometimes or better the production or optimization.
Very good. I have here Marcio Martins. Would you like to say anything? I can see you have raised your hand. Yeah.
Yeah. Yes, please. I just have a question. Thank you, Luis, for the outstanding presentation. I'd like to know. You have such a flow meter that separates phases, okay? And however, you have the situation where you you must measure the legal measurements. You have the legal measurements, and on the other side, you hear a lot the persistence problem of the legal measurements, such as, for example, water and gas stream. So, what's the state of the art in all of this process, from the production to the legal measurements? Because everyone here is trying to have one multiphase flow meter, a real one, if I say like this. But after you separate the phase, we still with the problem. The problem persists of have multiphase strings in the legal measurements. Okay, what you can say about this?
Yeah, the multiphase for metering. If I understand your question, talking about the multiphase for metering, the test separator, and nowadays in Brazil, and applying to multiphase for metering for requirement, we starting to use this technology. Okay, it's new for Petrobras, it's new for ANP, okay, Brazilian Regulatory Agency, but abroad, okay, in the Norway, this technology is applying a lot. So everybody knows, everybody using for this application, allocation measurement. When you see, okay, the separator, the test separator measurement and the multiphase for metering, when you compare, it's the same thing, okay? And you told one right thing, that the test separator sometimes produce oil with a lot of water, so I have to measure the oil with water. I don't know what's the performance of this measurement of oil, because the water in oil impact this measurement. And the gas has a lot of liquids too in the test separator output. So when you're talking about the multiphase flow metering, sometimes people say, I don't know if the equipment is good or not, When you put one in the lab, you can see the performance of the equipment. The challenge is, when I put it in the field, how can verify this performance, okay? Because I'm going to use this test separator that I use now, but it's not a good reference sometimes. But what I have now, so we have one challenge that I need to solve. It's a methodological rastreability, okay, of the multiphase flow, okay? How can do this rastreability, metrological rastreability? Because for monophase measurement, I put you on the lab that has a rastreability in one place, okay? But multiphase flow metering don't have it nowadays. So I saw some groups in the Europe studying this multiphase flow measurement metrology, like that, okay? We have to study it, how to do it, because it's important for application of the technology.
Okay, so I'd like to thank you, Luis Otávio, for this very, very nice presentation. It's very important for us from the academia to listen to a professional like you that's actually facing the real challenge in real life, in production. So thank you very much for this very nice overview about multiphase flow metering and all the challenges that are behind us. So the measurement and instrumentation session must carry on, must go on. So Luis Otávio, thank you very much. And now we go to the presentations. We have scheduled 7 presentations in this session, this measurement and instrumentation session. I just would like to remind the presenters that we are going to have 15 minutes for your presentation plus 5 minutes for questions. Okay, so let's try to get it right. Okay, 15 minutes for the presentation and plus 5 minutes for questions. Okay, and also thank you the audience. We are having a very nice audience in this session, and I'm pretty sure that you are gonna have presentations now also very interesting as the keynote speakers. Well, let's go to the first presenter here. It's Johan Castro. He's a PhD candidate from the São Carlos School of Engineering of the University of São Paulo. He's a member of the Industrial Multiphase Flow Laboratory at the University of São Paulo at São Carlos campus. So he's going to give us a talk about sound propagation in turbulent air-water pipe flow, part 1, single phase measurements. So Johan, please, the audience is yours.
Just a moment, please. I will.
Good morning for everyone.
Screen.
I am Johan Castro, a PhD student of the São Carlos School of Engineering at the Industrial Multiphase Flow Laboratory under the supervision of Professor Oscar Rodrigues. And today I will present my work, namely sound propagation in turbulent air-water pipe flow, part 1, single phase measurements. So in the offshore, in the petroleum industry, it is very common practice the use of gravitational separators. And these separators obtain the offshore flow, typically composed by water, oil, and gas. Hence, by the gravitational action, each of the phases will separate it and storage in different parts of the tank. For example, the water flow stays in this part, and the oil flow is in the right part, and the gas flow is in the upper part of the separator tank. However, the gas pipeline transportation could have some problems as liquid entrainment and the gas flow measurement. The most common technique used in the petroleum industry corresponds to non-intrusive techniques, for example, ultrasonic flow meters. this type of flow meters is composed by an emitter and receptor, and the emitter could provide a very short wavelength wave which travels to the theta direction until the receptor with short wavelength. Hence, when the flow file is applied, this ultrasonic sound wave are delayed in relation from the emitter to the receptor, and hence this delay is correlated to obtain the flow velocity and the mass flow rate. However, under the presence of the carryover phenomena or two-phase flow, or in the presence of the water drop, there is an increase on the number of interfaces, which causes an increase on the number of the attenuation of the sound wave, and hence there is no correct operation of this type of ultrasonic flow meter under two-phase flow conditions. One solution to this is proposed on different works from the literature as Potzik and Gorny as long wavelength flow meters, which consist in a sound source as a loudspeaker typically, which emits a long wavelength. Typically, the frequency of this wavelength is below of the first harmonic of the spectrum. Hence, these wavelengths are affected by the flow field, and then these effects are monitored in different positions of the pipe flow by different high-sensitive presence sensors. Hence, based on the correlation of each pair of these microphones, for example, this one to this one, the first with the third, the first with the fourth, could provide the amplitude and delay, the sonic flow meter with the sonic velocity. With the core, we would analyze the more simple case, phase flow, under it's applied length emitted by the loudspeaker and measured at some distance at different positions with the high sensitive pressure sensors. The methodology consists of the experimental data, and then this experimental data are collected and processing using spectral analysis, which provide a better explanation of the noise characterization due to the flow file and the external noise. Hence, it is developed a filtering process and noise reduction of the signal. Then finally, a correct signal characterization, phase estimation, based on the current method typically used in the literature. Now, for our case, the experimental apparatus were based on the methodology of Potzik, Gord, and Gorny, with similar works in this area. The experiment is of a turbofan which provide the flow. Our experimental apparatus have the possibility, the use of water injection, but in this work we not use. We have a sound source located at the bottom of the section, and in the upstream positions 4 microphones, 0, 1, 2, and 3. And the open end of the tube, we have a turbine anemometer which provides the lectures of the flow velocity in an experimental way. The sensor assembly, it were necessary to provide a 3D printing support also for the loudspeaker and the microphones. This because we need to provide a very concentrated sound into the pipe flow. Hence, the upper support composed by the upper support and the bottom support could fix it, the loudspeaker, into the pipe flow in the perpendicular direction of the airflow, and hence providing a powerful sound wave along the upstream and the downstream direction of the pipe flow. In a similar way, the 3D printed support for the microphone have various insulation cavities which is filled with foamy materials, which provide very strong insulation for the external noise, and hence this support provides the same position of every microphone used in this experiment under the radial direction. So, in the first part of experiments, we try to characterize the noise caused by the flow field of our experimental data. So, it is observed that under no acoustic signal, the noise is characterized and is spread over all frequency spectrum. It is observed that for the frequencies, this noise influence, which is a way to work in their acoustic signal under this range or the frequency. We try to use a long wavelength over the band 0 to 2 kHz. In that way, we use a sweep sine pulse over the 1000 Hz. Hence, it is observed for this velocity exceeds the swings of the energy noise, in this case white noise, of the flow field. However, it is still easily recognized that our sweep sine pulse is very easy to see in the frequency spectrum. However, when we increase the velocity of the flow field, there is an increase in the energy noise presented over all spectrum. However, it is necessary to provide some bandpass filters and robust techniques or digital signal processing to compute correctly the phase of the signals, and then the acoustic, the sound velocity and the flow velocity. To do that, we try to use the coherence analysis presented in Mueller and Govindan, which consists of the computing of the cross spectrum and the out spectrum of each pair of the signals, defining in that way the coherence function. Based on the maximal value of this coherence function, we determine the phase of the at which the frequency of the maximal coherence correspond to the phase of the signals. So, as can be seen in the figure, we have the coherence function, and we determine in a graphical way the maximal values for each pair of the microphones of the coherence function, and then it is observed that the frequency match of each pair of microphones 01, 02, and 03 correspond to 1550 Hz. And then from this frequency we determine at the same position the phase of the signal, which correspond to the lag between them, and for all range of velocities tested in this study. So, in the table 1 are presented all the flow velocities tested in this study, varying from 0 to 30 meters per second. And then we have the phase measured for each part of microphones. However, I mean to analyze the possible effects of the flow field, we choose the Reynolds number and the Stroh number because it relates the properties of the fluid, the frequency of the spectrum, and the flow velocity and the pipe diameter. And it is a correlation from the phase lag and the Reynolds number, and an inverse relation with the Stroh number. This suggests that the delay between the collected signals could not be estimated based on the direct way or proportional direct relation with the phase, with the calculated phase. This because the flow field causes strong influence on the sound wave. However, it is necessary to provide another methods to improve the system sensitivity and immunity to noise. I mean to increase the precision measurements, and later, and in the other part, it is necessary that
JEM 2021.
Oscar, pode entrar com a live para as perguntas. Oscar, pode entrar com a live para as perguntas.
Bom, então, sorry. So we had the Johan Castro presentation, and we don't have any question. We don't have any question here from the chat. So I'd like to ask our other presenters here in the room if anybody would have any question. If not, Johan, please. What do you think that are going to be the most challenging issues you're going to have when you go to two-phase flow in this experiment?
So in these experiments, a great challenge is try to correlate the variations of the influence of the two-phase flow interface, or considered as a elastic interface, which could influence the sound propagation. Also in the wave characteristics, attenuation, and sound velocity, and delay, and other reflections, reflection coefficient, attenuation coefficients. This is a very great challenge with the two-phase flow, really.
Okay, so I think we might finish your presentation here. So I'd like to thank you, Johan Castro, for your very nice presentation. Thank you very much. So now we are going to the next presenter of our measurement and instrumentation session. It's going to be Leandro Amorim from the University of Campinas, Unicamp. He belongs to the group of Professor Eugenio Rosa. So Leandro, please, he's going to present the work entitled Automated Quick Closing Valve System for Three-Phase Flow Hold-Up Measurements. So let's go to your presentation.
Okay, thank you, Oscar. Good morning, everyone.
Excuse me. I think you're going to have your presentation given in the YouTube, the recorded one. Then after the presentation, we are going to come back for the questions alive. If I could understand Professor Marcio Martins correctly.
Exactly.
Okay.
Oscar,
So we are going to project now your presentation, the recorded one at YouTube, and then after that we come back. Okay.
Closed valve system for three-phase flow hold-up measurement. This work was done by Professor Eugênio Rosa, Professor Ricardo Maza, the student Jordan Leite, and me, Professor Niederauer Mastellari, at the School of Mechanical Engineering, Unicamp. Key-closed valve is a widely applied technique on laboratory multiphase flow studies. It can be used as a reliable method of calibration to pick up the volumetric phase fraction of the phases on vertical column when the steady state of multiphase vertical stream is established. It is formed by a transparent section delimited by fast-acting valves. On laboratory three-phase flow studies, thousands of trials are performed. Hence, is suitable to automate key-closed valve system for hold-up measurement. With the technology of motion control, precision axis, microcontrollers, sensors, and supervisory systems, it was possible to perform the automation of the experimental setup. For this, an optical assembly is precisely moved up and down around the glass pipe, measuring directly fluid column heights based on the fraction index of the fluid inside the pipe. However, these direct measurements are affected by the foam and droplet coalescing, as we can see from the picture. To overcome these effects, pressure measurements are performed to indirectly obtain the equivalent water height. These direct and indirect data are fused using maximum likelihood estimation algorithm. Merging the data with maximum likelihood estimation, uncertainties are minimized. This work presents the design of the automated key-closed valve system for hold-up measurement of three-phase flow, air, kerosene, and water. The key-closed valve apparatus can be seen by the picture. The main parts are the transparent glass section, two key-closed valves, the step motor upside, two pressure transmitters. The key-closed valve system was designed to operate on a mainframe with a 30 meters long three-phase line for upward flow. The glass pipe has an inner diameter of 26 millimeters. And the optical device is on a platform that slides up and down, guided by the precision ball screw and two steel rectified shafts with negligible backlash. The optical sensor is composed of a red laser diode and a set of 6 phototransistors type BPW85C. The electron signal of each one phototransistor is amplified by one operational amplifier AD8608. The laser beam crosses the pipe and the fluids being detected on the other side of the tube by the phototransistors. The picture exemplifies when the laser beam crosses the pipe filled with water. Each one phototransistors is associated to a specific index of refraction. The maximum likelihood estimation is used to fuse the signals. The uncertainty is inversely proportional to the light intensity received for each photodiode in relation to the whole set. The figure shows the scanning of three-phase column with phototransistor voltage on the left and data fused on the right. It's possible to identify the water and the kerosene column heights. There were liquid bubbles adhered to the pipe. This caused interference in the measurement. The methodology for calculating holdups. The optical device scanning while going up makes the direct measurement of the water column, LW, and its uncertainty, ULW, and the total liquid height, LL. At the same time, the pressure transmitters indirectly obtain the equivalent water column. From this data, it's possible to calculate two new redundant water heights at LWP1, LWP2, and their variances, UP1 and UP2 squared. With this set of direct and indirect information, it's possible to infer one more precise water column height using the maximum likelihood estimation algorithm. First calculates gamma, apply the average, and calculate its uncertainty. By this set of information, we will calculate the water holdup. The water holdup is calculated as well as its minimized uncertainty, UHW. The other values, such as holdup and kerosene holdup, are consequently obtained. To validate the operation of the kick-close valve system, tests were performed controlled by the supervisory system. 3 different arrangements of volumetric fractions were prepared as shown in the table 1. In this table, 2 measurements were taken from each trial. It's possible to see the data obtained indirectly and directly in the calculation of the holdups. AJ, holdup of air, HW, holdup of water, HK, holdup of kerosene and their uncertainties. It can be seen that the system measures precisely low height columns. In the last test, the holdup of kerosene was less than 1% of the total column. A test was prepared to study the effect of the fluid agitation on the measurements. The column is initially well defined with total liquid column height 337 millimeters, water column height 302 millimeters, and kerosene column height 35 millimeters. A set of the measures was performed after 10 minutes of air injection, flow rate 15 liters per minute. The system was programmed to obtain measurements every 2.5 minutes until 15 minutes after closed valves. Through the glass pipe, it's possible to observe that liquid particles adhere to the surface of the glass column, so there is a decrease in the liquid columns. Analyzing the table data, the indirect measurements vary with their range, and the direct values of the heights of the water and the kerosene and the total liquid height vary with the time. Water decreasing and the total height column increasing, which is expected with the coalescence of the drops. Conclusions. The objective of this work was to present a key closing valves automated system for hold-up measurement on three-phase vertical experimental setup. An optical device was developed to direct measuring the heights by the index of refraction of each phase distributed internally to the glass tube. Two more indirect pressure measurements of the liquid column were made. The maximum likelihood estimation algorithm was used to merge this data to calculate hold-ups with an appropriate compromise between reliability and accuracy. Validation tests conducted by a supervised system show that it's possible to use this method to automatically measure small columns of less than 1% of the total column accurately. Thank you. Thank you.
So thank you, Mr. Mastellari, for your very nice presentation. This can be really a very nice tool for laboratory experiments, of course. And I have a question about your technique. One of the issues we have in three-phase flow is that gas and water usually get emulsified in oil. This can happen. So how can the technique handle the time the phases need to separate?
It's a question that we don't answer today. The truth, we spend time to separate the phases. It is an parameter of this problem. Now we expect the 10 minutes for each test to obtain the holdups, but sometimes we expected that we need more time to work with this problem. And actually, semi particles will be inside the water, kerosene in water, and the water in kerosene. But we expected a time to minimize these quantities.
See, kerosene is not a very viscous oil, so you might not have a very strong effect of emulsification, but sometimes when you are dealing with real crude oil, that could be an issue, or so that's the reason of my question, but thank you very much for your answer. And there is another question here from Clayton Mendonça that actually is related to my question, by the way. So in which degree the foam and the droplets coalescence interfere in your system? For example, effects just by adding certitude, or is it a limitation? I think it's related to experimental uncertainty, the effect of foam and coalescence. How could that interfere in your experimental uncertainty?
We mix direct and indirect sensors exactly by this. Using pressure sensors, we can calculate the heights without effects of coalescing, kerosene water interface coalescing. So we expected when we use intensively these apparatus, that the uncertainty is less than the uncertainty of pressure sensors. 2% by 2% of the total column, 2 meters, né? Plus, minus 10 millimeters of error.
Motions in gravitational equipments?
I don't know. The separation system is more robust, no? I think the industry don't will stop this system to measurement. But I think that the multiphase flow meters, né, electronic, using data fusing, combining with Coriolis, and the other techniques, electrical, né, capacitance, resistance sensors, probably we will have a very robust and reliable equipments. I expected it.
Okay, so I thank you again for your nice presentation, and now we move on to the next one.
Okay.
Thank you very much. The next presentation is going to be given by Ana Luisa Beltrán Santana from the UFPA, Technology University, Federal Technology University of Paraná. She belongs to the group of Professor Rigoberto Morales. She's going to present a work entitled Experimental Characterization of Liquid Thickness in Downward Vertical Air-Water Annular Flow. Okay?
My name is Ana Luisa, and I'm here to talk about my work titled Experimental Characterization of Liquid Thickness in Downward Vertical Air-Water Annular Flow. My presentation will start with a brief introduction to the flow pattern investigated in this research. Then I will present the methodology used in the experimental tests, and at least I will present the results and the final remarks of my work. The annular flow is characterized by a continuous fast-moving gas core with a liquid film that flows around the pipe wall. This flow pattern is often observed in industrial applications such as chemical reactors, evaporators, and condensers. The gas-liquid interface is covered by waves that were formed due to high interfacial shear stress between the phase, and can be classified by disturbance waves, identification used for the large waves, and ripples, which are the small waves that cover the base of the liquid film. Furthermore, it has been observed that the waves provide entrainment of liquid to the core flow due to the interaction between the liquid and the gas phase, and affect the interfacial shear friction that influence the pressure drop, the two-phase transfer of momentum, mass, and heat. Several studies analyze and propose correlation for different orientations of the annular flow in the literature. It should be noted an extensive number of studies for upward vertical annular flow and a lack of attention to the downward direction. Therefore, the downward vertical annular flow still needs an investigation. In this regard, the main goal of this work is to feature the behavior of liquid film in air-water downward vertical annular flow. An apparatus to carry out experimental tests in annular flow was designed. The ring consists of a test section made of transparent plexiglass with an internal pipe diameter of 26 mm and 1.2 meters length. The work fluids used in the tests were air and water at ambient pressure and temperature, a non-intrusive ring-shaped dual condense sensor, and an intrusive capacitive 16 by 60 wire mesh sensor were deployed to measure the liquid film thickness. 9 combinations of gas and liquid superficial velocities were used in the experiments. The water superficial velocities ranging from 0.05 meters per second to 0.15 meters per second, and the air superficial velocities ranging from 15 meters per second to 25 meters per second. All the combination of phase superficial velocities used in the tests fall into the annular flow pattern as plotted on the flow map proposed by Barnea et al. In 1982, and also the combination of phase velocities fall into the different annular regimes as plotted on the annular regime map proposed by Zadraz et al. In 2014. These graphics show the liquid thickness time signals for the ring sensor and wire mesh sensor. Analyze the liquid thickness topological behavior. It can be observed the presence of sharp peaks and more stable interface between the peaks. These peaks represent the waves in the gas-liquid interface, probably being disturbance waves due to the high amplitudes observed in the time signals. Compare the liquid thickness time signals of the ring sensor with the wire mesh sensor. It can be observed a difference in the peak amplitudes between the same combinations of phase superficial velocities. This difference may be due to the greater sensitivity of the wire mesh sensor, since this sensor has a major number of measurements in the cross-section area, thus capturing the interface in higher detail when compared with the mean volume area of the ring sensor. Although the difference in the time signal, the liquid characteristics were estimated by an average showing good agreement between the ring and the wire mesh sensor. Depending on the combination of phase velocity, the wave can be more frequent and with higher amplitude. These waves were formed due to the gas sharing action on the interface. The different behavior of the liquid thickness time signal observed in the flow combination 7, as it can be seen in figure G and P, which presents an interface more stable in comparison with the other flow combinations, it's probably due to the different annular regime of this combination as present before in the annular regime map. Figure A shows the average liquid thickness as a function of the phase superficial velocities. It can be observed that the mean liquid thickness is affected by the phase superficial velocities. An increase in the liquid velocity leads to an increase in the mean liquid thickness, and the decrease in the gas velocity also provides an increase in the liquid thickness. As a result, the tiniest liquid thickness is observed for the flow combination with the smallest liquid velocity and the greatest gas velocity. On the other hand, the liquid film velocity has an opposite tendency with the phase superficial velocity, which tends to increase with the increasing of both phase velocities as present in figure B. With the measurements using wire mesh sensor, it's possible to create a representation of the liquid thickness and evaluating the behavior of the liquid film around the circumference of the pipe, as present in this figure. These are some videos for different combinations of flow rates used in this work. It can be observed the presence of disturbance waves with velocities and frequency of wave dependent on the phase velocities. Also, it's possible to observe the presence of entrainment of liquid in the gas core and the bubbles in the liquid film. The experimental data are compared with a prediction of liquid thickness using a momentum balance. A momentum balance in downward annular vertical flow is presented in equation 1. It was assumed fully developed liquid film, no entrainment of liquid to the gas core, equilibrium condition between gas-liquid phase, uniform liquid film thickness, uniform liquid film velocity profile, and isothermal and incompressible flow. From equation 1, the liquid thickness can be estimated using the flow conditions and physical properties of the working fluids. These figures show the comparison between the current experimental data for both types of sensor with a prediction calculated from the momentum balance, with an agreement of more or less 10%. For the comparison with average velocity obtained experimentally by cross-correlation of the time signals, an underestimation of 30% is observed. An exception is observed for the smaller combination of phase superficial velocity. This better agreement probably can be due to the different annular regime flow of this combination that provide an interface without disturbance waves, and it's better predicted by the momentum balance due to the consideration assumed that the liquid film has a constant velocity. Due to the presence of the disturbance waves, which have a higher velocity when compared with the base film velocity, the determination of the mean velocity by the cross-correlation technique is more affected. So, my final remarks. In this work, experimental characterization of downward vertical annular flow was carried out using non-intrusive and intrusive sensors. The experimental results were compared between the two sensors and a momentum balance, and a good agreement were observed, and also important parameters such as average film thickness and wave frequency, wave velocity were measured and evaluated. Thank you.
Okay, so Ana Luisa, thank you very much for your very nice presentation. We have some questions here. The first one is from Marciele Oliveira. Ana, how small should be your white mesh to have a good resolution to estimate the thickness?
In this test, I used a 16 by 16 wire mesh sensor, and the results show a good representation of the average film thickness. And in comparison with the other sensor that I used, the conductance sensor, this 16 by 16 wire mesh was good.
16 by 16, right?
Yeah.
Okay. Does anybody here in the Google Meet room would like to make some question to Ana Luisa?
I would like to make some question.
Okay, Bruno.
I would like to ask if I see correctly, there was a deviation of 30% of one of between your measurements and in in the model. Why is that?
Okay, this occurs because the technique used to calculate the velocity is by cross correlation, and if you see the time series and the cross correlation cut the velocity of the disturbance waves. So when I compare with the model, which propose a correlation for velocity in the mean film, the base film, this comparison is not fair because I am comparing with the velocity of disturbance waves, which is more higher than the velocity of the base of the film. This is the difference that you observe in the graph.
Just one more thing. Maybe there is a room for you to propose some corrections since they are systematic deviated.
Sorry, could you repeat, please?
Maybe there is a room for correction of the model since there is some deviation, systematic deviation.
Yes. This is a very initiate comparison with a simple model, and the further analysis, I will propose a new correlation to predict more accurately this velocity.
Okay, thank you.
Thank you for the question.
Okay, would anybody else in the room like to make another question to Ana Luisa? We still have some time. I'd like to ask you a question. Okay, flush-mounted conductance ring-shaped or wire mesh sensors have been already used for measurement of liquid film thickness in upward or downward gas liquid nanoflows. Usually the results we get from this technology, usually it's this big, higher amplitude, higher thickness, the rolling waves, the liquid film related to rolling waves. I could see that you have measurements, a sensitivity of around 1 millimeter, right?
Okay.
Is that correct? It's about that, right? The uncertainty you have.
Yes, it's correct.
Okay, so my question is if it would be possible to improve this kind of technology to obtain information about ripple waves, these very, very small, high amplitude, high frequency waves that we see that develop sometimes on the rolling waves, the ripple waves. Do you believe that it's possible to improve the spatial sensitivity of this technology in order to measure the properties of ripple waves too?
Is the next step of my investigation. Now I am performing some tests, and I will analyze the time series, and it's possible to characterize the ripples on the interface of the film. And yes.
How do you plan to do that? I mean, what's the strategy to do that?
Well, now the idea is to analyze the time series and compare with the resolution of the wire mesh sensor, but in now I am also performing tests, and the analysis will be done soon.
Okay, so I'd like to thank Ana Luisa again for her nice presentation, and let's move on to the next one. The next one it's going to be presented by Eduardo dos Santos. He's also from the Federal Technology University of Paraná. So he's going to present the work evaluation of conductance flow sensor for liquid thickness measurement in annular flow. So let's go to Eduardo's presentation.
Santos. I am a researcher at the Multiphase Flow Research Center, Curitiba, Brazil. In this work, I will report the evaluation of a conductance flow sensor for liquid film thickness measurement in annular flow. The motivation of this work lies in the need for accurate measurement techniques for online monitoring. For instance, in enhanced oil recovery application, which petroleum production often requires separation of gases coming out of the solution from the liquid hydrocarbon. In this scenario, the annular regime might be present, and this regime is formed by the liquid film flowing on the channel wall and the gas flows in the car as depicted on the video. So the measurement of the flow parameters such as liquid film thickness, phase velocity, among others in annular flow can directly contribute to the improvement in the efficiency for the design of such systems, and also give us the development of more accurate engineering correlations and flow models can be developed using such an experimental database. In this study, we focus on the evaluation of a conductance sensor regarding its capability to investigate annular flow. The sensor is installed in a vertical pipe section in which ring electrodes measure the electrical conductance of the flowing media. So the information is then processed and analyzed by the sensor, which computes the phase fraction, the liquid thickness, and flow velocity with embedded models. Secondly, flow computer receives the information and realizes more advanced calculations, such as structure detection and other correlations. The sensor was developed by means of an innovation project involving the company's backers, the Multiphase Flow Research Center, and financially supported by Fundação Araucária. The sensor performs fast conductance readings up to 100 kilosamples per second per channel, which is crucial to investigate such a phenomenon. And those samples are also time sampled and synchronized with accuracy for determining the flow parameters. So the sensor also measures range goes from 1 microsiemens to 1 Siemens, covering a wide variety of applications with multi-probe functionality, which means that you can switch the probe regarding your application and make it non-intrusive or intrusive as desired. The sensor can communicate with local and wireless networks, serial and industrial protocols, and analog outputs such as port 20 mA current output and customized voltage outputs. The sensor was first evaluated with this commercial LCR meter by Keysign, which varying the water solution conductance with sodium chloride from 100 to 600 microsiemens. We could compare the results among both equipment. So the measurements were performed using the full pipe measurement, which means filling the sensor measuring section with the experimental solution. And we can see on the upright plot the general a good agreement with the LCR meter, except for 2 points where there were the fewer conductance measurements. And the second experiment was performed to investigate the temperature drift on the measurements, an important factor to consider with when measuring electrical conductance on fluids. So the results also show an increased height in the electrical conductance by 2% Celsius degree, which is expected based on the literature and commercial instruments reports. Here an experimental setup was constructed for investigating annular flow to accommodating those non-conducting polymeric photons with different diameters concentrically aligned inside the electrode sensor section. So the electronics are connected to the upright sensor, which is formed by non-intrusive ring-shaped electrodes, and therefore there's no avoiding any disturbance on the liquid film, so there's no intrusive. And the interrogation volume is defined as the volume occupied by the fluid between the pair of the receiver and the emitter electrode, and also the gap between the phantom and the internal pipe wall. So in order to characterize the sensor response, 18 phantoms diameter were selected to simulate this annular flow phase distribution for liquid film varying from 100 microns up to 9 millimeters. And also a full pipe measurement is also needed as a reference for calibration and estimate liquid thickness. The measurement data are shown here in the slide, where the x-axis represents the liquid film thickness formed by the phantom, and on the y-axis the dimensionless conductance is depicted. So what we propose here is an exponential fit, and the liquid thickness can be estimated by the inverse fit function. And the figure also highlights the results for measurement from 100 microns to 1 millimeter with a 5% max deviation from the proposed fit. As mentioned before, the temperature is an important factor and must be considered when the accuracy is required. So for temperature compensation, linear formulas are often used as a general approach to estimate the electric conductance at a given temperature. We also made a comparison with the finite element method simulation. So they were performed using the same sensor parameters, such as geometry, electrode distance, excitation, frequency, electronics gains, electronic input voltage, to confirm the sensor sensibility to the region of interest. So the electrical current density between the emitter and receiver electrodes is depicted in the upper left figure, and the comparison has shown a good agreement within a 3% max deviation for liquid film thickness less than 2 millimeters. And the last experiment was deploy the sensor in the two-phase flow loop. The sensor was able to estimate the liquid thickness, the detector structures, and measure the wave's velocity in annular conditions. So in further works, they will investigate such parameters with literature correlations regarding the liquid film thickness and liquid velocity. The conclusions of this work are the successful application of dual conductance sensor for annular flow, reading liquid thickness between 100 microns up to 1 millimeter within 5% deviation from the calibration curve, and also offering the temperature drift compensation necessary in flow application where the liquid water is present. So the good agreement between the experimental and numerical calibration and easy calibration with high resolution makes this instrument a cost-effective system and suitable tool for flow investigation, and could contribute to the oil industry to improve overall process and efficiency, maybe minimize machinery downtime. Recently, Nuane facilities received 8 units to investigate two-phase flow in horizontal and vertical flow conditions, enabling new studies in the flow phenomena, even in horizontal, vertical, and other flow region conditions. So I would like to thank all the people who contribute for this work, and thank you all the people who watch me here so far. Thank you. Bye-bye.
Eduardo, thank you very much for the nice Well, we have some questions here about. We have some questions here about your presentation. There is one from Clayton Mendonça. What's the challenge in measuring the core flow diameter instead of measuring the annular thickness? I don't know if Clayton is referring to the gas core or to the liquid annular flow. I mean, the core annular flow. However, this is the question: what's the challenge in measuring the core flow diameter instead of measuring the annular thickness?
Hi, thank you, Oscar, for the question, and Clayton. And well, I would say that for this application where annular flow with liquid, water, and gas, since we're measuring the liquid thickness is just a matter of subtraction from the internal pipe diameter, then we can have like an estimation of the gas core diameter. Of course, we cannot measure the liquid droplets inside, but we can have a very nice estimation of the gas core.
Very good. We have another question here from Professor Rogério Ramos. Do you make any effort to identify dynamic behavior of readings? I mean, the thickness measurement in transient flow, or you just evaluate at steady state condition?
Okay, thank you for the question. Well, I think my presentation came earlier than the prior presentation from Anna, but and our work was like estimate this liquid thickness by doing some statistical tests, and Anna was introducing her research to investigate in dynamic situations. So I would say that there's a transient flow as well will be investigated by her and me in the near works. And I would say this was a kind of preliminary that we take as well, because we developed the system to read up to 100 kilosamples per second due to the behavior of the flow that you want to analyze. So yeah, I would say that we will get into it in the next steps.
Okay, there's another one here from Stella Cavalli. Could you use the signal from the sensors to estimate the entrainment of gas in the liquid film?
Thank you for your question, Stella. With using this kind of sensor, a conductance sensor, we'll not be able to estimate the droplet, the liquid droplet inside, because we can measure only the liquid in contact with the ring electrodes, the liquid volume in contact with these ring electrodes. But this kind of platform we developed, we can also measure capacitance. It's not the focus here, but using such a methodology, we could kind of estimate, but yeah, I don't have the results to show here, but yeah, not with this technique.
Would anybody in the Google Meet room like to ask some question to Eduardo? Okay, we still have some time. Eduardo, let me make you one question. I could see one very nice result of yours in your presentation. That's the dimensionless conductance as a function of the liquid film thickness. And I could see that in the range of 0.1 to 0.9 millimeters, we had a good linearity there, and a very nice point spreading there, very low actually uncertainty there, very low error. But you are using in your tests actually some phantoms of that have, of course, very well-known and very constant electrical properties. But since you are using a conductance technique, you know that in real applications, the salinity you might have in, dissolved in your fluid, for instance, if you have a production water in the oil industry, might actually affect your technique, strongly affect your technique. I mean, the salt, the salinity you might have. How can you in this stage of your research assess the effect that salinity would have in your instruments' experimental uncertainty?
Okay, thank you for your question, Oscar. Well, some prior tests made us estimate this range of operation from 1 microsiemens to 1 Siemens, which is inside this high conductivity range with high salinity. But yes, we haven't tested this range yet with the sensor and what the salinity can create even in the electrodes. But I would say that it's just a matter of the conductivity range. So if we are capable to measuring such a conductivity, I would say that the response for this curve could be almost the same. But yeah, we would need to get into it to give you a right answer. But I would say yes. I would say it would not be a problem.
Okay. So I think we don't have any more questions. So yeah. So we could go to our last presentation, the last presentation of today's session. This last one. No, it's not the last. It's one before the last. We have now the presentation of Bruno de Moura, exactly Bruno de Moura, from the Federal University of Espírito Santo. He's going to present the work implementation of a phase sensitive detector with Cordic algorithm in microcontrollers for low cost EIT demodulation procedure. Bruno is from the group of professors Márcio Martins and Rogério Ramos from the Federal University of Espírito Santo. So please, let's see the Bruno's presentation.
Hello everyone, I'm Bruno de Moura and I'm presenting the article entitled Implementation of a Phase-Sensitive Detector with Cordic Algorithm in Microcontrollers for Low-Cost AIT Demodulation Procedure. I would like to thank the Multiphase Flow Journey for the opportunity to present the article, and I also would like to thank the other authors who made this work possible. Here we present a brief summary with an introduction of the AIT method, followed by the objective, the digital phase sensitive detector, the Cordic algorithm, results and discussion, and conclusion. The AIT method, or the electrical impedance tomography, is an image technique based on the electrical conductivity estimation. We have here tone measurements which are made on a tube, for example, and we obtain the image, the electrical conductivity of the medium. And this method is widely applied to multiphase flow measurements. We are going to show some of these applications. One of the characteristics of the method, it requires a forward problem and an inverse problem. The inverse problem is obtained by minimizing a voltage surge from a forward problem and a voltage surge from measurements of the system. And how these measurements are made? These measurements are made by injecting a current into the medium and measuring the boundary voltage of the medium. From this measurement, you can obtain a voltage set. And this technique has the following properties. It has absence of ionizing radiation, which turns to a safe application, relatively low cost, non-intrusive sensors, which is important to not disturb the flow, and a high temporal resolution, which can achieve 1,000 images per second. It is widely applied in multiphase flow to flow pattern identification. Here we have a flow, the flow direction here, and we can identify it as a bubble flow. We can measure the void fraction of the flow by knowing where each fraction of the flow is in the cross section. You can obtain this information. You can measure the velocity of the dispersed phase or flow measurement by utilizing two planes of sensors, and correlating a signal, you can obtain the velocity of the flow. Here is another application combining several flow measurements. Here we have so the image from the AIT. We have here oil in water, bubble flow. Here we have gas and oil in water, a slug flow. The low-cost systems are being widely constructed due to the easy access that they provide for the research to the technology. So it's important to provide this access for researchers. Low cost have some characteristics. It is not so accurate as a performance system, and the speed of acquisition is not as fast as this the most developed system. So we have developed in our group a low-cost system, and we found that the limiting speed of the system was the demodulation subsystem, which limited the acquisition of the system to 3 images per second. In the literature for local systems, it has several types of demodulation, such as sample and hold, external integrated circuits for measuring, RMS rectifying demodulation, but none of this uses a phase sensitive detector. So the objective here of our group is to implement a digital phase sensitive detector to a AIT system. It must combine the Kodiak algorithm, since we are going to use a microcontroller, and and the resources are limited for the microcontroller. The objective here is to demodulate the sine wave from AIT measurement, giving the amplitude and phase information with a low burden to the microcontroller. Here is depicted in this figure the method of the phase sensitive detector. We have here analog signal, which is digitized in the analog to digital converter. The signals are then multiplied by a reference signal, a cosine here up, in bottom the reference scene, a reference scene is multiplied to the signal, and these references are obtained by the Rodrigues algorithm. By sum all the contributions of the samples, you can obtain the in-phase and quadrature signal, which are used to calculate the amplitude and the phase of the wave. The Rodrigues algorithm is based on a basic rotation equation. Here we have the rotation equation, and if you divide all by cosine, if you manipulate the equation, you have this equation here. Depending on tangent of the angle. This tangent is calculated by a lookup table. So we have replaced the tangent by a simple shift operation to make this calculation of the algorithm very fast. Therefore, it is substituted for a shift operation here. This cosine is the gain of the algorithm, which is calculated by this equation here. It's approximately a constant of 0.6 the value of the cosine, the gain. The methodology here we use, we have the experiment on an Arduino Duo controller board, the analog to digital converter and digital to analog converter have 1 megasample sampling rate. The sine wave we output on the DIC is 1.5 kilohertz. This sine wave is measured by the oscilloscope DS203, and 100 measurements are used to calculate the signal to noise ratio. We are going to investigate the signal noise ratio of the method. So we have here the scene from the oscilloscope and from the ADC. It's possible to observe that the oscilloscope is not as precise as is not precise enough. So we obtained on the oscilloscope at 0.3 volt, which is close to what we observed in the phase sensitivity detector and at ADC. Here we have the Cordic output, a cosine wave and a sine wave. It is possible to observe the method is good, is well applied. Another important observation is that the phase sensitivity detector ignores the offset. Therefore, the 0.3 is ignoring the offset of the signal. Here we have the results for the signal noise ratio. It was observed the following. For 8 samples and one sine wave cycle, it obtained a poor noise performance. Therefore, it is important to demodulate with 16 samples. The AIT, it's possible to analyze and sample the sine wave. So we test for 2 sine wave cycles, 3 sine wave cycles, and 4 sine wave cycles. It's possible to observe that 8 samples is not enough, since we obtain a greater cycle, greater time. So it is poor resolution here. It has a poor resolution. So for 2 sine waves, it is required 32 samples for presenting a good accuracy. Another aspect that is important to demonstrate is that for 104 measurements, which is the adjacent protocol quantity, it represented 9,000 microseconds, which would possibilitate over 100 images per second, which is a great improvement considering that the system now has 3 images per second. So the conclusion here, we implemented a phase sensitivity detector with Cordic algorithm. The Cordic algorithm output good results. The demodulation results are according, close to 0.3 volts. The signal to noise ratio presented results on the order of 15 dB using 16 samples and one sine wave cycle. Sampling with 8 samples only presented high noise. The modulation procedure should greatly improve the low-cost AIT system temporal resolution. I would like to thank all of these institutions for possibilitating this work. And that's all.
Hey, thank you, Bruno, for your nice presentation. Okay, so we have one question here from Marciele Oliveira. Bruno, which defines a low-cost system? Until where sophistication added to the system push the low cost to a normal one system?
Thank you, Marcelo, for your question. that's something that we still debate, discussion, what is really a low cost or not. We don't have the specific answer, but we know that some of the most developed systems have, for example, one analog to digital converter for each electrode. So that's a more complex system, but exactly the lineage, it's still in discussion. Basically, is that.
Okay, Bruno. We still have time. I have a question for you. We have used, in my group, this kind of demodulation technique of separating the signal in amplitude and in phase in the past to actually find enough equations for measuring the electrical properties of three-phase flows, okay, when we have three phases. So we have, for instance, oil, water, and gas. So we use that kind of technique in order to be able to obtain the third equation that's necessary to close the matrix, okay, to close the linear system to get volumetric fraction, okay? My point is, in your case, you are trying to apply that to a two-phase flow, right? For two phases only. And if I could understand correctly, but you haven't tried that already yet with real mixtures, right? Of fluids, not yet, right? You made a sensitivity analysis of error, right? This is my first question.
This type of demodulation, it is utilized to demodulate the wave that enters the medium and returns. It is how can I put? It is changed by the medium, the resistivity medium, and now we have some amplitude depending on this medium. So the demodulation is based on this procedure. Is from the signal that you inject into the domain. So exactly, we're not specifying which flow we are using. We are the first. We even assembled the system yet. We are still testing the subsamples individually, so we can later assemble a system and use it on a tool, on a multi-phase flow with different fluids. Currently, we assembling with partnership with Nemog for testing the previous system. So this system is yet to be developed.
No, very good. I think it's a nice approach. When you have data, I'd like to see them, if I may, because one of the issues of this kind of application is that sometimes we have problems in assuring the mass balance. The continuity sometimes is not preserved with this kind of approach. At least it's the experience we had. Okay, in our lab, we did something like that like 6 years ago, using exactly this kind of modulator. We have another question here. It's from Eduardo Santos. Since you are planning to use a microcontroller, 100 images per second will be only possible with non-interactive image reconstruction algorithm as LPB. and so on. Could you please comment on that?
I don't exactly know this type of how do you say, what is the question? Can you repeat, please?
Yes, since you are planning to use a controller, 100 images per second will be only possible with non-interactive image reconstruction algorithm. With a non-interactive image reconstruction algorithm, for you to reach 100 images per second, you need that algorithm, the LPB algorithm. Okay, he wants you to comment on these critics. Yeah.
The objective here is not to obtain 100 images per second. It is to extract the full potential of the microcontroller. So 100 images per second was a rough estimative of what we could obtain. So what we are doing, it's a low-cost system. So we are not using DSP or other types of. We are planning to be on the microcontroller and exactly explore this potential to help to gain access. We're planning later to make some others more. How can I say? We're planning to build other systems without the microcontroller, but for now, what we have is this.
Okay, Bruno. So thank you very much again for your presentation and for your answers. Okay, we have to move on. So thank you very much. Now we are going to, we are going to our last presentation. Now it is really the last one. Okay, it's going to be presented by Marco Cerucci from Emilio Palladino's group at the Federal University of Santa Catarina. Okay, he's going to present the work, a deep learning based image processing technique for measurement of two-phase bubbly flows using particle image velocimetry, PIV. Okay, let's go.
Hi, I'm Marco. I'm a mechanical engineering undergrad student at the Federal University of Santa Catarina. And today I'll be presenting a deep learning based image processing technique for the measurement of two-phase bubbly flows using particle image velocimetry, written by Rafael Cerqueira, me and Emilio Palladino at the Computational Fluid Dynamics Lab, CIMEC. Firstly, we'll be talking about our motivations, why we are studying bubbly flows using PIV technique, and some of the challenges of using this technique, and what we aim to achieve in this work. Next, I'll be showing the experimental setup used to acquire PIV images and the deep learning model used to discriminate flow phases. Then I'll be showing the flow conditions studied in this work, the masks generated by the deep learning model, and the average liquid profiles calculated using this model. And finally, I'll be talking about the conclusions we were able to make from the results we got and an outlook for future papers. Gas-liquid bubbly flows are important in several processes in industry and nature, and gathering information about the liquid phase velocity field is of fundamental importance to characterize the flow structure. PIV is a powerful technique as it's non-intrusive and provides spatial distributions of velocity fields. However, applying it to gas-liquid flows is challenging due to laser light scattering by the gas-liquid interfaces, and image treatment is necessary to get consistent average fields. In sum, PIV is used to study flows in detail because it doesn't interfere in the flow structure, but due to light scattering in bubbly flows, the gas bubbles will appear as these different structures, and they can cause spurious contributions to the liquid velocity fields. Previous works in this field used classical digital image processing techniques based on Gaussian filters, but those algorithms are dependent on user-defined parameters and need to be optimized for each flow condition and geometry. We propose a deep learning approach that makes use of a convolutional neural network that is more accurate than classical methods and are able to generalize well for different flow conditions, such as dense bubbly flows with high void fractions. Our goal then is to create a dynamic masking, remove the gas phase from PIV images, removing their spurious contributions and providing consistent liquid velocity averages. Here we have a schematic of the flow loop used to capture the PIV images used in this work, and a picture of the actual assembly on the right side. With the PIV images in hand, we now need to apply an image treatment algorithm. Before talking about specific deep learning algorithm chosen in this work, we must discuss some of the classical computer vision problems. Image classification is the most basic of these and consists of a model that can output. Image or semantic segmentation goes one step further and is able to discern the areas of an image where a certain object class is located. We chose a UNet deep learning model. UNet is a CNN for semantic segmentation, and it provides us with a pixel by pixel mask of an image that in this case discriminates the bubble and gas phases. The advantages of using UNet are that it's fast and precise, and I'll show you further that it has encoder and decoder layers that are interconnected, which means that the information lost during encoding can be retrieved in the decoding layers. The result of this process is a binary mask. Here is an example of how we created the dataset for training the UNet model. We take a raw PIV image here on the left and manually draw ellipses surrounding the bubbles. Then we use an algorithm to make this mask here on the right. And now we see here how the previous images are used in the model as input and output. The raw PIV images are used as input and the masks as output. During the decoding here on the right, the encoder and decoder layer become connected or concatenated, and this helps us recover lost information. After the model is trained, we are able to pass it a raw PIV image frame, and it should return us a mask like the ones used in training. Before we go to the results and visualize the masks we were able to produce, we must discuss some of the hyperparameters we had to fine-tune to get better results. To have a good model, we had to fine-tune these three parameters and find a good trade-off between accuracy and training and inference time. We found an image size that would generalize well for different flow structures, and a number of filters that could extract enough features from the images without putting too much strain on our computers. And we found a kernel size that could get enough context, which means the model has more information of its surroundings and in turn is better at identifying interfaces within objects. These are the flow conditions that were used in experiments in this work, detailing the liquid and gas superficial velocities. And here are the final masks generated by the UNet model. We input the raw PIV frame on the left, and it returns us the binary mask here second from the left, which is then inverted and subtracted from the original image to get a masked PIV image. Here is a liquid velocity field with and without masking, and when we zoom in, we see that the vectors on top of the bubbles were removed. We can see here that the effects of the masking process in the average liquid velocity profiles are very evident, especially in cases such as here in the left, where the liquid superficial velocities are smaller and in turn the slip factor between the liquid and gas phases is bigger. The light blue line represents the results of not using any image processing, and the dark blue line is a result from a previous work whereas the red dots are the results obtained in this work. The obtained average velocity profiles were appropriately validated. So, in conclusion, the velocity profiles calculated using the UNet masking are consistent with previously validated results, and UNet has proven itself as a valid tool in phase discrimination for PIV images. Now look then for future works would be to couple the UNet model with a traditional CNN model to discriminate bubbles that are in the laser plane and off the laser plane. With information from the bubbles in the laser plane, it's possible to obtain their velocity and local gas volume fraction. Therefore, we can fully characterize bubbly flows obtaining liquid and gas velocities solely from PIV acquisitions. Here are some preliminary results we were able to obtain, where we managed to use data from the manually drawn ellipses to discriminate some of the bubbles in the laser plane here in green. And finally, I'd like to thank everyone for watching the presentation, especially the National Petroleum Agency for supporting this research, and Rafael and Professor Emilio for allowing me to present our research. Thank you all very much.
Thank you, Marco Cerucci. This very nice presentation indeed. I believe that the use of artificial intelligence is really a trend. And as far as I could understand from your work, you are actually proposing this deep learning based image processing technique in order to make it automatic. I mean, the correction of this information obtained via PIV, which is actually an issue, and sometimes we do it, but manually, and we assume actually that the errors are in the uncertainty, and we have to live with that. But you don't want to live with that, so you decided to use this artificial neural network in order to obtain more precise and in order to obtain a correction that could be made by the machine itself. And I could see your results in your velocity profiles, and they are actually astonishing. I got impressed with the improvement you had. So I'd like to ask you whether you think that these techniques could be also used to obtain, for instance, better void fraction profiles or other informations out of the two-phase flow that could be actually improved, significantly improved, using this kind of artificial intelligence technique.
Well, thank you for your comments regarding the presentation. Yeah, well, the objective of the group is to try and get a full characterization of bubbly flow using these deep learning techniques, and we have got some very good results already. And in the future, yes, we plan on calculating void fractions, I believe. I'm not very well versed in the multiphasic flow structure yet. I'm just an undergrad student, but I think the ultimate goal of the group is to present that as a result.
Okay, Mark, we have another question here for you. It's from Lívia de Oliveira Zamperetti. Did you use a filter over the images before you use them to train the neural network?
I believe so, that before we provide the computer the PIV images, they have some pre-processing, some blurring techniques, something like that. But we are trying to use as little as possible of this and try to get the most of the filtering done by the artificial intelligence.
Okay. Another one here from Clayton Mendonça. How the PIV works on more in-depth frames? I mean, more in-depth frames. Is it a real 3D image acquisition?
I think he meant more in depth, as in the deeper parts of the flow pipes. We have some trouble in that. I have discussed in the presentation that the bubbles that are in the laser plane are very hard to discriminate from the fluid phase because of how they look like in the laser. And we are developing already a method to better classify these in-plane and off-plane bubbles so that we can get better results even.
Marco, also in line with Livia Zamperetti's question that asked about the filters, I can understand that in your setup there at the Federal University of Santa Catarina, you had your lighting system, you have your camera, high-speed camera, and everything set up for your experiment only. So you got data that actually was used to train your algorithm, your prediction algorithm. But my point is, did you care about proposing a methodology that could be actually extended to different setups, to different situations? Because we know you can interpolate your data, but it's only for your case and for your case only. So what would you say for another guy that's in another university, another lab that would like to use the same technique?
We have, in the same research group, we have some other flow structures such as Venturi tubes also that weren't covered in this article specifically, but we are also looking forward to using these techniques to other flow structures that and Rafael also has worked on slug flow a lot using some techniques, but not this UNet proposed that we have in this article.
Okay, I'd like to ask if anybody here in the Google Meet room want to make any other question to Marco?
Yes, Professor. Can I do a question?
Okay, Luis Otávio, please.
Thank you for your presentation, Marcos. Very good your presentation and job that you have to do. One thing that I would like to talk to you about, the oil gas industry has one challenge that to measure the oil in water. We have to measure because the environment requirements. So we use techniques, optical techniques for measure this oil in water. Do you consider to apply this technology for measure oil in water, or do you have another application that you're looking for?
I don't know the specifics, but we do have some work with ANP, but I don't think we will specifically apply it to oil flow or oil water or something like that. The only thing I know that we have already tested is some glycerin mixtures, but I'm not really sure about how it would compare to oil or something like that.
Okay, consider it, consider the measurement of TOG, oil and water fraction, it's a good application for this technique, and another challenge is measure it's in black fluids like petroleum. It will be nice too, to think if it's possible to measure water in oil. I think the challenge is it's the worst challenge for this technique, but it's important too.
Well, yes, if there is a lot of is it visual discrimination between the phases, this neural networks, these convolutional neural networks, they work very well because they are very good at distinguishing these color patterns. You can say something like that.
Yeah, for oil and water, I believe that it's fits very well because nowadays we use optical techniques that this optical window turn dirt, okay? Turn dirt. It's a challenge. Sometimes we lose. We get some error in measurement or uncertainty because the dirt. If you have one technique like that, maybe the technology will work well. So it's interesting to show this technique for the guys that's working in this. Is not my main job, but I can drive or work for people that's inside of Petrobras. I think it's a good opportunity.
Yes, certainly, it would be nice.
Okay, we have some answers here, actually in the chat, in the YouTube chat, for mine and for Luis Octavio's questions, actually. So, Ladinos, this research advisor is saying that the technique should be applicable to any PIV bubble flow image. And also Rafael Cerqueira, who is co-author of this work, is saying that it's possible to use the technique of transfer learning in order to go to different flows, to phase flows. Okay. Oh, that's it. Okay, the session is over. It's already time because there are other sessions starting in a while. So I'd like to thank all the presenters, all the audience. We have a very good audience, 53 people watching now our session, which in my opinion is excellent. So congratulations to the organizers, to Professor Marcio Martins, Professor Rogério Ramos for this success. Okay, and I'd like to thank all the presenters for being here. We had no show. No show. I mean, everybody was here to answer the questions. That's excellent. And thank you very much to everybody. And I thank the organizers also for inviting me to lead this session. It was a pleasure. And thank you and congratulations for the excellent event.
Vamos dar início aqui agora, né? Eu sou Bruno, professor Bruno Furtado de Moura. A gente pode dar início aqui já, Márcio?
Já, Bruno, pode ir.
Vamos dar início então aqui à sessão. Quero agradecer a todos pela presença, né? Nós vamos iniciar então a sessão. We're going to initiate this section in industrial equipment and applications, né? Our first presentation is Thierry Magalhães, from the São Paulo University.
Good morning, my name is Thierry. I am going to present my work to you. My work is about thermal effects in multiphase flow analysis for offshore oil systems. The authors are Magalhães, Azevedo, Andreoli, and Balino. Magalhães, Azevedo, and Balino are from University of São Paulo, while Andreoli are from Unisanta and Petrobras. The presentation was organized as follows: Introduction, Objectives, Model, Results and Discussion, and Conclusions. The relevance of oil to society is vast and essential. In this context, studies about the flow of oil, especially in the production and exploration systems of the wells, are vital. Multiphase flows involve several complex and coupled phenomena such as slip between phase, heat transfer, turbulence, thermodynamic process of equilibrium, etc. Then, empirical analytical correlations based on experimental results and field data are used to determine properties of fluids. Thermal analysis is important in assuring minimum temperatures in order to prevent hydrates and paraffin formations in the pipelines and houses. The incorporation of the energy equation and thermal effects make the flow analysis more realistic. This slide shows a typical offshore oil production system. The main components of the system are wet Christmas tree, pipeline, riser, and platforms. These are the main objectives of the work. Numerical implementation of a model in order to calculate the stationary condition in offshore oil production systems, and determination of more accurate profiles for state variables along the flow. Assumptions for the developed mathematical model are: The flow is one-dimensional and three-phase. Compressibility is taken into account for gas in liquid phase. Oil and water have the same speed and are homogenized as liquid phase. The flow pattern in the pipeline in riser depends on local state variables and inclination angle. Moving on, the characterization of fluids and mass transfer between the phase is done according to the black oil formulation. The void fraction depends on flow pattern. For boundary conditions, constant pressure at separator at the platform and constant temperature at wet Christmas tree, acronyms WCT, were adopted. This slide presents the general geometry of the production system. This geometry consists of a flow line connecting the wet Christmas tree with platform through a variable path S. Moving on, the multiphase flow model adopted is based on the Milkshire model and considers four conservation equations: mass balance for the gas and liquid phase, linear momentum, and energy balance for the gas liquid mixture. The black oil approach considers that the liquid phase has solubilized gas that vaporized along the flow. The mass transfer terms is positive in equation 1 and negative in equation 2. Follows: pressure gradient is in general the sum of friction, gravitational, and inertial contributions. However, flows are low in offshore systems, so pressure waves have no dominant effect compared to continuous waves. Thus, we can neglect the inertial contribution in pressure gradient, resulting in equation 3. Equation 4 shows the density of mixture in function of the density of phase, while equation 5 presents the algebraic relation between the volumetric fractions. The energy conservation equation implemented neglects axial heat flux, dissipative source, normal stress powers, and kinetic energy terms. Heat transfer to the walls is taken into account. Heat transfer is modeled through an overall thermal conductance made of internal convective heat transfer through the fluid, conduction at the different wall layers, and external natural convection heat transfer through the seawater. Thermal capacitance is neglected. An offshore pipeline catenary riser was analyzed with input parameters shown in Table 1. These parameters comprise operational conditions, geometric data, thermophysical properties of internal and external fluids, as well as discretization of the model. Given these considerations, these were the main results obtained through the numerical implementation of the model using finite difference with the software MATLAB. This slide shows the temperature profile obtained with the parameters from Table 1. The blue curve represents the results for the model with thermal effects, while the orange line represents the constant temperature in the wet Christmas tree used in the isothermal model. Inlet temperature was 51 degrees Celsius and the temperature drop in the system was about 28 degrees Celsius. Figure 4 presents the pressure profile along the flow, obtained with input parameters shown in Table 1. The blue curve represents the results for the model with thermal effects, while the orange curve represents the results for the isothermal model. Pressures at the wet Christmas tree, calculated by the model that includes the thermal effects, slightly higher. The thermal effects were slightly higher than those obtained by the isothermal model. The difference between them was between 2 and 3%. This is main conclusions of the work. In this paper, the flow in the stationary state was studied for a pipeline riser system, including thermal effects. Temperature has a secondary effect on the stationary state in offshore systems. Deviations about the isothermal model must be taken into account in order to improve reliability of numerical results. The results obtained in this study show in the potential of this technique as a useful tool for analyzing real flows in oil production systems. These were the main references used for the research. The authors wish to thank you, especially to Petrobras, main sponsor of this research,
Bruno, teu microfone está mudo.
Thank you, Thierry Magalhães, for the exceptional presentation. We are now going to open for questions. Any questions in the YouTube platform for Thierry? Well, since none, I have one question. Thierry, did you check in this model for the velocity sensitive to the thermal solution? If higher velocities, oil velocities would present a higher discrepancy between these two models?
Bom dia, Bruno. Bom dia, pessoal. Eu vou responder em português porque eu me sinto mais confortável dessa forma. Em relação à velocidade das fases, o que acontece? Esse modelo da equação de movimento, da equação de balanço de momento linear que a gente utilizou, ele já está assim, separado, desacoplado do par pressão e velocidade, né? Que normalmente a gente observa na equação de Navier-Stokes. Mas, enfim, a temperatura ela influencia nos demais parâmetros, consequentemente ela vai influenciar na velocidade, apesar de que nessa abordagem a gente considera que na fase, tipo, o escoamento trifásico, né, escoamento de óleo, gás e água, só que na fase líquida, né, a gente considera que o óleo e a água têm a mesma velocidade, e, assim, tem assim, as diferenças em relação aos resultados numéricos. Do modelo isotérmico para o modelo com os efeitos térmicos, acaba que ficaram na ordem de entre 2% a 5%, dependendo do parâmetro. O parâmetro que apresentou maior sensibilidade foi a fração de vazio, a diferença chegou a ser de 4%. Caso a pressão vai entre 2% e 3%, a velocidade acho que ficou entre 1% e 2% também. Só que a velocidade até que os escoamentos são lentos, né? As velocidades são pequenas nesses sistemas. Mas no caso das versões ou de outras variáveis, a acessibilidade acaba sendo maior porque a ordem de grandeza é maior.
Okay, we have some more questions here. Márcio Martins says that temperature has a secondary effect on the flow in offshore systems. Means we can ignore the temperature effects?
Não, então, eu falei que a temperatura tem um efeito secundário nesse escoamento, porque apesar da temperatura influenciar em todos os parâmetros e influenciar diretamente no escoamento, ela não é o efeito dominante. Por exemplo, se tem um sistema, eu exemplifiquei ali a lama d'água, escoamento da árvore de Natal até o separador na plataforma. Se tem um riser de 1.000 a 2.200, acho que de 2 km, ou seja, a altura do sistema seria de 2 km. Assim, o principal efeito dominante nesse escoamento, seja no diagrama de pressão, é a gravidade, embora a temperatura influencie em todos os outros efeitos, transferência de massa, né, porque devido à vaporização, expansão das fases, compressibilidade, enfim. Como você tem um escoamento plenamente turbulento, se a gente observar o diagrama de Moody, por exemplo, você triplicar ou quadruplicar a viscosidade, né, que é um parâmetro de transporte importante, ela vai alterar pouco o número de Reynolds. Então, assim, a temperatura ela é importante, muito importante, porque, por exemplo, a pressão ela foi discretizada do separador para a plataforma. A gente adotou condição de pressão constante no separador, né, e com isso a gente discretizou a equação de movimento e calculou a pressão de entrada, né, na NM. E a diferença entre a pressão de entrada na NM no modelo com os efeitos térmicos em relação ao modelo isotérmico foi de quase 3%. E essa pressão, por exemplo, no modelo isotérmico foi de 110 bar e no modelo com os efeitos térmicos 112. Então você tem uma diferença de 2 bar. E uma diferença de 2 bar ela não pode ser negligenciada, né? Isso é equivalente a 21 metros de coluna d'água. Então, assim, a temperatura ela é importante, ela tem que ser avaliada, só que ela não é o efeito dominante. Era essa a ideia que eu quis passar.
Okay, Jay, thank you for your words. Now we're going for a small break for lunch. We are going to return, so 1 and 10 p.m. Okay, we're leaving here the chat open, so we continue later.
Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve, o mundo merece sua ideia, a sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve, o mundo merece sua ideia, a sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CPIDES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CPIDES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CPIDES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TioSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TioSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TioSolve e transforme a sua ideia em solução aplicada na indústria. TioSolve, o mundo merece sua ideia, a sua ideia merece a TioSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TioSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TioSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TioSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TioSolve e transforme a sua ideia em solução aplicada na indústria. TioSolve, o mundo merece sua ideia, a sua ideia merece a TioSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TioSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TioSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TioSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TioSolve e transforme a sua ideia em solução aplicada na indústria. TioSolve, o mundo merece sua ideia, a sua ideia merece a TioSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TioSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TioSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TioSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TioSolve e transforme a sua ideia em solução aplicada na indústria. TioSolve, o mundo merece sua ideia, a sua ideia merece a TioSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TioSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwareização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TioSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TioSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TioSolve e transforme a sua ideia em solução aplicada na indústria. TioSolve, o mundo merece sua ideia, a sua ideia merece a TioSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TioSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TioSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TioSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TioSolve e transforme a sua ideia em solução aplicada na indústria. TioSolve, o mundo merece sua ideia, a sua ideia merece a TioSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TioSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da UFPA, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente. Nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TwoSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TwoSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TwoSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TwoSolve e transforme a sua ideia em solução aplicada na indústria. TwoSolve. O mundo merece sua ideia. A sua ideia merece a TwoSolve.
back for our online transmission, the multiphase flow journey, the 2021. It's important to remind you that it is highly recommended and that you leave your question for discussion later. And now we're going to continue the presentations with Guilherme Mustard from Technological Federal University of Paraná, with the work entitled Influence of Shear History on the Apparent Viscosity of Drilling Fluids, Hydrate Slurries.
My name is Guilherme Milset, and I'm going to present the work Influence of Shear History on the Apparent Viscosity of Drilling Fluids, Hydrate Slurries. The authors of this work, it's me, Jonathan Galdino, Diogo Andrade, and Cesar Negrão. The increase in oil consumption and depletion of conventional oil reserves lead to exploration in deeper areas, as you can see in this illustration. With the increasing depth, the water becomes colder. The deep environments favor the hydrate formation, that's its high pressure provided by the film column and low temperatures by the cold water in the environment. Those formations can occur partially or totally the flow. On well drilling process, engineers adding inhibitors on the water-based drilling fluid to avoid the hydrate formation. The amount of inhibitors in the mud is measured according to the expected conditions of those processes. Do an unexpected event like a kick, light hydrocarbons enters in the mud system. The hydrate could form in the well bore and obstruct flow or a drilling equipment. Near the wellhead, the formation can occur on the BOP, keel and shock lines, pipes and risers, causing not only safety issues but also environmental and economical losses. But what is hydrate? Hydrate is an ice-like crystalline structure composed of water molecules and a gas fluid, normally light hydrocarbons. The gas fluid is occluded in a hydrogen-bonded water cage to form a unitary cell that agglomerates with each other to form an hydrate structure. There are 5 different cages that could form 3 different unitary structures, S1, S2 and SH, but only the structure 1 and structure 2 occurs in the oil industry. To avoid the high pressure needed to form gas hydrate, the present work uses tetrahydrofuran as a gas fluid. The advantages of using THF is that the fluid remains at the liquid form at ambient conditions, is totally miscible on water, and forms hydrate at ambient pressures with temperature above the water freezing point. The THF forms the structure 2. The structure 2 unitary cell consists in 16 small cages and 8 large cages. Because of the THF molecular size, it is occluded only in the bigger cages. Since S2 units contain 136 water molecules, and there are only 8 large cages, the THF molecular fraction is 1 to 17 of water. The objective of this work is analyzing the influence of a constant shear rate on the hydrate formation in drilling fluids and the influence of shear history on the apparent viscosity of the drilling fluid hydrate slurries. The materials used in this work was a high-purity tetrahydrofuran as a gas fluid and a water-based drilling fluid provided by Petrobras. To maintain the material as a slurry, the maximum volume fraction of hydrate glycerin structures presented during the tests was stipulated as 40%. Since the sample volume are determined by the rheometer's geometry and the density of the components are known, it is possible to calculate the mass fraction of each phase. As mentioned before, THF hydrates presents the S2 structure, as each unit cell of this structure contains 136 molecules of water and 8 of THF. The molecular fraction is 1 to 17. As the water content in the drilling fluid was known, and considering all of the gas fluid will be included, the mass fraction of THF in the sample are 6.94. The equipment used on the experiments was the HACMARS 3 rotational rheometer, using a co-wet geometry with a serrated wall cup. The first experiment represents the hydrate formation during a constant shear rate. The sample was prepared and a press shear was imposed to ensure completely homogenization of the compounds. After that, the sample was cooled at a constant rate of 1.5 degrees Celsius per minute. The cooling was made dynamically, imposing a shear rate. The same shear rate was maintained till the end of each experiment. After each shear imposed test, the temperature was elevated in order to dissociate the hydrate and clean the geometry for a new sample. This experiment procedure was made with those shear rates. The shear influence of the hydrate formation is now discussed. A constant shear rate was imposed to the sample from 3 to 300 per second. As shown in figure A, the shear stress increased during the cooling for all the applied shear rates, meaning a growth of the material's apparent viscosity. After reaching 10 below zero, the stress tends to stabilize, undergoing a sudden change after a certain time. That is attributed to the hydrate formation. Observing those curves, we can note that the higher the shear rate, the higher the shear stress, the shorter is the induction time, and the faster the material reaches the steady state. The figure B shows the apparent viscosity as a function of the applied shear rate. At the test startup, 5 degrees Celsius, at the end of the cooling period, 10 below zero before hydrate formation, and after the hydrate formation at the end of the shearing period. Whereas the temperature reduction from 5 to 10 below zero increased the apparent viscosity of the hydrate-free drilling fluid by approximately 1.5 times. The hydrate formation enlarged the apparent viscosity by approximately 1 order of magnitude at the same temperature. As noted, not only the hydrate-free drilling fluid but also the hydrate suspensions are shear-thinning materials, as the apparent viscosity decreases with the shear rate. The next experiment was proposed to analyze the influence of the shear history on the material's apparent viscosity. The initial steps are quite similar. change only the rate of the shear using the cooling procedure, in this case 3 per second. After cooling, the shear rate was maintained at the 3 during 6 minutes. From this point on, the shear rate was stepped up to 10 per second and maintained for another 6 minutes. Then stepped up to 30. The stepped up procedure was repeated every 6 minutes up to the limit of 100 per second. A shear step down course was then initiated, reducing to the previous shear rate to 70, to return the shear rate of 3 per second. Given the apparent viscosity results from the step up and step down procedure, we can note that during the step up sequence, 6 minutes of shearing are not enough to achieve the material's steady state. Comparing with the results obtained in the figure 1a, which shear rates above 10 per second reach the steady state quite fast, the magnitude of shear applied during the hydrate formation affects the material structure. In contrast with the step-up period, stress undershoot, less noticeable than the overshoot, are observed after the shear rate sudden reduction, with the stress tending slowly to the equilibrium. As the stress measured during the step-down period never reached the same stress level obtained during the step-up period, for the same shear rate, the material structure cannot be completely recovered during the step down. In other words, the maximum shear rate applied to the material breaks down the hydrate particles into smaller size aggregates, and consequently the apparent viscosity is irreversibly reduced. The viscosity measured at the end of each shear rate steps period were plotted as a function of shear rate. The up blue triangles represents the step-up sequence and the down blue triangles represents the step-down. Comparing the above curves, it is possible to note the irreversible degradation of shear on the material's microstructure. The viscosity values of hydrate slurs showed in the figure 1b are plotted in orange diamonds. For low shear rates, these values are quite close to the ones obtained in the step-up shear rate test. While for the high shear rates, 30 and 100 per second, the step-up values are lower than the ones measured after the 1 hour of shearing at the constant shear rate, meaning the time of the shearing also affects the material structure. It's worth mentioning that the material was sheared for many hours in the step-up test, in comparison to only 1 hour period of the constant shear rate experiment. Similar results for the lower shear rates would be expected if the shearing time were increased. The influence of type of shearing is an important issue that should be investigated in future works. As a matter of comparison, the flow curve of the hydrate-free drilling fluid at the same temperature, red circles, was plotted. The rheological behavior of hydrate slurs in water-based drilling fluid formed with THF as a gas fluid was investigated. The main conclusion can be summarized as follows. The higher the imposed shear rate during the cooling period, the shorter is the induction time and the faster the material reaches the steady state. The apparent viscosity of hydrate slurry is at least 1 order of magnitude larger than the drilling fluid's apparent viscosity. The hydrate suspensions are shear thinning materials as the apparent viscosity decreases with the shear rate. The maximum shear rate applied to the material breaks down the hydrate particles into smaller size aggregates, and consequently the apparent viscosity is irreversibly reduced. In a practical sense, hydrate slurries sheared previously at high shear rates require lower pumping pressures than ones mildly priorly shared. Once mildly priorly shared. Once mildly priorly shared. Once mildly priorly shared.
We thank you, Guilherme and Mr. for the presentation. We appreciate the effort you applied in your presentation, and we hope that you recover well from COVID. Now we are going to begin the questions. We have one question from Flavio Bittencourt. Could you please give us more information about the methodology to establish a stable slurry? Is there a standard norm?
If they mentioned a stable hydrate slurry, we base it on the thermodynamical conditions that with 10 below zero, they could form hydrate, and the hydrate will form and remains at the drilling fluid as a slurry. But the conditions of the slurry change with the shear rate applied to the material. How you made your slurry? We made our slurry. We mixed the drilling fluid with THF, and the slurry was made by forming hydrate crystals, and the hydrate crystals made the slurry. The crystals are formed by the temperature driving force that the hydrate forms like at 7 below zero, and we applied a delta T of 3 degrees Celsius. Then this driving force initiated the crystal formation, and then forms the suspension or the slurry. The slurry was composed by drilling fluid and hydrate crystals. The crystal size could change by some experimental conditions, like the shear imposed during the formation, the temperature, or the shear applied before formation. So we applied with formation with a low shear rate and applied a higher shear rate before that. The materials rheological characteristics will change.
We have time for one more quick question. So, following this question, I ask if this hydrate slurry, the conditions, properties such as electrical conductivity and thermal conductivity changes?
Sorry. the audio was cut. I can't hear. Can hear you.
The question is if in these slurries, hydrate slurries, the thermal and electrical conductivity changes when precipitates.
Yes, the hydrate formation was a exothermal crystallization. They release energy, heat, and the thermal conductivity and electrical conductivity was changed, but we don't focus on that purpose of these measurements, only of the rheological measurements. With the flow, in this work of the flow curves, the apparent viscosity, but we are studying the material structural strength and yield stress, the material brightness, and we start the study with the gas hydrate, simulate the field conditions like high pressure and low temperatures.
Okay, Guilherme. Thank you for your work. Very illustrative. Now we are going to present the next presentation. We begin with Enzo Justina from the Federal University of Rio de Janeiro, presenting the work Flow Simulation in Choke Valves for Offshore Oil Industry.
Everyone, my name is Enzo, a student at the Universidade Federal do Rio de Janeiro, and I will be presenting about flow simulation in shock valves for offshore oil industry. And in this work, the objective is to evaluate the flow through a drilling choke using computational fluid dynamics, CFD. Flow control valves are essential to oil industry through exploration and production phases. These valves operate in offshore wells under extremely high pressure and velocity regime, in addition to contact with abrasive fluids, which leads the equipment to suffer great abrasive wear. Initially, pressure drop on shock valves were analyzed in analytical models using empirical data correlation, and with time, the numerical and analytical models has evolved to predict the effect of multiphase flow, gas and liquid mixture, through the valves. And the use of CFD can contribute for the operational purpose of controlling the well and for measuring the equipment integrity. Valves have numerous damage mechanisms, such as fatigue, caused by cyclic load from the flow induces vibrations, corrosion, flashing, erosion, and cavitation also contribute to the decrease of the expected life service. And the high working pressures amplifies the loss of equipment integrity. And between this damage, the main concern is cavitation, which its prediction is one of the main objectives of this work. In the presence of flow circulation at great pressure drops can reach vapor pressure, causing steam bubble nucleation and thus the cavitation phenomenon. And its prediction will wait for better equipment project and design. The choke valve is essentially constituted by two main parts, a fixed body and a mobile valve that can have its linear position modified to regulate the restriction to flow. This allows the choke to control the pressures of the well, avoiding well collapse and the influx of undesirable fluid from the well. As it can be seen in the image, the outlined walls is the fixed body, and at the constricted flow region is the moving part, which varies depending on the openness stage. So, the geometry was initially created in CAD with the SolidWorks software and imported to OpenFOAM version 7, where the simulations were carried out. In this work, 5 opening levels of the choke valve were conducted in the numeric simulation, each representing a different operation stage of the valve. For the simulation validation, the numerical results were compared to the valve experimental test data, The test is constituted by the water flow at a fixed rate of 200 gallons per minute, defined at the inlet boundary condition. Then the valve is initially set to the completely open setup and is gradually closed. And the opening percentage is recorded when the upstream pressure sensor indicates a pressures of 1000, 1500, 2000, 2500 and 3000 psi as per Petrobras standard. With this test, it is possible to experimentally check the choke performance in a well-controlled situation. This is the example of the geometry and the main dimensions used in the simulations. The inlet having a diameter of 50 mm and the outlet diameter being 78 mm. And this is the area of interest, the choking region, where the flow suffers a great restriction. In this region, the velocity highly increases and the pressure drops abruptly. Here is an example of the strangulation dimensions for the 25% of openness to see why the flow in chokes are critical. The smallest section of the choking area is 2.5 mm. And here is where it can find the highest velocity and greatest pressure drops. In this section we show the results by opening stages, both velocity and pressure profiles. The velocity profiles were taking the entrance of the choking region. As it can be seen in the right, the velocity profile changes at the same flow rate of 200 gallons per minute, increasing while the openness percentage decreases. At the 25% of openness, the velocity reaches a velocity of 14 meters per second, and at 35, it reaches at 9 meters per second. And here is the depiction of the pressure distributions of the valve in the strangulation region for the operation stage from 35% to 26%. It can be seen that the lower the open stage, more critical the flow turns. For instance, at 35% of openness we have a 1064 psi of numerical value, and at 26% of openness we have a 2409 psi of pressure. Note that, due to the incompressible hypothesis, the pressure in the scale is relative to the atmospheric pressure and is divided by the water density. And here is the pressure distribution of the valve in the strangulation region for the 25% openness, the most critical stage. It can be seen in the darker blue area the presence of a very low pressure value, below the water vapor pressure, which can be stated that the cavitation would probably develop in this region. According to the results, a good fit with the experimental model could be found, with a mean deviation of 5.12%. And for individual open stage we found an error of 6.4, 6.5, 0.9, 3.7 and 8.1%. Respected to the 35% of openness, 30.5%, 28%, 26 and 25% of openness. Thank you all for watching.
Okay, thanks for your presentation, Enzo. It is very good presentation, very good work. See if we have some questions here in YouTube. I have a question myself. I was wondering if you check the mesh quality and convergence of the results. We know that if you don't have a really convergent mesh, you could have some slight different results. And how many nodes do you use it in your mesh?
Hello, can you hear me?
Yes.
Yes, the mesh was the main problem of this simulation, because of the 2.5 millimeters is very critical for meshing. So the overall quality of the error, relative error, was like 10 elevated to -3 of error of error, and the overall mesh quality was for 3.2 of ratio, aspect ratio. And for, I heard, do you consider isotropic flow in the model Rogério Ramos? First, I will answer for the first question. What is fluid flow in the simulation? Was water, because of the tests of the Petrobras standard, was first, it was at before the real states of the offshore industry passing oil, the valves it passes into a test with a water test to know the integrity, and if the valves passes the minimal requirements for operation the well. First is water test after it is installed and put in the offshore regimen. And isentropic flow in your model, yes, I considered it. It was like homogeneous and single phase with a simple algorithm.
Okay. So do we have more questions from the audience? Okay, then. If no more questions is asked, we are going to
Bruno tá sem áudio.
So, any more questions from the YouTube audience? If there is no more question, we are going to end the section industrial equipment and applications. I'd like to thank you everyone for the support, for seeing this section. It was really productive, many questions. I would like to thank the presenters and the organized committee. Thank you all. And now
Hello, everyone. My name is Luis Machado. I am from the Federal University of Pará. It is my pleasure to be your chairman for this session. The area of this session is wet and dry particulate system. For this session, we are gonna have 4 works. Each work will have 15 minutes for the presentation. After this presentation, we are gonna have more 5 minutes for questions and to have a little discussion. So if you would like to send some question to the speakers, there is one way. You need to use the chat on YouTube. So let's go to the first work. The title is Eulerian Analysis During a Barchan-Barchan Interaction. The author is William Assis from the State University of Campinas.
So, hi everyone, my name is William Henrique Assis. I am a PhD student from the University of Campinas, and I would like to share some results about Barchan-Barchan interaction. So the title of this presentation and current study is Eulerian Analysis During a Barchan-Barchan Interaction. Also, I would like to thank my advisor Eric Franklin and all the teammates I have worked with in our lab. So starting with the motivation, we got to understand what Barchan dunes are and where and how they can show up. Among all the types of dunes present in nature, one in specific, which we call Barchan dune, is widely studied by physicists and geophysicists. And this kind of dune has a crescent-shaped form, and they appear in areas of unidirectional fluid flow and with a limited amount of granular material. So we can find them in some environments, for instance, on Earth's surface, and we can find them on deserts, in bottom of rivers, and in industry, we can find them inside oil pipelines. So I brought some photos over here, so some examples of Barchan dunes. So this photo over here, the first one, we can see some Barchan dunes on surface of Mars. So this one, some Barchan dunes on California, United States, and also this last one. We can perform some experiment using Barchans under water. Okay, so the difference between these environments are actually the scales they are related to. So for example, on surface of Mars, the time and length scales of dunes are the order of decades or several years, and actually the kilometers to grow and move. When we see Barchans on the surface of Earth, we can take actually years and hundreds of meters to move and to grow. But inside a lab or Barchans underwater, we got smaller time and length scales in order of millimeters and seconds. To study this behavior of Barchans, and we got to understand the first that Barchans do not live alone. So if you take a look at these pictures again, we can see Barchans interacting with other Barchans. They belong to a dune field. So inside this dune, there is mass exchange, there is collision, and other dynamics which can regulate the behavior and actually the size of the field. So to study this kind of dynamics between Barchans, we started with experiments. with subaqueous Barkans in a binary interaction, which means two dunes interacting with each other. Okay? So first, I'd like to share some previous work we have performed. And we performed these experiments using two piles of grains in a line and off-center position. And we could see 5 different patterns of interaction. The first one, in letter A, we call chasing, where dunes with similar masses does not reach each other. The second interaction we call merging, where the upstream dune collides with the downstream one, and they just merge. The third one we call exchange pattern, where after the collision, a small barking dune is ejected. The fourth pattern observed we called fragmentation chasing, where due to this wake region, the downstream dune splits before being reached. And finally, the last one we called fragmentation exchange, where this fragmentation starts, and as we described it before, but actually the upstream dune collides first, and after this collision, a baby Barkan is ejected. So you can see these patterns over here for the align position, and also the same pattern described over here for off-center configuration. So with all the tests performed, we organized our data into 2 maps. Figures A and B here are the points collected for align and off-center configuration. And if you see figures C and D, they are the same maps, but we just drew lines separating the patterns observed. So we could see that they are quite organized based on the C parameter, which represents actually the relation between masses of dunes on the grain scale, and also the Schutz number, which relates the mobile and resisting forces. So taking this into consideration, our goal right now is to investigate the motion of grains over Barkans during a Barkan-Barkan interaction called exchange, as I described before. You can see some animated movies. So our goal is to investigate what happens with the velocity field over Barkans during collision for both align and off-center configurations. Okay? So to do that, I'd like to explain our experimental setup first. So it consists in a 5-meter closed conduit channel with a rectangular cross-section area, 2 centrifugal pumps, a water reservoir, a flow straightener, a settle tank, and a return line. I put a picture here describing our test section, which you can see a camera, our channel, the grains before they turn it into barking dunes, the LED lights used, and the traveling system. So our test section starts from 40 hydraulic diameters from the channel inlet, so which means we got a fully developed flow, and we used a high-speed camera to track the particle displacement. So our frequency was up to 200 Hertz. And after we take this picture, we used a PVLab software to analyze all the images acquired. So we use a variable mesh from 64 square pixels to 80 square pixels, and the total time of our experiment was 4 seconds. So right now, after all this describing, I'd like to share some results what we have been doing. So first of all, we got the velocity fields of Barkans during these 2 states for both align and off-center configuration. So figure A and B, they represent the exchange pattern during off-center configuration, figure A the initial stage, and figure B the end of this interaction. And the same in the figure C and D, but for the align configuration. We can see from this figure, during the initial and final states of the align configuration position, figure C and D over here, it's possible to observe a variation of the longitudinal velocity through the symmetry axis of the dune, which I illustrated here by this red section. There is a region we actually put between these two red circles in the figure, which would be the recirculation area of the upstream dune, which has a movement of the particles in the opposite direction of the flow. Although we do not have measurements of the fluid at this moment of the interaction, it's possible to observe a difference in the height over the dune, which actually may result in acceleration of the fluid after this region, resulting in a higher erosion of the particles until the new baby Barkans has been ejected. And also from this figure here, the figure A, it's possible to observe that the behavior during the collision is quite different, because there is this off-center parameter between dunes. So there is no region with negative or even new velocity of the particles because of this offset between dunes. So about this image, we can take this information, and taking this into consideration, we plot some velocity variation across and along this symmetry axis as I described it before, and we normalize it by this velocity by the shear velocity for each stage of the interaction, and the distance, which starts over here in the upstream region as I described it before. This distance is normalized by the length drag, which scales Barkan lengths. Okay, and from this figure we can see that there is a difference in the velocity field over the dune, with regions of acceleration and deceleration of the particles in both states. The exception is in the stars. You can see here the first stage of the off-center configuration, and we do not have this deceleration behavior, and the reason is because the dunes are in the off-center position. Okay, and from this figure we can take this information, and actually we are still digging about this, and although these results are preliminary, they may be responsible, this variation along over the Barkans may be responsible for the ejection and birth of new Barkans. So after all this explanation and all these results I presented here, I'd like to conclude and also just talk about some next steps we have been thinking about. So first, we plot the velocity fields over Barkans during this Barkan-Barkan interaction. The first interaction we are investigating is the exchange pattern, and we could see this kind of acceleration and deceleration of the particles velocity in both states. So right now we are thinking to track the number of grains moving per unit area of our mesh. Okay, so I believe that's this I bring today. So I'd like to say thank you to FAPESP for the financial support, and also to University of Campinas. If you have any question, if you have any ideas which can improve the work, you can contact me anytime. Thank you for watching this presentation.
William, I need to say that your work is amazing. Congrats for that. It is a very rich and detailed work. It seems we have two questions here. The first one, it is, there exists a specific motivation to study such Barkan structures? And there is a second one. Barkan was someone that named it for the first time.
So hi, Professor Luis. Hi, everyone who is watching right now. Thank you for your words and comments. And thank you for these two questions. So first of all, the motivation we are looking here is to understand the dynamics between a fluid and a solid behavior, right? When we do have interaction between a fluid and some material like a granular material like sand or even other kind of granular mixture, if the fluid is on a unidirectional orientation, right, this kind of dune appears, right? So we are trying to understand this behavior because we have so many examples in nature, like deserts, rivers, and also on surface of Mars, extraplanetary environments. So we are looking to understand this kind of dynamics on this. If we take a look on industrial side, for instance, we have another application inside oil pipelines, right? It's a unidirectional fluid flow and interacting with some particulate inside that, and this kind of behavior can also appear. So I think this is our main motivation here to understand this kind of dynamics. So for the second question, I am not sure if the name of Barkan belong to a person who just saw this in the first time. I got to take a look on maybe internet to know why this is the name.
Yeah, definitely. This is the first time that I'm hearing this name too. And we have one question. Is there any line of research to reproduce a computational solution for this experiment?
Yes, thank you again for this question. Yes, there is. Inside our lab here at the University of Campinas, we are using some computational methods to solve and to understand this. We are using OpenFOAM plus a lights software. They are both free software. So we are using OpenFOAM to solve the fluid, right? And also lights to solve the granular mixture we are using to develop the Barkan dune. So when we couple this OpenFOAM plus lights, we can make some and prepare some simulations. So the question is the answer is yes. There is some ways to solve this behavior using using the computer, right?
So we don't have any more questions from YouTube. Is there anyone here on Gmeet that would like to ask something to William? No, I have one question. William, it is possible in some way to relate your work with the formation of avalanches?
Yes. For instance, when we take a look on the shape of Barkan dune, there is a region in the middle of the Barkan dune where these avalanches happens, right? So the grain just move from this kind of transport. So when we take some a look inside this particulate, we can understand a little bit, but in this part, inside a Barkan dune shape. Without this, we got to dig a little bit more about this avalanche behavior. But inside a Barkan dune shape, yes, we can understand that.
Thank you, William. Probably the beach will not be the same anymore because of you. So thank you.
Thank you.
Congrats for the amazing work.
Thank you, Professor.
So let's move on. Our second work, the title is Computational Model for Path Mapping of Spherical Particles in a Continuous Medium Bulk Materials Fall. The author is Rodrigo Leão from the Federal University of Espírito Santo.
Xavier. I'm here to present my work entitled Computational Model for Path Mapping of Spherical Particles in a Continuous Medium Applied in Bulk Materials Fall. It was developed in the Computational Transport Phenomena Laboratory under the guidance of Humberto Bellis and Márcio Martins. So we can define bulk material as a material composed by particles. Here we have some examples. And here is our motivation. The bulk material fall can generate dust. Here, dust being generated. So how is dust formed around a bulk material fall? And what's the size of particle prone to form dust? Here we have bulk material fall dynamics, and it's well explained in these two works here. So basically we have the big particles falling in the center here, while the small particles fall around in a plume shape here, something like that. This core drags the air around it due to the noise-slip condition. This air is accelerated, and this changes the pressure field here, and it will create a low pressure zone here and a high pressure zone here, induce the formation of a vortex, which in turn induce the formation of upward air currents here. And upward air currents can carry the microparticles away from the control volume. Here we have a finished solution of this case, and the core is here. So we have the drag air zone or the induced air zone. Here the vortex zone or her circulation zone, and here the upward escape zone. So here's the definition of ISO of what is dust. So we can consider dust particles below 75 micrometers in diameter, which settle out under their own weight, but which may remain suspended for some time. So it's a somewhat open concept. And to have an idea of the scale, here you have a human hair, which is around 50 to 70 micrometers in diameter. So we're talking about particles that have a diameter near a human hair. And these particles are easily transported by air. And if you have an industrial scale, the uncontrolled dust can become a social problem because these particles go to somewhere, and it can be houses or it can be the oceans, and we don't want this in the 21st century. So here we have the particle motion equation by Max and Halley. And here we have mass, time acceleration, and the gravitational force or the Bohr force. These terms here, they can be neglected, okay, in our case. This is an impermanent term, so it's not the case. Here we need to have some recirculation, and here is due to the buoyance, so they can be neglected. So the drag force acting on a particle will be 3p, the dynamic viscosity of the continuous medium. That's why the subscribe C. Where you have subscribe C, we talk about the medium, and it can be the air or it can be dust. So here we have the particle diameter, the drag factor, FO, the continuous medium velocity V, and the particle velocity U. So the drag factor is calculated by this equation here, where CD are the drag coefficient, and this term is the relative Reynolds number presented here, and the particle diameter times the difference between the velocities, divided by the kinematic viscosity of the continuous medium, and the kinematic viscosity defined by the dynamic viscosity divided by the specific mass. If we are working with small particles, you probably will be in a Stokes flow, and in a Stokes flow, the drag coefficient have a first degree relation with the relative Reynolds number, this line, and is given by this equation. So in this case, we have the drag factor equal 1. Here we have an analytical solution, and we consider weight, the buoyancy, and the drag acting on the particle. And D, when we have the subscript D, it's the particle or the dispersed phase. And in this equation, we do F equal 1, Stokes flow, and this buoyancy term, and K is a drag term. And we have this differential equation. So here the solution of the differential equation. And if time tends to infinite, the particle velocity tends to its final velocity. It's given by this equation because these exponential terms, they are equal to 0. And the final velocity of the particle is this term, Bg divided by K, plus the medium velocity here. So if this term is considerably small, we can say that the particle tends to the medium velocity. What is the case for small particles like particles of 10 micrometers in diameter? And if you see here, the terminal velocity of the particle is exactly this term here. Here we have the equations applied on the computational model. So we have here the velocity equation and the displacement equation discretized in terms of delta t. And to solve these equations, we need the acceleration, and we can obtain the acceleration, calculate the force acting on the particle for each time step. And the force acting the particle is the Body force plus the drag force. And we divided the force by the particle mass to obtain the acceleration in the time t. So the acceleration in time t will be a Body force, and this will be gravity in the vertical and will be 0 in the horizontal. We have this term that is dependent only of the properties of the case and is a constant. F is 1. And this equation, the medium velocity, is a space function. And so we need to obtain the particle velocity in each time step to obtain the acceleration in each time step. And having the acceleration at time t, we can calculate the new velocity of the particle and the new position of the particle using these equations here. Here we have some terminal velocity cases for particles of 10 to 15 micrometers in diameter. So here we need to observe that if you want to observe the acceleration of the particle, you need to keep your model time step below the particle terminal time, which is the time to reach 99% of its terminal velocity. So if you're working with particles of 10 micrometers that have a terminal time around 5 milliseconds, we need to work with a time below that, and our time step of your model have a half of milliseconds. So here we have some preliminary results in table 1, and they will help us to understand why particles up to 10 micrometers in diameter are the main source of dust formation. And if you look here in the final column, we have the suspension time of a particle, which is the time necessary to the particle reach the ground from a certain height. In this case, is a 1 meter in height. So the suspension time of a 10 micrometers particle is around 1 minute and 16 seconds. And during this time, any velocity above 13 millimeters per second can carry the particle away. This is the terminal velocity of the particle here. So it's too easy to particles of 10 micrometers to follow the continuous medium velocity. In this case, we are talking about iron ore particles. And by the same idea, we can consider that particles of 20 micrometers in diameters are also prone to airborne suspension, because it have a suspension time of almost 20 seconds and a low terminal velocity. Here we have our first conveyor belt case, and the particles have an initial velocity of 1 meter per second in the horizontal direction. In this case, the particles are falling in quiescent pure air. Here are the air properties. This dashed black line is a vacuum case. And we have here particles to 10 to 200 micrometers being analyzed. And what we can see in this case is that the biggest particles tends to a Newtonian behavior, while the small particles, they suffer great action of the drag force. In the second case, we consider that the book fall generates an upward air current inside the control volume, and this has this intensity here. This is an upward current of pure air, and we can see by the dashed lines here that considering this upward current inside the control volume, particles up to 15 micrometers in diameter can be carried out from the control volume. We keep the straight lines. The quiescent case has a reference here, and we can see how the upward currents change the behavior of the particles. In the third case, we consider upward air currents inside the control volume, but now it will be a dust current, and the dust have a different specific mass of the pure air, and this can be calculated by this equation here. And if we consider a concentration of 0.0025, we obtain a specific mass for the dust of 13.8 kilograms per cubic meter, and subscribe MO is the mixture, so the dust is the mixture in this case. So we have a higher specific mass, and we will have a higher drag force acting on the particles. So in this case, particles up to 200 micrometers can be suspended and carried away from the control volume, like we can see by the pink dashed line here, which represents the 200 micrometer particles. Okay. And the fourth case, we consider a structural fan above the belt, and the structural fan generates air currents on the top of the control volume, and the air currents have this intensity. It's dust currents. Okay. So in this case, the structural fan was capable to suck particles up to 115 micrometers in diameter, but the particles of 200 micrometers in diameter are carried away from the control volume anyway. So this all was hypothetical cases that I presented here. And the idea was to present a computational model of easy implementation and low computational effort that can be useful when analyzing dust formation. And we saw that particles with a diameter of up to 200 micrometers can suspend. A structural fan has been shown to suck particles up to 115 micrometers. And in table 1, we saw that iron ore particles with diameter up to 20 micrometers are prone to form dust too. And the model, if you adjust it, can be useful in making decisions related to the reduction of dust formation. Here we have some reference. So this is it. Thanks. Any questions?
Hi everyone, my name is Fernando.
Rodrigo.
Hello.
Congrats for this great computational work.
Thank you.
We have a question on YouTube. It is from Eric Quintela. What do you think about humidify your bulk material previously in order to increase their cohesion and consequently decrease the plume of dust?
Thank you for the question, Eric. And we are working in some lines when we talk about dust formation. And in this case, I try only to show how we can create a computational model to analyze the displacement of microparticles. In this case, we already have the continuous velocity, which is a space function, so it's not a time function. We consider a permanent continuous velocity field, and we displace the particles inside that. What you're talking about is reference to other works we are doing, and this could be done, and probably would be done, like we saw yesterday with André, but it's not what we are doing in this work now. So I don't think so if I answer your question, but we're not doing experimental and not simulating the plume fall in this case.
I was thinking the same thing that Eric was thinking, because you have some very complex equations in your work. I was thinking, what will change if you include the humidification in your work? Could you tell me something? Because your work seems to be very complex. You know, it is a computational model, very, very hard to do it. But if you include humidification, what will change in your model?
Yeah, I had some ideas yesterday, watching Andrea's presentations, the mini course, and here it's not complex. Okay, so we have only 15 minutes, but if I had more time, I could show you that it's too simple, and this is probably the basis to, if you want to begin a computational model for this kind of particle displacement. It will have only here, what you have is the drag force, which depend only on the velocity difference between particle and the medium. So this is the only force acting in this case. So if you put humidifiers, first we need to consider attraction force, and we need to consider the shock between the particles, which are not in this case too. So these two equations should be, we should use these two equations too to calculate the acceleration of the particle. This force should be include in that term of force. That term of force should be more terms there to consider this case.
Okay. We have a second question for you, to you, Rodrigo. Everyone is concerned about to change your conditions. So how the particles would behave in different weathers, like sunny, if we include sunny.
Okay. Yeah, probably we have this humidification problem too. If you are in a, you have to meet humidity in the air. Okay. So we probably approach this considering the humidity of air and adapt that to how this interfere in the force. And we have a big problem, which is the air viscosity, that it changes, where if you have particles, microparticles in the air, this will change the air viscosity. But we don't have literature about how the air viscosity changes in presence of particles. We have some things, but we have not something concrete. And we have problem of viscosity to consider in this case.
Thank you, Rodrigo, for your very nice work. So let's move on to our third work. The title is Flow Measurements in Narrow Fluidized Beds. The author is Fernando Cunes from the State University of Campinas.
PhD student at the University of Campinas. And first of all, I would like to thank you for watching this video. Today I'm going to talk about a part of my PhD that its title is Flow Measurements in Narrow Fluidized Beds. That was developed by me and my advisor, Professor Eric Franklin. So let's start. So, fluidized beds are basically explained as a suspension of solid particles submitted to an ascendant fluid flow, where the fluid may be liquid or gas. Here, there is a balance of forces between the acceleration of gravity, which entrains the particles downwards, as we can see in this animation, and the drag force exerted by the fluid flow, which entrains the particle upwards. So there is a balance of forces. Thus, the granular bed reaches the suspension. Fluidized beds are extensively found in industrial applications due to their ability to transfer high rates of mass and heat. For instance, they are used for separation of material in mineral industry, as well as for combustion and gasification of biomass in chemical industry. Although the fluidized beds have been studied for many years, their dynamics is very rich and then difficult to understand yet. So for that reason is that we are studying the fluidized beds. If the ratio between the tube diameter and the grain's diameter is less than 10, then we have a narrow fluidized bed. In this particular case, the high confinement effects due to the low ratio between the tube and the grains leads to the formation of granular plugs. For this specific case, besides the fluid forces on grains that are given by the drag force and the virtual mass force that is considered in this work because we are working with liquids, we also have the influence of the redirection of forces, as we can see in this picture. Here we also have the formation of arcs due to the redirection of forces and the solid friction force between the grains and the wall. So in this case we have two mechanisms that tends to block the particles, as we can see here in this region, and that tends to displace the particles upwards. In this case, the mechanisms that tend to block the particles is given by the acceleration of gravity and the solid friction between the particles and the wall. And the mechanism that tends to displace the particles is given mainly by the fluid forces. In this work, in this first work that I made in my PhD, We compared our experiments with numerical simulations. As we can see in this animation, the numerical simulations represented well the behavior of the narrow fluidized beds. As in this part of the numerical simulation we have access to all the information of the particles, we computed the network of contact forces to see how is the evolution of the contact points over time. As we can see here, in the case when the granular plug is formed, we have that there is a high redirection of forces that comes from the center of the tube to its wall. Finally, in this case, we can see that the granular plugs are formed by a high concentration of particles, and the liquid bubbles are formed with a low concentration particles. In this another work, we studied the crystallization and jamming in narrow fluidized beds. This effect occurs when we decrease the velocity of the fluid flow to a velocity slightly higher than the minimum fluidization velocity, as we can see in this picture. So the grains start to organize from the inlet of the tube to the top of the granular bed, as we can see here. If we analyze the granular temperature, as we can see in this figure, we can see that the granular bed starts to behave as a solid, and in this case from the solidification front above these values, we can see that there are higher values of the granular temperature, so in this case the bed behaves as a liquid. So for that reason we call this line as the solidification front. But when we, in this case, in this region, the grains maintain a microscopic motion, so in this case we call it as a crystallization of the granular bed. And then if we increase a little bit the velocity of the fluid flow, we can get the granular bed JEM. In this case, the microscopic motion of the granular bed disappears. But if we increase a little bit more the velocity of the fluid flow, then we can get another crystallization structure that is given by a volcano-like structure, that is an annular structure, when the particles organize in the tube of on the wall of the tube, and then the fluid flow passes through in the middle of that structure, as we can see in this animation. So all the grains goes to the wall, and in the center of the tube it just passes the fluid flow. Therefore, the main goals of this study are to measure the fluid flow in narrow fluidized beds by using the refractive index matching technique, to understand how the fluid flow induces the grains to form different patterns and how strong its influence is when particles crystallize and jam, and finally to calculate the instantaneous velocities of fluid and particles before and after the crystallization is reached. The experimental device that we used in this work was basically consisted in a fluid reservoir, a centrifugal pump, which was controlled by a variable frequency driver and a computer, a set of bulbs, a flow meter, a flow homogenizer, a vertical acrylic tube, and a return line, so the fluid flowed in a closed loop. The fluidized beds were formed with glass beads, and we used water plus potassium thiocyanate as a fluid in order to match the refractive index between the fluid and the particles. In the test section, we also used a visualization box that was filled with water in order to reduce the distortions due to the curvature of the tube. The light source that we used in this work was a green laser sheet that was projected in the middle of the tube, and a high-speed camera was used in order to acquire the images. For our experiments, we used 3 flow rates which corresponded to these values, and the granular beds were formed with 4 arrangements of particles consisted of 200, 250, 300 and 350 particles. This table shows the main parameters used in our experiments, which this term is the settling velocity for one particle, for one single particle, and is given by this expression, where this term is the terminal velocity and this term is the initial packing fraction of particles, where is given by this expression, where this term is the total volume of particles and this one is the total volume occupied by the particles inside the tube. To process the images, first we detected all the particles with our own scripts written in MATLAB. As we can see in this figure, we detected all the black holes in the raw image, and then we created a binary mask, which is given by this figure. So we have access to all the particles in the middle of the tube that are moving along the tube, and then we have the resultant image. So to obtain this image, we computed the instantaneous velocities by PIV processing, and then we erased all the spurious values that are given by the particles or the black holes in this image. So we erased those values by applying this binary mask. For our results, first we measured the base flow without the presence of particles. As we can see in this animation, the flow direction is given upwards, and we use this flow rate. And as we can see in this figure, we computed the vertical mean velocity and the XY component of the Reynolds stresses, as that is given in by this figure. From this, we can see that we have a well-developed fluid flow, and also we have that the shape of the XY component of the Reynolds stresses is well behaved. As we can see here, the stresses go to zero in the walls and in the middle of the tube. For our experiments with the fluidized beds, we computed the instantaneous velocities of the fluid flow at different times, as we can see in this figure. First, we took a picture when the particles don't move, and then we imposed the different flow rates, as we can see here. And then we computed the flow around the particles at each time step. In this figure, we can see that around the particles, the flow is accelerated, and the flow reached a value 1 order of magnitude higher if we compare this velocity with the velocity when in the absence of particles. Finally, we also measured the fluid flow after the crystallization process occurred, as we can see in this animation. Here we can see that all the particles went to the wall of the tube, forming an annular structure known as volcano lattice structure. Above the granular bed, we can see in these regions that there is a recirculation of the fluid flow. From this processing of this video, we computed the mean velocities of the fluid flow at different flow rates, as we can see in this picture. So, in this picture, we can see that even for flows high enough, if we compare this value with the minimum velocity of fluidization, the particles are jumped with no motion. From this figure, we also computed the vertical component of the mean velocity at different heights above the granular bed. As we can see here, for the height just above the granular bed, we can see that the velocity profile has negative values in regions close to the wall, and then it reaches its maximum in the center of the tube. If we follow the behavior of these curves along the tube, we can see that it starts to increase for this value of height, and then it starts to decrease until it gets the same shape as the base flow. If we analyze the XY component of the Reynolds stresses, we can get the same behavior as the vertical component of the mean velocity, where the maximum of the shear stresses starts to increase to this height, and then it starts to decrease until it gets the same shape of the base flow. Finally, our conclusions were the first one is the fluid flow was measured before and after the crystallization process takes place. In the case of the crystallization, the grains were trapped, though with small fluctuations, so we have the microscopic motion, and if we increase the velocity a little bit, we have that this microscopic motion stop at all, and we don't have a fluctuation of the particles. Then we have that the flow velocities near the particles are higher if we compare those velocities with the velocity fields located far from the particles. And finally, for the volcano-like lattice, we found that the fluid passes in the middle of the lattice in the crystallization process, as we show it in this work. So thank you very much for your attention, and if you have any questions, please don't hesitate to send an email to this address.
Thank you, Fernando, for your very nice presentation. We have a question on YouTube. Adriana, from Adriana Malafaia da Mata. She asks, what are the applications where the narrow fluidized beds are in relevance?
Hi everyone. Thank you, Professor Luis, for giving this question. About your question, Adriana, thank you for your question. First of all, the narrow fluidized beds now are working with in fluidized bed reactors, mainly in the biological treatment of domestic wastewater. In the last years, it was useful because when you have to treat the wastewater, you have a lot of particles, big particles, and also small particles. So the main goal of these bioreactors is to understand how is the behavior of the particles inside the tube. And in this case, when you have like big wastewater, you have to treat these particles are modeling as big particles when you compare with the diameter of the tube. And another application is mainly in the medical industry for the production of pills. In the last years, mainly in this year, due to the coronavirus, the COVID-19, there are a lot of medical industries that are trying to transport pills and trying to transport the new vaccines in a powder form. So in this case, understanding the behavior of the big particles inside the tubes in the big scale, we can take this behavior to a micro scale behavior. So I think that's it. I don't know if I...
We have more questions from the audience. Ramon Martins is asking, would you have any explanation for the behavior of the shear Reynolds stress close to the wall? Is this a measure measurement or real flow situation?
Yeah, close to the wall, the shear stress, the main Reynolds stresses actually is the XY component of the Reynolds stress, have to be zero because the fluctuations of the velocity are zero, right? So they have to go to zero. I don't know if that is the question that I have to answer. Yeah, it's that. So it's a real flow situation because you don't have velocity, you don't have a slip in the wall, so the fluctuations goes to zero.
In some point in your presentation, Fernando, you said something about temperature in your system. How do you calculate or do you measure the temperature?
Okay, so in this case, it's like an analogy from the real temperature that we used to know. In my case, is the granular temperature. So how do you compute the granular temperature? It's just to compute the energy that the fluctuations of the particles are giving in our system. So if you compare like how the temperature or how you increase the temperature in a material is like the fluctuations that at the atomic scale, the atoms or something like that suffers in order to increase the temperature. In our case, the fluctuations of the particles it's just an analogy. The temperature, the real temperature of the particles are always the same, but the kinetic energy of the particles or maybe the fluctuation of the particles starts to grow or it starts to decrease, depends of the system that are we working on.
Okay, our time is very sharp, but Ramon would like to ask you something more, but maybe you two can connect and discuss this question. Thank you so much, Fernando, for your presentation. Let's go to our last work. It is our fourth work. The title is CFD Model for Free Falling Bulk Materials Analysis. The author is Leandro Lima from the Federal University of Pará.
My name is Leandro. I am a student of Federal University of Pará. I represent the Laboratory of Fluid Dynamics and Particulate (FluidPA) from the Amazon Development Center in Engineering. This work is about a safety model for free-falling bulk materials analysis, done by me, Leandro Lima, Marcel Furtado, and André Mesquita. So, the structure of this work is introduction, safety model, case study, results, and conclusion. So, the handling of bulk solids often involves free falling of particle streams in air, such as falling particles from a hoop in a silo. The free falling particles can induce the flow of still air due to particle fluid interaction. The induced air will usually detour from the mainstream of the solid, and at the same time, fine particles containing the particle streams will be entrained into a flow, causing dust emission into air. The dust emission is hazardous to both the environment and the health of the operation personnel if not properly controlled. Air explosion may happen when the dust concentrations reach certain volume. Then, since the work of Eman 1960, several studies have been conducted to calculate and determine the capacity of entering the air during the free fall of granular flows. The figure 1.3 shows the example of dust generation at reference points, formation of water piles, and material discharge. The entrainment pattern of free falling streams of bulk materials can be influenced by bulk materials properties such as particle size and density, as well as operation conditions, such as drop rate, particle mass flow rate, and other environment factors. So, in this case, we can see another experimental apparatus by Whipshed and Cook in 2005. So, recent study was performed by Ismaili 2013, where experiments were presented to measuring the air induced by free-falling particle flow. From these results, a new semi-empirical for predicting the induced flow rate is developed and presented to form of an analytical equation. This section presents an approach that explains of the concept presented by Cooper and Arnold to calculate the amount of entrained air for free-falling ground materials based on the conservation of the volume. The volume of the free-falling streams from the hopes with the single outlet is estimated to the volume of Taconi, like we can see in figure 1.6. So, for each of the above materials in study, a high-speed camera was used to record the falling stream of particles over the range of drop rates. The general layout of experiment can be seen on figure 1.7. JEM. Nowadays, significant efforts can be devoted to improving numerical tools such as computational fluid dynamics, or CFD, to predict such problem flows. However, today we have ANSYS, we have OpenPhone, and Eden, and others. So it was being identified that systems containing only or more particulate phases are the most complex and challenging on the field of multiphase flow modeling. To accurately predict the solid behavior, it is necessary to choose a numerical method capable of accounting not only particle-fluid interaction, but also particle-wall and particle-particles interaction in 3 dimensions and across any particle size distribution. In dealing with modeling gas-solid flows, the Eulerian is and the Eulerian-Lagrange methods are the frequently used approaches. So, in Eulerian approach, all the phases are treated as continuous phase, while in the Euler-Lagrange approach, the fluid phase is treated as a continuous phase, but the solid phase is treated as a discrete phase. So, we have some research already carried out using CFD to study particular materials. According to Chu at 2020, in recent years, numerical modeling has proven to be a useful tool to improve the fundamental understanding of fluid flows in literature. The author developed a study via CFD, discrete element method, analyzing that both the rate of induced air and the drag force filled linearly according to the height of fall, but the results can be varied and the airflow is difficult to be estimated only using the drag force. So, the same way, Schultz at 2019 also used CFD and coupling modeling to investigate the release of dust from the book solids during handling in iron piles under winding influence. So, I'm going to our model, the DPM, dense discrete phase model. For this model, we have the equation 1, then the equation 2. I show a continuous equation, then the momentum equation. So, we have in these terms representative of Maleshian cells with the continuous phase. These terms is responsible to coupling between the phase, and these terms represent the other forces that come to act the fluid, and these terms as the volume fraction of the phase, the fluid phase, and these terms represent the transport speed between the phase, and these terms represent the coupling coefficients between the phase. So the coupling between the phase is done through the term FDPM, which incorporates the change or gain or loss of the amount of movement during the passage of the discrete phase through each control volume of the compositional mass of the continuous phase. So the coupling term of the amount of movement is expressed by the equation 3. So we have these terms is represent the coupling coefficients of the drag force, and these terms represent the other force of the discrete phase incorporate of the model, in this case the DPM. So ongoing, we have our model. Now we can see the model is the same schematic by Ismaili 2013, and this is the equation developed for him, and these are the material settings used in the experimental setup. So now we can generate the mesh. We generate 4 mesh for test of convergence. We decided to utilize mesh number 4, and this is our parameters to configure it. To make it more easy, we can show the configuration in Fluid. So we can choose the Euler model and selecting dense discrete phase model. Then we choose the turbulence model, and we will configure the discrete phase model. In discrete phase model, we can set up our particles with diameter, velocity, and mass flow rate. We choose the Guidaspo for the Drag's law, and we configure the same drag float used by Ismaili 0.47, and we select the same velocity for the each experiment. So the results are obtained through the self-depot auto-evaluable and the ANSYS software. Lines and planes were used to obtain the results at the respective rate. Then, furthermore, based on the simulation results shown in the figure 4.2, it's possible to notice a very large dispersion of the induced air velocity field from inside to outside flow, causing a detachment in relation to the surrounding air as the rate drop is increasing. So, in the figure 4.3, represent the simulation air velocity constant for the influence of drag caused by the fall on the analyzed particle. The plastic pellets with the same diameter as the glass beads should allow maximum velocity of the surrounding air. This is due to the fact of the influence of the greater mass of the glass beads. The influence of the particle size for the same material can be observed when comparing the result of the 3 and 6 mm particles of the glass, where it is possible to notice that the smaller glass particles with 3 mm has a high velocity of the solar airflow than the particles large with 6 mm. Then, now we can see in the graphic the figure 4.4. It's possible to observe that the particle speeds in the simulation carried out in this work was very close to experimental work carried out by Smiley in 2013. So, in the graphic of figure 4.5, show the results from the high velocities into 900 mm drop sections. This velocity profile can be related to the inconstant shape of the flow of granular material in free fall, concentrating the greatest speeds in its flow center. The figure 4.6 shows the results obtained by Smiley 2015, in which a good algorithm with the author can be observed. Now, from the data of air velocity, it's possible to analyze the induced air volume for each egg based on the average air velocity in the cross-section of the flow diameter. The data obtained from the simulation were used together with the flow diameter D obtained experimentally by Smiley 2013. Then we can see in figure 4.8 show air displacement in relation of the material drop weight for the 3 mm plex pellets of the results predicted by equation 4 in case of simulation using the Euler DDPM model. When analyzed the amount of rain trained by the 3 mm plastic pellets, the simulation performance were maintained a good correlation with the simulation by Ismaili 2015 and equation 4. A target significantly overestimating the amount of air when compared of the experimental data performed by Ismaili in 2013. The sum occurs with the figure 4.9 for the 3 mm glass beads and figure 4.10 for the 6 mm glass beads. How I can see that here and here. So, in conclusion, we have a good agreement with the work of Smiley at 2013 and 2015, and we can say that the DDPM two-phase flow model can be considered as an alternative to the attempt to describe the flow of particles in the air. So, through the simulation, it is possible to conclude that a variation of the drop rate of the material directly influences the variation in the amount of air induced by the falling material. And the use of CFD technicals is essential for saving time and money. So, this is my reference, and thanks.
Thank you, Leandro, for your presentation. We have some questions on YouTube. The first question is from Eric Quintela. An operational solution would be to avoid air to entering the plume of dust, isolating, for example, the book material with plastic curtain attached to the exit nozzle. Don't you agree?
In Portuguese or English?
It can be in Português.
Obrigado pela pergunta. Eu creio que
Essa solução operacional, ela é inclusive muito utilizada hoje em algumas situações de tratamento de poeira, né? Justamente para se evitar que uma poeira passe para outro local, né? Eu creio que sim. É uma boa solução, só que muitas das vezes não é muito operacional, como por exemplo, em chute de transferência, né? Então, a resposta eu creio que sim.
We have a lot of more questions for you, Leandro. The central core have the same diameter in all cases?
No, esse centro ele se altera de acordo com o material que está sendo utilizado no experimento. Então tal que no slide, esse diâmetro de fluxo ele vai se alterando de acordo com a especificação de cada material, ora seja com o diâmetro da partícula ou com a densidade, e sempre variando de acordo com a altura que ele é liberado.
Nice. We have more questions. For the mesh test, which parameter you use to analyze the coverage of the mesh once you have the presence of two phases?
Bom, a minha condição eu creio que não deu para ver lá na imagem, mas foi a velocidade do ar. Eu fiz uma análise em cima da velocidade do ar na minha saída. A partir do momento que essa velocidade ela se tornou quase que constante, ou seja, sem variação, eu escolhi para a minha quarta malha para se utilizar nas simulações.
The final question, Leandro. What are the boundary conditions of your problem?
No caso, a minha condição de entrada, eu selecionei a minha velocidade de entrada do meu material. Uma consideração importante que eu fiz foi considerar a velocidade do ar igual à velocidade da partícula, até para se ter uma boa convergência, que eu percebi isso no decorrer das simulações. As minhas condições de paredes foram abertas ao meio ambiente, no caso open, que a gente consegue selecionar lá na fase discreta do fluent, e a minha saída eu pus como uma condição de pressão outlet que é de 0, simulando uma condição ambiente também.
I'm gonna switch to Portuguese. Leandro, eu não sou um usuário do ANSYS, tá? Então, assim, a minha pergunta é bastante honesta. Como é que você checa se o seu código ou o seu programa, eles estão corretos? Tem algum processo de secagem, assim, de teste para ver se tá certo, se faz sentido físico?
Bom, o principal, assim, digamos que uma certeza que a gente tem, que o cálculo está de acordo com as equações da continuidade, né, que são as que governam o CFD no Fluent, é a questão da convergência dos nossos resultados. Quando ela está sendo calculada de acordo com o número de interações, ela vem lá no nosso monitores, ela tem aquela convergência, ela fala que tá convergindo. Ou seja, quando os resultados eles chegam a uma solução, o próprio software ele dá essa questão da convergência.
Okay, thank you so much, Leandro, for you to apply this wonderful work in this Congress. So here we are finishing this session. I would like to thank you, the organizer, for the invitation. I hope to see everyone next year. See you soon.
Thank you.
E Leandro, você vai ou eu inicio? Vai lá.
Pode começar já?
Pode ir, Márcio.
Start? Okay. Greetings, everyone. Welcome to JEM 2021. Now we're gonna start a panel presentation, and several students are here to present their work along the lines of their study. So we should start now. Who is the first?
I'm going to present about wet gas metering by differential pressure methods.
The first work will be presented by
is essential to industry,
Enrico Sarcina.
possible and appropriate production management, well monitoring, proper transfer, and legal matters. However, in most of the gas production fields, the use of complex multiphase meters is economically unviable. Given this scenario, the use of differential pressure methods to wet gas flows become an important research topic due to its low installation operation costs, reliability, are based on simple principles, and are consolidated in literature with many years of operation history on single-phase measurement. In most of the gas production sites, a single-phase differential pressure meter is already installed to measure dry gas flow. However, separators are not 100% efficient, leaving some amount of liquid on the gas outlet. This liquid loading causes a positive bias on the pressure differential reading, called overreading. But what is overreading? For example, let's use an orifice plate to illustrate this effect. In a dry gas flow, a certain level of differential pressure is achieved when the flow occurs. When the gas contains liquid, three effects surge: interface interaction between gas and liquid acceleration, gas acceleration due to area reduction. These three effects together result in a differential pressure increase, called overreading, culminating in an erroneous gas flow rate prediction. Aiming to correct this shift, authors are researching and developing empirical correlations based on experimental data. This graphic consolidates the most relevant correlations for Venturi, Vacone, and orifice plates. It can be noted that Venturi meters are more sensible to liquid content than Vacone and orifice meters, presenting a higher overreading. To compare the orifice plate correlation performance, experimental points were extracted from Murdoch work and Steven et al. 2011 work. Despite being of the first contribution with gas correlations, and not the limitation of his work, the Murdoch curve predicted overreading for the orifice plates with the lowest absolute shift, with a maximum of 4.8%, while the newest correlation by Steven et al. 2011 had a maximum of 19% of shift. This overreading correction technique will be tested on Oil and Gas Flow Measurement Study Center, NEMOG, at Federal University of Espírito Santo, in a multiphase circuit with air and water flow. The objective is to develop a new correlation for NEMOG circuit. Thank you for your attention.
Hi everyone, my name is Rodrigo Bonacursi, and I'm gonna talk about my scientific project. That's a non-intrusive method to measure gas flow, based on the propagation of acoustic signals. I'm going to start with the project motivation. Some conventional flow meters directly insert in the pipe, for example, orifice plate or reversed cone, perturb the flow, and then it reduces the system's efficiency. Because of that, the flow measurement at petroleum industry has been done using sonic methods. The experimental apparatus used two pairs of microphone sensors to measure the sound pressure, and an air blower was attached at the left pipe end point. Now I'm going to talk about the methodology. The initial step is acquired the experimental data. It consists of pressure sound values. To reduce the noise coming from the air blower, a Butterworth filter was implemented. Now I'm gonna talk about the governing equations. There is a relationship between the sound velocity c and the flow velocity v. 4 and 5 correspond to the governing equations that will be implemented via a MATLAB code to obtain the experimental velocities. This image shows a filtered pressure signal with a Butterworth filter. With the filtered signal, it's possible to obtain the experimental velocities via cross-correlation. Now I'm gonna present the results. The V and E correspond to the reference of average flow velocity, and the VXP correspond to the experimental velocities. The results are great, and the technique proved to be efficient for a given range of average flow velocity. I would like to thank you for your attention.
Introduction. The pulsating heat pipes was proposed by AKK. Its heat transfer mechanism is based on the oscillatory or pulsating movement of the vapor plugs and the liquid slugs along the tube. The figure 1 presented the schematic of a pulsating heat pipe and its design variations, open loop and closed loop. Experimental description. The figure 2 presented the schematic drawing of the experimental bench in a favorable vertical. The data were obtained through a transient method. Thermal resistance in adiabatic region. The thermal resistance of the pulsating heat pipe adiabatic region is presented in EQ. Total thermal resistance model. Using the analogy with electrical circuits, the total thermal resistance of the pulsating heat pipe is presented in EQ. The figure 3 represented the equivalent circuit for thermal for resistances of heat pipe. Total thermal resistance model. The total thermal resistance of pulsating heat pipes is presented in EQ. Results. Case 1. Total thermal resistances with a single turn in the adiabatic section and 2.0 mm in vertical favorable. Results. Case 2. Total thermal resistances with 80 turns in the adiabatic section and 1.6 mm in vertical unfavorable. Conclusion. From the proposed model for total thermal resistance, it can be concluded that the mean absolute error for total thermal resistance is in the range of 24% to 30%. Acknowledgements. The authors gratefully acknowledge the financial support given by CAPES, Coordenaco de Aperficamento de Pessoal de Nível Superior and FAPES, São Paulo Research Foundation.
The extraction of oil in new fields takes place in extreme conditions, such as the high conductivity of saline water. Conductive variation can impact EIT image reconstruction, and an alternative is to make online calibration viable. The study of the conductive on performance criteria can contribute to safety and control. Therefore, this article aims to assess the behavior of EIT performance criteria according to variations in conductive. The methodology is based on measurement protocols. Initially, for system validation, 300 frames were recovered. The median of the recipient error characterizes a system with typical performance, with read less 2%. Distilled water presents larger measurement errors, lower SNR, and higher read. For tap water, the measurement errors present the most representative data, with the highest SNR. However, the reciprocity error for type water was larger than 2%. Finally, in the solutions with saline water, the reciprocity error has reduced to values that indicate high performance with Re less to 1%. The gain is multiplied by the signal measured at the EAT to increase the signal. For security, the signal is usually kept close to 1 volt, because the reconstruction may include signal peaks. It was necessary to adjust the resistor until the gain of 120.05, when the gain stabilized with the measurements close to safe peak of the Arduino. It was possible to observe the behavior of the Korok's law from stronger electrolytes. When increasing the saline concentration, we need to increase the gain. As the molar concentration increases, the molar conductivity decreases. That is, the total conductivity of the solution increases less and less, until it's not necessary to increase the gain. The behavior of measurement errors can be characterized as the salt concentration increases. From saline concentration, measurement errors tend to stabilize, as noted in the table data, through the median value of S and R. And 2 for reciprocity error. Although the conductivity of the solutions has increased significantly, the molar conductivity tends to stabilize. Thus, it's possible that the molar conductivity has a greater impact on the analysis in EAT. However, it's not possible to guarantee that there will be the same behavior in the quality of image reconstruction. Therefore, further investigation is necessary to affect on image quality.
Good afternoon, everyone. I am Clayton Mendonça. I am going to talk about computational fluid dynamics analysis of air liquid water flow using differential pressure meter. This is the presentation outline. This is the purpose of this work. In this work, we will be verified the influence of two fluids in different phases, gaseous and liquid, to compose rich gas flow using computational fluid dynamics. Here is summarized the methodology adopted in this work. The initial conditions are obtained from the work Murdoch paper. These parameters are added to the numerical model. Obtaining the results of the numerical model, this is compared with the result of Murdoch. So, this is the geometry used in the simulation with respective dimensions. Here are some details above the mesh. Here the boundary conditions used are present. To verify the mesh independence, we test 5 mesh size. We choose to take two pressure difference in the orifice plate for single phase flow and plot the graphic. Mesh 2 was the one that obtained the best results and was used in the simulations. Here is the velocity profile with liquid water using mesh 2. It's possible to observe some recirculation zones. The accumulation of liquid water at the bottom occurs due to the difference in specific mass. Here is the error obtained with the simulation to the experimental data. These are my final remakes. Bibliographic. Thank you very much.
Hello everyone, my name is Henrico Sarcinelli. I'm currently a mechanical engineering student at the Federal University of Espírito Santo, UFES, and I'm going to present some OpenFOAM customization basics for unique models implementation. As long as new methods for modeling new physics arises, many of them need some support to be resolved. So having the ability to modify existing numerical solvers can save significant time and effort. So OpenFOAM is an open source finite volume CFD software where all setups and commands are given through coding. So it's built up with a very simple but not very user-friendly interface. As the case setup is a folder and the control dict file is that simple as we can see here. But some of them can be very tricky, such as the setFields dict, which requires a description of a region without a visual interface. Now, imagine that you want to solve a scalar transport equation such as this one, which is very similar to the velocity equation, and it can be done by quickly copying the original solver and mimicking the existing coding lines. And you can find how it is written in the IcoFoam solver, and then add the scalar transport equation to the code, using the velocity equation as a base with the slightly changes. So as the code calls new variables, they need to be defined in the file responsible to create the fields. So you can find a description of the existing variables that most fit the new ones and use them as the basis, such as nu and p used to define gamma psi and psi. And as the solver code is complete, rename the solver and the path, compile it, and it's possible to check if it was compiled well by checking the usage. With the solver ready to run, have a check if the boundary conditions are well described. A good practice is to use the other files as bases as well, such as p used to write psi. As an example, the cavity case was used with an initial psi field settled as shown. The results can be visualized using the software ParaView, and here is an example with the streamlines plotted in white. Now turning to another case, imagine this situation from Xavier et al., where the flow containing airborne dust particles was modeled by the assumption of a single-phase mixture of fine dust and air. It was possible to reach an analytical solution for the pressure field, but not the velocity field. So for that solution, we can use a steady-state turbulence solver, the simple foam, as the base for our solution, and have a look up at the files of the solver. So understanding the simple loop algorithm, it is possible to dissociate the pressure corrections from the code. And this image shows the solution obtained by Xavier et al. With the velocity vectors plotted in a solid color with no size scale. And it is clear the potential of those kind of open source softwares like OpenFlow and how it is easy to represent the equations, and how they can lead to a substantial reduction of time and effort by avoiding the need of developing an entire efficient code using one of the known numerical methods. Thank you for your attention.
Hi, my name is Igor Gouveia. I'm a master's degree student at UFPA no UEM in Curitiba, and I'm here to talk a little bit about my paper entitled Multi-Electrode Capacitive Sensor Applied to the Level Control in a Multiphase Separator. So, the sensor used in this project was designed and developed at UEM and is composed of 16 electrodes, referring to 16 channels that are responsible for capacitance measurements of the different substances inside the tank. And from these measurements, we can estimate the level of the interfaces and send this information to the control system. Here we have the schematics of how the sensor is applied to the separator, and here you can see the test separator we have at UEM with the capacitive sensor prototype attached to it. This separator has a diameter of 30 centimeters and is 1 meter long. The control system was designed to control the multiphase separator values through the sensor response. And the control strategy chosen for this project was the PID controller because it has an easy computational implementation and can be efficient if well tuned. For this work, we started developing and simulating the control loop using MATLAB and Simulink, and then port the system to LabVIEW to make the communication with the sensor and make the supervisory system as well. Here you can see the results of the preliminary tests that we did with the control system developed, and it shows that the water level, which is the black line, is stabilized at the defined set point, and by controlling the opening of the water output valve, the control system let only the oil layer flow over the weir. So, in conclusions, the test showed that the control loop developed was able to separate the two substances in the tank and maintain the water level at the defined set point. For the future, other control strategies may be tested, and a larger separator is being constructed so that the sensor can be adapted and applied under conditions more similar to the field. Thank you for your attention, and I'm available if you have any questions or suggestions. Bye.
So now we are open for questions from the audience. Any questions?
Hello, everyone. I'm here with Leandro. We are mediating this section, so this section is intended to be very relaxing, so don't worry and consider this as a talk between colleagues, okay? So you are free to ask questions, to chat about the other's work. So if anyone has any question. So I have a question. I have a question for Miss Adriana. Adriana, you for each electroconductivity of the solution, you're testing with different resistors, right? So is it possible to also insert the gain in mathematical modeling?
Yeah. We are going to study this possibility, but we need to access the noise because with very low signals, if it's in the same order as the noise, we cannot trust the signal. One option would be to use a correction factor, but this can vary widely from one condition to another. As the gain tends to stabilize, we see that for each background solution, we need to understand the parameters that most impact the measurements. We intend to go deeper into online calibration studies and select effective parameters that can assist in the calibration of measurements by EIT, electro impedance tomography.
Thank you, Adriana.
I would like to make a question to Rodrigo. In your sound measurement methods, can you tell me if there is any significant difference in the using this technique when you have different patterns of flow of the fluid that are being studied, or if that fluid is multiphasic or monophasic? Is there any significant change in the pattern of the sound measurement?
Hello, everyone. Well, Leandro Amorim, the test was implemented for some conditions of the airflow, just a single multiphase flow. So in this case, I didn't implemented a fluid flow, just a single airflow. And the criteria was Reynolds number and the flow velocity. So I didn't I didn't study others kind of pattern flows, just a single flow.
Thank you for the answer. And did you manage to find any major changes for different Reynolds numbers?
Yeah. When the flow velocity is coming up for the range of 25 to 29 meters per second, for example, the experimental error reduced is lower than if the flow velocity is 5 or 10 meters per second, for example. I probably it comes to it was obtained because the cross correlation technique is limited by a range of velocity. Among other things, like the noise comes from the air blower to influence in this aspect, but yes, there's a range of velocity flow that the cross correlation technique produced lower errors, experimental errors, about 2 or 3%, for example.
Okay, right, great. Thank you for your answer.
We have a question from the YouTube chat. The question is for Henrico. Henrico, Rodrigo is asking, what are the practical applications of your work?
Hello, Rodrigo and everyone. I would say the practical applications are more as to speed up the process or to the new models that are under development. So when you need to solve, when you are, such as the Rodrigo's work, actually, that he has another model and has to mathematical model, had to solve the velocity field. So instead of writing an entire code of CFD code or to solve the equations, you can easily implement and use the already built-in functions from the OpenFOAM to solve it quickly. So it will save a lot of time, I would say. And there are, of course, other applications, such as if we can imagine that we have another a parameter, such as humidity or something like that, that we can use it to, we need to implement it into the equations. And I think maybe it can be really hard to do it in a closed source software. And in this way, it is quite easy, as we can see. But in this particular case, I would say this is another application when we are developing a parameter and you need to test it.
Okay, let me complement this question for you, Enrico. Is it also possible to customize the boundary conditions in OpenFOAM?
Sure it is. But I would say in general, it is a bit more complicated than to customize the solver itself. But the procedures are basically the same. But sometimes you need to have some knowledge on programming or things related to this, because you need to actually write all the equations that you have for your boundary conditions, and this can be a bit tricky if you don't have a lot of knowledge or some kind of knowledge in programming.
Okay, thank you.
But yes, it is possible, and it's very an interesting approach.
Thank you.
Question here for Clayton. Why did you use hexahedral mesh, not the tetrahedral mesh?
Okay. Fluent works better with this type of mesh. This mesh is lighter, which take result in relation to the processing time. Okay. Oh, thank you.
You want to say something more? All right. Any further questions for anyone? If not, we can conclude this session. I'd like to thank you everyone for having participating. I'd like to thank you all the students that present their work here, and thank you. Let's move on to proceed our next presentations. Thank you. Marcio?
Can I just put one more question?
Oh, sorry.
No.
Of course.
I have a question also for Clayton. I just would like to know if is it possible to apply your method to high flow rates, because I noted that you used low flow rate, right, in your simulations.
I am investigating possible changes for high float error is what of Ignis standard investigation.
Okay, thank you. Come on, everyone. We need a question from one author to another. Let's go. Let's participate. We have a question here in the YouTube chat for Igor Gouveia. Igor, Bruno is asking, how is the signal conditioning of the sensors you are using?
So the communication with the sensor is made by Arduino, so we use the serial communication with the the computer, and then send the signal to the valve that I'm controlling by 4 to 20 milliamperes is the control. I don't know if that's the sensor is use a serial communication, and then the valve they're controlling is 4 to 20 milliamperes.
Thank you. I think I lost the first part of the presentation of Mr. Jordan. Could you please just tell me the applications of your work, please? Is Mr. Jordan here? No, I don't think so.
I don't think he have presented. I think we have started with Renan.
Okay, okay. So do we have another question? Let's go. Come on, everybody.
I would like to make a question to Mr. Renan about his work. Have you found any significant difference in studying the models of more empirical models like Murdoch's and theoretical models from Chisholm or Stephen?
There is difference between these works, but the difference is relevant when you change the type of the differential pressure meter. For example, orifice plates have some amount of overrating, but when you use Vicone or Venturi, the overrating increases. But between the same meter, this difference is not so relevant.
And there is any difference when you use different types of patterns flow, like stratified flow or churn flow? There any difference?
Most of the authors they mention two types of flow patterns: stratified flows and annular mist flows. Okay. And the other kinds of patterns is not mentioned. I didn't read yet about other.
Not even the
patterns.
bubbles.
No.
Oh, all right. Thank you. Thank you for your answer.
Okay.
We have a question here in the YouTube chat from Ramon to Adriana. Adriana, is there any perspective to use this EIT approach for flows with 3 or more phases?
Yeah, I'm here. This is a study. This study intended on the future relies for 3 phases, but the EIT has a limitation. EIT distinguishes only water from oil or water from gas, because the electrical conductive of oil and gas is approximated for 0. Okay, and for intended 3 phases, we need to complement it with other techniques, and other techniques can improve also detections of variations in fluxes, the well, when we can very slow temperatures and conditions is exchanges and different conditions, when we can very guess and the one technique is not possible the total flux in this variation. Can you understand me? If you can say Portuguese.
E Adriana, eu entendi sim. Obrigado.
Thank you, Adriana. We have another question for Igor Gouveia. Does your sensor can be used to measure emotion in separator?
Yes, it can be, because every substance has a different electropermittivity, so measuring the capacitance, the level is different between water and emulsion or oil. So if I can make an efficient correlation, I can identify an emulsion and separate from the oil and water.
Thank you, Igor.
Any further questions?
Come on, let's go. More questions?
Eu tenho uma pergunta, vou falar em português.
Ok.
Pro Clayton. No teste de malha, qual foi eu vi ali que você usou o parâmetro, foi o ΔP, mas aonde que é esse... Em qual ponto você utilizou para analisar, ou se foi a superfície?
Ok. Então, o teste de malha foi feito em torno da placa, cara, de orifício, na variação de pressão da placa, porque ali eu conseguiria ter os melhores resultados, né? Para isso, no caso, eu peguei tanto a jusante quanto a montante, aí rodei o meu modelo, acabei obtendo ali, no caso, a variação de pressão, e dessa variação de pressão eu calculei o erro, né? Como eu tinha, no caso ali, eram 5 malhas, aí dessas 5 eu peguei a mais refinada, considerei ela no ponto mais, como fosse a malha mais qualificada para atender as melhores condições, né? E com isso eu fui me baseando nas outras. Acabou que eu obtive um erro menor para a malha número 2, que tinha 4 milhões de elementos, e ela eu usei para fazer o trabalho. e o parâmetro que foi utilizado foi a vazão de ar. Eu considerei o modelo monofásico para fazer o teste de convergência, né? Porque aí eu consegui ter os melhores resultados. Pelo menos para o teste de malha, isso já atendia a minha necessidade. Ok? Consegui explicar?
Sim, sim, perfeito. Valeu.
We have one more question.
Eu posso fazer mais um levantamento de questão?
Sim.
Eu queria compartilhar. Hoje eu recebi um aviso de um colega que trabalha com essa aplicação de medições em óleo e gás, e ele estava contando que eles usavam um medidor multifásico ultrassônico, e ele era empregado a determinadas condições ideais não, reais, mas condições já pré-calculadas. E aí eles tiveram um problema que o medidor ficou por 40 minutos sem conseguir inferir as medições, justamente por causa de uma temperatura mais baixa no oceano, que gerou essa saída de gás maior, né? E aí comprometeu a medição, e eles só conseguiram, o que achei curioso, né, é que eles só conseguiram medir depois que o padrão normalizou para as condições, o fluxo do petróleo normalizou para as condições pré-calculadas. E aí a gente vê uma inversão, né, que seria o padrão precisando se ajustar ao medidor. Acho que é um levantamento, uma experiência importante que ele trouxe para a gente se atentar, né, nas medições.
Acho que o Ramon quer complementar também, Ramon? Ramon quer complementar?
Não, é uma outra pergunta.
Ah, ok.
Quando puder, me avisa aí. Não sei se alguém vai comentar ainda o que a Adriana colocou, mas...
Pode seguir com a pergunta, Ramon.
Maravilha. Minha pergunta é para o Rodrigo. Bom, ele apresentou lá alguns resultados experimentais usando o ar, né, no aparato deles. Minha pergunta é se eles têm alguma previsão, alguma indicação para caso o fluido seja diferente, né? Por exemplo, sei lá, um gás natural com uma composição específica, enfim, qual a influência de uma eventual composição diferente na questão da acústica ali, por exemplo, se tem algo previsto nesse sentido, se foi testado e tal.
Boa tarde, Ramon. Então, seguinte, a gente fez, considerando o ar seco mesmo, fizemos os experimentos assim, somente com a propagação dos sinais acústicos e o escoamento de ar. O escoamento de ar, ele variou com uma velocidade de cerca de 5,45 metros por segundo até 28,90 metros por segundo. A gente não utilizou mais nenhum outro fluido, porém, é uma perspectiva dos demais pesquisadores seguirem com esse projeto e incluírem um atomizado de água. O projeto inicial consiste na implementação de um sistema de gotículas com diâmetro na ordem de microns e uma baixa vazão de água. A gente está trabalhando num projeto futuro com a utilização de bombas dosadoras de água. Porém, a gente ainda não sabe se a técnica utilizada de correlação cruzada, se ela vai atender a esse escoamento bifásico, porque a gente sabe que, pela teoria, esse atomizado de água vai gerar uma queda da temperatura, né, local, né, dentro do interior desse tubo, o tubo de seção circular, e isso pode afetar totalmente a nossa metodologia. Provavelmente a gente vai conseguir encontrar uma velocidade média, né, somente local, ou isso aí pode alterar também, porque a gente sabe que a velocidade do som é uma função da temperatura do meio no qual o som se propaga. Tem até equações propostas por o Miara, no artigo dele, Introdução na Aula Acústica, e tem também do JEM, que são dois modelos com relações teóricas entre temperatura e a velocidade do som, então varia significativamente. Quanto ao tipo do ar, se o ar vai ser um tipo do gás, se ele vai ser puro, se não vai ser, tipo do padrão do fluido, a gente não estudou. Mas o limitante desse método não seria nem o tipo de escoamento, e sim os ruídos. Se vai ter um ruído externo, se o filtro vai ser capaz de atenuar esse ruído, qual vai ser a sua faixa de incertezas ou de erros que você gostaria de atingir, entende? A gente utilizou uma transformada de Fourier para a gente caracterizar a frequência no qual o ruído era mais intenso. Aquela frequência no qual a densidade espectral de potência, aferida via transformada de Fourier discreta, era maior. E com isso a gente conseguiu atenuar todo esse ruído por meio da aplicação de um filtro passa-faixa, no intervalo das frequências de maior intensidade de ruído, caracterizados pela Fourier, e depois a gente conseguiu, com a correlação cruzada, também atenuar esse ruído. Então, eu acredito que para um ruído considerável, não muito alto, acredito que um outro tipo de gás também poderia ser implementado sem problema algum com esse tipo de técnica.
Tá joia, obrigado.
A sua dúvida. Ficou claro? Tem mais alguma dúvida?
Não, ficou assim. Você tocou num assunto que seria minha segunda pergunta, na verdade, relacionada justamente a essa incerteza, né? Principalmente relacionada a ruídos externos e o próprio escoamento, né? Certamente vocês estão mirando escoamentos turbulentos, então a turbulência também já tem um espectro razoável aí de frequências para confundir o sinal, né? O sinal de interesse, assim. Então, imagino que seja um desafio muito grande mesmo essa questão dos filtros. Acho que, bom, você pode até dizer melhor que eu, mas eu imagino que seja o grande gargalo aí do trabalho, não?
A questão da turbulência? Então...
Não, os filtros. Os filtros.
Certo. Tá, só caracterizando fazer um levantamento. Quanto à turbulência, a gente colocou a nossa sessão de testes experimental, o microfone, todo o hardware, os sensores e tudo, nós colocamos após o complemento de desenvolvimento da turbulência, né? Justamente para evitar essa queda, esse gradiente muito alto, queda descendente da pressão, para a gente evitar todos esses fenômenos de quando o escoamento entra no interior desse tubo, né? Quanto ao número de Reynolds, realmente o escoamento é bem turbulento, o Reynolds estava na ordem de bem alto mesmo. Quanto aos filtros, a gente tentou utilizar um passa-baixa, um passa-alta e um passa-faixa, o Butterworth. A gente implementou via MATLAB, a gente conseguiu... foi um algoritmo um pouco, assim, a gente teve que realizar vários estudos, mas essa parte a gente conseguiu consolidar já. A parte do filtro está bem eficiente, bem implementado.
Rodrigo, tem uma pergunta aqui da Lígia. Qual é o diâmetro do tubo?
Certo. O diâmetro do tubo, ele é de 5 centímetros.
Okay. Tem mais uma pergunta aqui para o Renan. Renan, qual é o desvio máximo de placa de orifício que você tem de overreading hoje?
Então, utilizando a correlação mais nova que tem, né? Correlação empírica de Stevens, de 2011, e isso é função também da quantidade de líquido, né? Tomando uma quantidade de líquido aí de 0,3, que seria a máxima considerada aí
de gás úmido, a gente pode atingir até 45% de erro na leitura, né? Se não corrigido. É um valor bem alto.
Então, pessoal, acho que a gente já atingiu o nosso tempo. Então, acho que a gente pode encerrar por aqui. Agradecer a participação de todos, a todas as apresentações, excelentes trabalhos. Em alguns minutos, a gente vai iniciar a sessão de Multiphase Flow, with Phase Change and Chemical Reactions. Então, mais uma vez, obrigado a todos.
Muito obrigado, Flávio. Muito obrigado a todos.
Obrigado a todos.
Gente. Até a próxima.
Até a próxima.
Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TruSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TruSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TruSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TruSolve e transforme a sua ideia em solução aplicada na indústria. TruSolve, o mundo merece sua ideia, a sua ideia merece a TruSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TruSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-ES. Trabalhando com a TruSolve, você conta com um pacote completo de soluções. E se você já tem um protótipo e quer transformá-lo em produto, além de engenharias, a TruSolve oferece análise de mercado, processo produtivo, certificações, validações em campo, marketing e vendas. Absorvemos todos esses esforços para te ajudar a transformar a ciência em soluções para a indústria. Nossas estruturas financeira, contábil, jurídica e comercial estão prontas para te ajudar. Trabalhe com a TruSolve e transforme a sua ideia em solução aplicada na indústria. TruSolve, o mundo merece sua ideia, a sua ideia merece a TruSolve. Você é pesquisador e precisa materializar seus experimentos, protótipos e bancadas? Conte com a gente, nós temos um time multidisciplinar pronto para te ajudar. Com a ajuda da TruSolve, você vai se preocupar apenas com estudos, experimentos, análise de dados e a publicação de resultados. Nosso time multidisciplinar de profissionais está pronto para te ajudar com todo o restante. Projeto mecânico, circuitos eletrônicos, softwares, caldeiraria e soldagem, integração de sistemas e operação de experimentos. E não é só isso. Nós também te ajudamos com orçamentos, compras e fiscalização de entregáveis. Atuamos em diversos projetos realizados em instituições como UFPA, Escola de Engenharia de São Carlos, Escola Politécnica da USP, Centro de Pesquisa, Inovação e Desenvolvimento, o CEPID-AS. Trabalhando com AutoSolve, você conta com um pacote completo de soluções.
Hi, everyone. Can you guys hear me?
Yes, it's working.
Okay, so we're going to get started with the last session of the day. I'm Marco Zanoni. I'm a research officer from NRC, the National Research Council of Canada. And the session today is going to be about multiphase flow with phase change in chemical reactions. And we're going to have 4 speakers during this afternoon. And in the end of the session, we're going to have a keynote speaker, Fatemeh Salehi, and she's going to talk about computational modeling for reacting multiphase flows. So just keep tuned, and we're going to see very interesting presentations today. So the first presentation is going to be from Carlos Lange Bassani, from Universidade Tecnológica Federal do Paraná. And the title of his presentation is going to be Multiscale Modeling of Gas, Water, and Oil, Slug Flow with Deformation and Agglomeration of Gas Hydrate Crystals. Carlos, please feel free to start your presentation.
Everyone, I'm Carlos Bassani, and I'm a postdoc student at the Federal University of Technology, Paraná, in Curitiba. And today I'm going to present a bit about my PhD studies, which I defended last year. And it's about gas hydrate formation, how is this crystallization and agglomeration under multiphase flow. And this study was made in collaboration with Mines Saint-Étienne in France and the Colorado School of Mines at the United States. So the context of this study is an offshore production and of oil and gas. In this case scenario, we can be producing at some water depths of 2 to 3 kilometers. That means a lot of pressure. In that scenario, what can form is these hydrates, gas hydrate crystals that agglomerate and can lead to the plugging of the flow line. And this is one of the main issues faced nowadays by the oil companies. So basically the problem consists of a multi-phase flow. So we always have the oil phase because we are producing oil. There is gas, and there is always some residual water as well. And the fact that we have gas and water inside of the pipeline makes, with these high pressure, makes the gas hydrates to eventually form. So the phases flow along the flow line, and at some point they will reach the conditions where the nucleation of these crystals happen. And from this point on, as the crystals flow, they undergo the basic steps of crystallizations, which is growth, breakage, and agglomeration. And depending on the average size of these particles and on the lift forces over those particles, we can reach a stable regime, a stable slurry, which is the ideal condition where everything flows homogeneously, or the agglomerates can settle down, causing some partial restrictions that eventually will lead to plugging. So here down below we see a video recorded in Saint-Étienne. That's what we can see here is that it is simplified. We don't have these gas pockets here. There's no free gas phase. I'll come here to the beginning of the video and pause it. We see these round and translucent bodies. Those are water droplets inside oil continuous phase. And we can see here, I'm going to move forward some seconds. And what we see here is there's no water droplets anymore. We have, these are hydrate crystals. So in a very few seconds, all of the water gets entrapped inside of the porous hydrate particles. So the idea here is I'm going to be looking at how is this crystallization of the water inside of the porous medium of the porous particles. So the agenda for today, I'm going to talk a bit about the multi-scale process of crystallization of gas hydrates and how we can interpret these in terms of agglomeration. I'm going to show you how to couple this with multi-phase flow, and the results are going to be into 4 different systems that this kind of model is able to capture. So for gas hydrates to form, we need contact in between the gas and the water is entrapped in the porous medium, porous particles. So what we need to model is how the gas is absorbed by the oil phase and then distributed to each particle. And then once the gas arrives in the capillary, it dissolves in water and it starts diffusing through the capillary. And concomitantly, it's going to crystallize in the capillary walls. So as you can all imagine here, this crystallization in the capillary walls will cause the capillaries to get constricted. And this means that in the macro scale, the porosity of that particle is going to decrease in time, and it will eventually seal the water inside of the particle. So there are many particles, a lot of particles flowing together. And these particles, they are constantly colliding between themselves. And this collision probability is influenced by the multiphase flow shearing. Once the particle collides, and if the capillaries are open, then there is the formation of this liquid bridge that holds these aggregate together. This aggregate can disrupt because of the flow shearing. So here is about the competition of the flow shearing against this liquid bridge force. Or if this aggregate state remains together for some time lapse, then this water content can consolidate into forming a much more stable agglomerate. So all of these is based on the assumption that this liquid bridge occurs, that this liquid bridge causes some force, some attractive force in between the particles. So that basically happens when the particles are wet. It means that when water can permeate through the porous medium and spread over the outer surface. But we saw that these capillaries, they are constantly getting restricted because of the crystallization process. So eventually the particles are going to seal off the water content inside of them, and they are going to dry out. And that's the ideal scenario we want to achieve, when the particles are dry, because they are not going to agglomerate anymore. So in order to dry out a particle, we need to have a high driving force, a high subcooling to promote fast crystallization. Or we can as well put some surfactant additives in order to lower that permeation rate. Okay, so those are basically the features that the model of my thesis takes into consideration, the mathematics. I'm not going to show you any mathematical expression today, but I took this new model and I coupled it to multiphase flow. And we need to understand that the gas hydrates, they are flowing alongside to the other phases, and at the same time, they undergo all of the crystallization and agglomeration processes. So how do I couple this multiphase flow and gas hydrates? So the multiphase flow basically is going to give me the pressure and temperature conditions. That means the subcooling, the driving force for the crystallization process. As well, all of the velocities, that means the shear rate that plays a role into the collision and disruption probabilities. And the multiphase flow gives me all the interfacial surfaces. That means the mass transfer system for the crystallization. In turn, the gas hydrates, they consume gas as they form. That means a flow deceleration. Gas hydrates means that I'm introducing a particle in the system. So once the gas hydrates form, I need to consider the parent viscosity because of the increased stresslets over the particles. And as well, if there is any bedding with partial restriction, that is also going to incur in increased head losses. And finally, the gas hydrates are a phase change with exothermic nature. So I need to account this heat release in the onset when hydrates form. So that's a very complex problem for four phases and crystallization, heat, and mass transfer. But the approach I used here is to split this four-phase flow into two groups. So it's a two pseudo-phase flow. And I'm splitting in an inertia group. So the gas is a low inertia group, and the water, oil, hydrates as a homogeneous phase is a high inertia group. And the reason why to split into inertia is because I'm mainly concerned with pressure and temperature, that is the thermodynamic state for the crystallization. And that's a good assumption to split in inertia in this case. So this pseudo-liquid here is oil and water before the onset of formation. I use a homogeneous model here. And after the onset of formation, we saw that all of the water gets entrapped into the hydrate particles, so we're mainly going to treat here as a slurry flow after the onset of formation. So literature presents several trends since the 80s of how the system behaves when hydrate forms. Mainly for the temperature, we have 3 trends. The first one is that when hydrates form, they release heat, so there is this reheating towards the equilibrium temperature in that dashed line here. And one trend is the formation of this plateau close to the equilibrium. The other one is we reheat the mixture, but then we start cooling down again. And the third one is some systems that are just insensitive to the hydrate formation in terms of temperature. And for the water conversion, the reported trends are linear or asymptotic. So this is the water conversion into hydrate. That means the crystallization rate. So although these trends are highly reported in literature for 40 years about, it is very unknown still the reason why and when they happens. And this simulator I'm proposing here is able to capture 4 systems. And now I want to discuss when and why each system occur. So the first system is the base case scenario, is what I call an active surface limited system. And it's described by this water conversion that has an asymptotic trend. This mainly occurs for natural gases, hydrocarbon gases in oil continuous flow, so that's the base case scenario. And why the water conversion is asymptotic is because the porosity decreases in time. That means all of the interface surface area for mass exchange decrease in time. And the secondary effect here comes from the agglomeration, because as the particles agglomerate, the interfaces between particle and the liquid bulk will also decrease. The second system is the dissolution system, and it happens when the gas is slowly absorbed by the liquid, or when the gas is poorly distributed to each particle. And what we observe here is that the water conversion starts behaving linearly compared to the base case scenario. So this happens mainly for water continuous systems, or in oil continuous systems it can happen as well when the gas has a low solubility in the oil. An example for that is carbon dioxide. The third system is the heat transfer limited system. As I commented before, when hydrates form, they release heat, because that's an exothermic phase change. And if the system cannot transfer this released heat to the external medium, then we start forming this plateau in the temperature with a considerably decreased subcooling, which is this distance between these 2 lines here. And what happens is that, again, the water conversion starts behaving linearly. And this occurs mainly for heavily insulated flow lines. And finally, the fourth system is the pressure drop limited system. So in the same way temperature can limit crystallization, pressure drop can as well. So basically this is reported in literature for closed systems, so those batch reactors, so small pressure cells, using what we call a isochoric procedure. That means when hydrates form, they consume gas and the pressure drops, and we do not reinject any other gas afterwards. And that can limit a lot hydrate formation. But from what I've seen using the simulator in flow lines, pressure drop is always a secondary limitation. So for example here, I consider a simulation with and without pressure drop, and although this subcooling changes a little bit from the black to the blue line, we see that the water conversion does not change a lot. So pressure drop is secondary limitation when dealing with flow lines. So that's it for today. So in conclusion, what I presented today is a multi-scale, multi-physics modeling of crystallizing particles inside multiphase flow. And well, we pass over some new features, especially on the gas hydrates, and everything comes to how the water is sealed inside of the porous medium. And with this simulator, when coupling with the multiphase flow, I show you some guidelines of the why and when each type of system can happen, and I hope this can better enhance flow line design and management for oil and gas production in the future. So that's it. I would like to acknowledge the universities, the laboratories that did the collaboration with us, and the sponsors as well. Thank you. Here is my email. I'm always open. You can send me a message anytime you want. Thank you.
Thanks, Carlos. This was like a great work.
Thank you.
We have a few questions here from the audience.
Yeah.
The first one is from Bruno Furtado de Moura. Which is the minimum scale size of your model? And how are you coupling the different scales to solve the model?
Okay, can you hear me well, Marco?
Yep.
Yeah. So the minimum size scale of the model is the Bohr scale, so the capillary size. It's about 100 nanometers to 1 micron. And how I couple the scales is through population balance. I have basically two population balance, a very simplified one for the number of capillaries. So the capillaries, they constrict in time, so they are going to close. So that's the death rate of capillaries. But they can also reopen because of all the stresslets over the particles that can microcrack the crystalline structure. And the second population balance is for the agglomeration and for the number of particles. So when particles agglomerate, they change in number. So these two population balance, they give me the number of capillaries and the number of particles in the system. So that's how I change scales.
Okay, great. Hamal Martins has another question. Congratulations for this brilliant work. I'm not sure if I missed that, but is this an in-house or commercial framework for the model? If commercial, which one? I think with in-house, he meant open source.
Yeah, we code it. It's in Fortran, so everything is done. I've been working with that that code in the multiphase flow. I started in 2014. So I was still an undergraduate, and I have, of course, there are people working together. But basically, what we are trying to do is to find some analytical solutions, or at least some simple solutions for numerical side, such, for example, population balance. I'm using method of moments. That's very quick to solve. For the slug flow, I'm using Titan-Barnea model, which is a trapezoidal integration. So everything is very fast. A simulation like that is about 1 minute per kilometer, and I haven't even done any polishing in the code yet. So that's it. Everything's in house.
Okay, yeah, that's great. Is there any reason to use Fortran?
That's the code we use in the laboratory. It could be anyone else. It's very fast because it's just like, for this type of code, what we need is do while loops. That's so any basic code can do that. If we use, for example, another thing like MATLAB, then we need to carry out all the other functions and then can make it much slower. In this case, we don't need it.
Yep. Marshall has one question here. Carlos, you solve the equations coupled or segregated?
Not really sure what you meant. What I have is, how can I say? I have mass conservation to update the velocities along the flow line. And I have analytical solution for pressure drop and temperature I can have this analytical solution for pressure and temperature as long as the pipeline is very short. Then I advance like 1 meter in the pipeline, and I need to update all of the variables of the system. So it's kind of a hybrid scheme I'm using. And once I have temperature and pressure, I can solve the growth kinetics. The growth kinetics occur in a much a smaller time scale than the of pressure and temperature variations. So while hydrates form in about 30 minutes, 1 hour, this means a lot of pressure and temperature variation, a lot of displacement in the flow line. So it's a different time scale, and then I can solve the hydrates decoupled. I don't know if I answered the question.
Yeah, I think you got it. We have like 20 seconds, but I'd like to ask you a question. I'm not sure if I missed that, but how did you validate the model?
Yeah, I haven't shown any comparison with experimental data. What we have is validation of the multi-phase flow model. Hydrodynamics is separated from heat transfer. So because usually heat transfer, we don't have the visualization of the flow. And then gas hydrates, I have two kind of validation. One's for the porous medium, everything that comes from the porous medium comes from the gas consumption rate. And for decoloration, we have some visualization that we can retrieve the size of the particles. But when it comes to the validation of everything together, so hydrates forming under multi-phase flow and agglomerating, we don't have experiments for that. We only have the trends I mentioned.
Okay, yeah, that's fine. Thank you very much. Good job.
Thanks.
So the next speaker is going to be Guilherme Stefan from Universidade do Vale do Rio dos Sinos. And his work is called A Critical Review of Cryopreservation of Cells Techniques, Thermal Aspects. Please go ahead. Yeah, Guilherme.
My name is Guilherme. I'm from the Mechanical Engineering graduate program at Unicinos, and I will present the article A Critical Review on Cryopreservation of Cell Techniques, Thermal Aspects.
A leading branch of biology which studies the effect of low temperatures on cells, tissues, and living organisms is cryobiology. Through this science, it was possible to develop cryopreservation, which consists of the preservation of cells and tissues at temperatures below the freezing point of water, in order to preserve the composition of the cells and maintaining their functionality indefinitely. Cryopreservation consists in the conservation of biological material at temperatures of minus 196 degrees Celsius, using liquid nitrogen. At the temperature at which the cellular material is conserved, all chemical reactions, biological processes, intra- and extracellular activities are suspended, which makes it possible for the conservation of the biological materials. However, for this to happen safely, it is necessary to use a cryoprotective agent, also known as CPA. Despite the use of CPAs, there are still other factors that can influence the preservation of cells, like the method of cryopreservation, the materials used, and the methods of defrosting of the cells. Depending on the method, the cryopreservation of cells can cause dehydration damage or degeneration of ice crystals on the inside of the cells, which decrease the cell's functionality. For this reason, the study of the cryopreservation process by different methods is so important. There are some methods of cell cryopreservation, of which the two most common alternatives will be presented. This process causes different types of cell injuries associated with freezing and defrosting process, known as cryo injuries. They can be classified as solute injuries and ice injuries, as we can see in the figure. In the case of slow freezing, excessive dehydration occurs, induced by freezing concentration that can damage the cells, resulting in damage to the solution. With the fast freezing, there is the formation of ice that can mechanically damage the biological structure of cells, resulting in ice damage.
There are two methods widely used to perform cell cryopreservation, namely slow freezing and vitrification. The basic difference is in relation to the speed at which the freezing process occurs. In addition, despite being different methods, cryopreservation is known by the following fundamental steps presented in the figure. In the first stage, the CPA is absorbed or adsorbed by cells through mass diffusion. The second stage is where the samples change from room temperature to cryogenic temperature. This process can occur with the vitrification or the slow freezing. After that stage, the frozen material is preserved indefinitely until it is necessary to use it again. When the material is needed, we need to defrost it in order to recover its cellular metabolism. For the last stage, before using the cells again, it is necessary to remove the CPAs in order to avoid the production of secondary metabolites that can be toxic to the cells. Like any process that uses biological material, it is important to evaluate the possible side effects from cryopreservation. For this, the use of cryoprotective agents, CPAs, began, which seek to reduce osmotic damage and reduce the formation of intra- and extracellular ice crystals. Despite presenting this benefit, it is important to limit the use of CPAs because in some cases this agent can be cytotoxic. The use of CPAs occurs according to the method of cryopreservation used, where they can be intra- or extracellular CPAs, depending on the desired action site. The most used CPAs are the intracellular, with its ethylene glycol, dimethyl sulfoxide, and propanediol as the main examples. In addition to their functions, CPAs can be used in different concentrations. Slow freezing processes require a lower concentration when compared with the vitrification process, finding values between 1 and 2 mol per liter for slow freezing and values greater than 4 mol per liter for the vitrification. The slow freezing process takes place inside a freezer with a temperature control system. The sample that will be preserved is stored in a container that supports cryogenic temperatures. In this case, the desired temperature is programmed and the sample is cooled until cell dehydration is finished. After that, the material is stored in liquid nitrogen until further reuse. The slow freezing process can be carried out using a constant or variable rate. This rate varies between 1 and 10 degrees Celsius per minute, which will be the range considered for slow freezing. In addition, the slow freezing process requires a low concentration of CPAs in the solutions. This process is widely used in the preservation of human embryos in the most diverse stage of development. This process have a result that has 70% embryo survival and the rate of pregnancy and development presented is like of no frozen embryos. So in the graphic presented, you can see the different rates of cooling between the slow freezing and the vitrification. Vitrification is a solidification process where a liquid is suddenly transformed into a material in a glass state, aiming to avoid the formation of ice crystals inside the cells. However, to obtain this state, it is necessary to increase the cooling rate, but with the use of a higher concentration of CPAs. In addition, another important factor of this method is the way in which the materials is defrost. This defrost must be at a uniform rate to avoid thermal stresses that can damage the cells. In view of the dangers from the use of CPAs, it is possible to reduce these effects by increasing cooling rates to a very high level, in the range of 100,000 and 1 million degrees Celsius per minute. Despite being efficient methods that use liquid nitrogen, it was still necessary to find a way to further increase the freezing rate. The main limitation in the vitrification with pool boiling is that the nitrogen vapor generates around the sample during the freezing, called a vapor blanket. This blanket acts as a thermal insulator and limits the heat transfer process between the sample surface and the nitrogen, as we can see in figure. In view of these difficulties, an alternative is the thin film evaporation method, where there is no formation of the vapor blanket. In this way, it will be possible to carry out an ultra-fast freezing method and consequently vitrify the cells. The thin film evaporation process basically consists of the evaporation of a thin layer of liquid that is in contact with a porous surface that stores the sample. This evaporation occurs due to the temperature gradient between the surface and the liquid. According to some authors, the fluid flow mechanism and the evaporation of the film guarantee an increase of the convective heat transfer coefficient. The thin film generated on the surface presents different regions throughout the evaporation process. There are three regions of the thin film evaporation process. Region 1. Considering the region of the no evaporation. In this region, the film has a fixed thickness and the evaporation process does not occur because of the attractive forces between solid and liquid. The vapor pressure and the substrate temperature do not reach the necessary values. The region 2, known as the transition region. In this stage, there is a weakening of the attractive forces and the thickness of the thin film varies along the substrate. It is in this region that the beginning of the evaporation occurs and where the greatest heat transfer occurs. For the end, the third region, also called as minuscule region, is where the slope of the liquid and the vapor interface become almost constant. This slope of the interface of this phase is what determines the contact angle between the fluid and the substrate. It is notable to identify improvements in the heat transfer with the use of thin film evaporation. For this reason, this method has been used to perform the cryopreservation of cells through vitrification with liquid nitrogen. Experiment performed by Chu et al. 2018 presented the best result in relation to the cooling rate and consisted of performing thin film evaporation in a CPA sample inserted in an evaporator. The evaporator was formed by two copper plates overlaid with a porous surface on their layered external sides, as shown in figure. Inside the two plates, the CPA solution was positioned together with a thermocouple to measure the temperature over time. In the experiment, the formation of the vapor blanket was not verified, and the temperature of the CPA solution in the evaporator varied from 20 to minus 188 degrees Celsius. In this research, they found an average rate of 150,000 degrees Celsius per minute, which helps to reduce some possible damages if this process uses cells. In another study performed by Su et al. 2017, an evaporator system like that of Su et al. 2018 was used with a set of fins. To evaluate different structures, the authors used three plates with square fins on the same size but in different amounts. As a result, it was observed that the plate with the highest cooling rate was the one with the most fins, reaching an average values of 50,000 degrees Celsius per minute. Finally, this study reviewed some of the methods for the cryopreservation. Some of the key findings from this study are follows. The slow freezing process uses low cooling rates and requires low concentrations of CPAs, but there is still a risk of cryogenic injury. The main process used for the cryopreservation of cell has been vitrification with high cooling rates and concentrations of CPAs. With the search of an increase in the cooling rate, the thin film evaporation method appears as one of the main options, reaching values above 100,000 degrees Celsius per minute. And it is understood that with the the increase in the cooling rate, it is possible to reduce the concentration of CPAs, thus avoiding toxicity problems after cryopreservation. Thank you very much for your attention and for the opportunity to present my work at this event. I'm now open for some questions.
Hi, Guilherme. Excellent work. I was very interested when I read your work. It's a very interesting review. We have some questions from the audience. The first one is from Adriana Malafaia da Mata, which was also like one question of mine. Why are you reviewing this topic? What are you developing?
Hi everyone, good afternoon. I'm reviewing this topic because I need to collect some reference about the area of cell cryopreservations, an area which is have a lot of studies nowadays, and we need to find some alternatives to make it if how can I say that the best efficiency in the process, because the process can have some dangers in the some damage in the cells, so we need to find the best method to make this cell preservation process doing fine. I'm basically I'm sorry for my English. Basically, I'm developing a continuation study on thin film evaporation process of cryopreservation of cells. Alternative. The idea is to carry out this filter study in an experimental and numerical way. So we want to make in the lab. Yeah. And with some CFD models with ANSYS. Basically is that. So we want to find the best conditions to perform the cryopreservation of cells using these methods of thin film evaporation process.
Okay, yeah, that's great. I have one question. Which method you're going to use? Are you planning to use the vitrification method?
Yes, basically the difference between slow freezing and vitrification is the use of CPAs. The vitrification need a higher concentration of CPAs, and the slow freeze and the vitrification also have a higher cooling rate. There is a lot of numbers of cooling rate, but like we can say 100,000 degrees Celsius per minute for vitrification, and the slow freezing need to use a lower concentrations of CPAs and have like a cooling rate like 10 degrees Celsius per minute. So it's this difference, and I want to study the vitrification using the process of thin film evaporation. There is some works that study this process in the past few years, and we want to continue this study to find the best solutions and the best conditions to perform this process.
Okay, yeah, that sounds good. I have one more question if nobody else has. I don't see any more questions here. Anyone in the meeting room want to ask something? If not, I'm gonna ask maybe the final question. I guess that's not.
If someone want to talk with me, you can get my email and send me we can talk later. It's all right.
Okay.
I'm here.
Have you found anything?
You can ask.
Sorry. Have you found anything in the literature about the thickness of the film? Does that affect somehow the evaporation?
Yes, in the literature we see that there is some regions of the thin film evaporation where the main let me see here the transition region is the region where is the higher heat flux, but there isn't a size or anything because depends of where the size of the we are using. If we are using some nano or some micro, it depends. Don't have the one value for the thickness.
Okay, yeah, that's great. Very interesting presentation. Good job.
Thank you very much.
So now we're going to go to the third speaker of the day, Tiago Augusto Moreira from Universidade de São Paulo. And his work is called Liquid Film Thickness Measurements During Convective Condensation of R290 in a Horizontal Channel.
I'm a PhD student from the University of São Paulo, and I'm here to present the paper entitled Liquid Film Thickness Measurements During Convective Condensation of Propane in a Horizontal Channel. My presentation is divided between the introduction, the experimental apparatus, the liquid film thickness measurement and technique and setup, my results, and conclusions. The liquid film thickness is a relevant parameter in both the heat transfer coefficient and pressure drop in two-phase flows, especially during condensation in horizontal channels. Once in stratified and wave flow patterns, there is always the presence of the very thin liquid film on the top region of the channel, which is directly related to the heat transfer coefficient and pressure drop. Therefore, the knowledge about the behavior of the liquid film thickness with varying experimental parameters is essential to the development of accurate heat transfer coefficient and pressure drop prediction methods. Therefore, in this study, we're going to perform experiments for the convective condensation in a horizontal channel of propane for the liquid film thickness. It's worth to highlight that propane is a low global warming potential and no ozone depletion potential fluid. Also, flow pattern images are obtained to be compared with the liquid film thickness signals obtained. My experimental apparatus consists of a closed loop in which the fluid is kept inside the condenser and driven by the circuit by one of two micropumps, B for low mass fluxes and A for high mass fluxes. Then it passes through a Coriolis mass flow meter, a subcooler, which is used to guarantee subcooled condition at the inlet of the test section, or the inlet of the preheater. The preheater consists of a countercurrent tube-in-tube heat exchanger with hot water flowing in the annular region and the refrigerant flowing inside the unit tube. Between the preheater and the test section, we have our stabilization section that's used to guarantee full hydraulic development at the inlet of the test section. The test section here is used to obtain heat transfer coefficient data, and as I'm going to present this data here, I'm not going to provide details about the test section, but it consists of also of a countercurrent heat exchange, tube-in-tube heat exchanger with chilled water flowing in the annular region and the refrigerant flowing inside the unit tube. Downstream the test section, we have a visualization section, which where the liquid film thickness measurement setup is installed, and two valves, a needle valve and a ball valve. Both valves are used to control the pressure inside the test section by opening it or closing it, in order to allow us to perform experiments with the minimum amount of fluid possible inside the circuit and avoid any risk working with hydrocarbons. The liquid film thickness measurement technique that we are going to use here was first developed by Shed and Neal for a flat surface and later modified to allow measurements in round geometries. The technique consists of applying a diffuse source of light in a transparent window that has on the other side the liquid film. Eventually, one of the light rays will reach the liquid vapor interface at a critical angle, reflecting and creating a ring pattern. And through solving the geometrical problems shown here, and based on the diameter of the ring, we can obtain the liquid film thickness. The critical angle here is obtained based on the index of refraction of both the liquid and the vapor, and the distance between that the light travels with inside the transport window is obtained from this equation. It's worth to highlight that if we have here very thick liquid films, the ring that we're going to be seeing here is not related to the reflections on the liquid and vapor interface, but on the liquid and wall interface, therefore serving as a threshold for the technique. In our case here, the threshold is 700 microns for the propane, so if we have measurements that is larger than 700 microns, they are not considered for the calculus here. This is the setup that I use for obtaining the liquid film thickness measurements. It's, as I said previously, it's installed at the visualization section, where we have the inlet and outlet here, so the test section is located in this location and the fluid flows in this direction. It has an inner diameter of 9.43 millimeters, which is the same as the test section. Here on the visualization section, we can perform experiments for the liquid film thickness both at the top and bottom of the channel. As here, I'm going to present just data for the top measurements. I'm going to discuss just this part. The laser is shot from the top region, pass through a mirror, through a hole inside the mirror, positioned 45 degrees here with the center of the channel, and reach the visualization section wall, external wall here, which has a translucent tape fixed on it that serves to diffuse the laser beam to create a diffuse source of light, and as a screen for the ring pattern that's generated based on the image. This ring pattern is reflected on the mirror and recorded by a high-speed camera. My experiments were performed for propane for mass velocities ranging from 50 to 250 kilograms per square meter second, vapor qualities from 0 to the unity, saturation temperature of 35 degrees Celsius, and heat fluxes inside the test section of from 5 to 60 kilowatts per square meter. In general, I obtained a negligible effect of heat flux regardless of mass velocity for all the data that I obtained here. For the lowest mass velocity, we observed intermittent flow pattern at low vapor qualities, which presented a very thin liquid film with some spikes related to the passage of liquid fronts, and wave flow pattern at higher vapor qualities, which related to very thin liquid films. And also we observed that the base liquid film thickness is constant for the whole vapor quality range and the lowest mass velocity. The base liquid film thickness is defined as the substrate of the liquid film in which waves flows on. And it's usually defined in literature as the median of the liquid film thickness signal, discarding the liquid film thickness results higher than the time average of the liquid film thickness data. For the mass velocity of 100 kilograms per square meter second, we observed also intermittent flow pattern at low vapor qualities. And as you can see here, for the lowest mass velocity, it's the same behavior of the liquid film thickness signal at the top region. We have a thin substrate with the base liquid film thickness, and here the red line here shows the calculated base liquid film thickness, and with some random spikes related to the passage of liquid fronts, as we can see here. It's just worth to highlight that's very thin films around 50 microns. And as we increase vapor quality between two values still lower than 0.5, we see the wave flow pattern, which is characterized by to have a very thin liquid film on the top region, which also is smooth, as we can see here, around 100 microns, and the liquid flows in the condensate layer at the bottom of the channel. As we increase quality to values higher than 0.5, the flow velocity of the flow increase, and the annular flow takes places. and during annular flow, we have a more even distribution of the liquid film around the channel, which results in an increase of the liquid film thickness at the top region of the conduit, and also in rougher interfaces, as we can see here. Concerning the results for the base liquid film thickness, we have very thin base liquid film thickness at low vapor qualities during wave and intermittent flow patterns. However, as we increase mass velocity, a more even distribution, as we increase flow velocity with increasing vapor quality, a more even distribution of the flow of the liquid film on the channel perimeter occurs, transitioning to annular, and therefore there's an increase in the base liquid film thickness, as we can see here. From this point, there's a decrease in the base liquid film thickness with increasing quality as expected for annular flow pattern. For the mass velocities higher than 200 kilograms per square meter second, the results are similar between the G of 200 and 250. It's annular flow pattern in most of the vapor quality range. However, we can see intermittent flow pattern at very low vapor qualities. As we can see here, based on the base liquid film thickness, we have the intermittent flow pattern here at very low vapor qualities. And as we increase flow velocity, the flow transitions to annular, causing an increase in the base liquid film thickness, which decreases with increasing vapor quality. So, as main conclusions, we saw a negligible effect of the heat flux on the liquid film thickness during convective condensation. For the lowest mass velocity, we notice intermittent and wave flow pattern with a constant and thin base liquid film thickness of around 50 microns, regardless of vapor quality. For G equal to 100 kilograms per square meter second, we observed the intermittent, wave, and annular flow patterns. For G larger than 200 kilograms per square meter second, we notice the intermittent and annular flow pattern. For mass velocities higher than 100 kilograms per square meters, we notice an increase in the base liquid film, that the base liquid film thickness increase at low vapor qualities until it reaches a maximum, which is characterized by the transition between intermittent and wave flow pattern, intermittent and wave to annular flow pattern, and from this point beyond, it decreases with increasing vapor quality. Here are my acknowledgements to UFPA, PCNPQ, and CAPS, and Mr. José Roberto Bogni for the technical support. And thanks, I'm available to questions.
Thank you, Thiago. Very interesting presentation. I think we have no questions from the audience.
Okay.
Does anybody in the meeting room wants to ask something? So I guess you did a good job. Everybody understood.
Yeah, thank you.
Oh, here is one question. Thiago, what's the effect on the heat transfer coefficient when the flow pattern is in transition? For example, when flow pattern goes from stratified to annular.
In annular flows, the heat transfer coefficient depends directly on the liquid film thickness. So when you change in the transition, you have a churn flow pattern, and also depends on the liquid film thickness. So it's basically that the liquid film thickness is the main thermal resistance on the heat transfer coefficient during condensation. So I don't know if I answered the question.
Okay. Does anybody have another question for Thiago? So while people think about it, I'm gonna ask you like a very general question.
Okay.
what is the next step now of your research? What you plan to do later?
Yeah, I gathered the liquid film thickness for this. In this paper, I presented just for propane, but I got also for isobutane, propylene, and mixture of these hydrocarbons. And I also obtained data for the heat transfer coefficient. So the idea is to combine the results for the heat transfer coefficient with the liquid film thickness ones.
Okay, that's great. I see no more questions. I have another question, but maybe I missed this during your presentation.
Okay.
So if you could just explain a little bit more. So how the thickness affect condensation?
The heat transfer coefficient?
No, how the thickness of the layer, of the thin layer, affect the condensation or evaporation or heat transfer coefficient?
Okay, so both in evaporation and in condensation, in annular flows, the liquid film thickness is the main thermal resistance on the heat transfer coefficient. So the conduction through it. So as thicker as the liquid film is, the lower will be your heat transfer coefficient. So this is mainly the reason.
Yep.
Listen, so it's directly affecting. And also the pressure drop. Pressure drop is also related to the liquid film thickness.
Yep. We have a question from Marcio. What do you mean when you say quality increase?
Vapor quality.
Vapor quality.
The
you
vapor
mean quantity?
Yeah, like the vapor quality, the thermodynamic vapor quality, like from 0 to the unity, it increases.
Oh yeah,
It goes like from liquid to vapor.
Yeah, I think this is what Marcio is talking about because he said fraction of gas.
Yeah, could be.
Yeah, okay. We have 1 more minute. So does anybody have more questions? Anybody from the meeting room? Oh, here. Quality equal gas mass fraction as defined from Johan's book, Carlos Massani said.
Okay.
So I guess this is clarified now. Yeah, good job, man. It was a great work.
Thank you. Appreciate it.
Yep. So we are about to end the questions in a few seconds.
Okay.
Good job.
Thank you.
Yeah, so now we're gonna go for the 4th speaker of the day, Leandro Maestri from Universidade de São Paulo. And his work is called Record Levels of Heat Transfer Coefficient During Convective Flow Boiling for R134A.
Good morning, my name is Leandro Maestri, master student in mechanical engineering at UFPA São Carlos in the Heat Transfer Research Group Laboratory, and I represent the article Record Levels of Heat Transfer Coefficient During Convective Flow Boiling for R134A. The growing demand for dissipating high heat flux from present devices create the need for new cooling technologies, as well as improvement in existing technologies. In order to increase the heat flux of a microchannel with single-phase cooling, maintaining the practical limits of the surface temperature, it's necessary to increase the heat transfer coefficient by increasing the flow rate or further decreasing the hydraulic diameter. Both are accompanied by a very large increases in pressure drop. However, the two-phase heat dissipation can achieve very high heat flux at a constant flow rate, and maintaining a relatively constant surface temperature. Initially, the mechanical refrigeration was limited to a few applications with ammonia, sulfur dioxide, and methyl chloride, which were the only refrigerants available, all highly toxic with the exception of ammonia, and all of these refrigerants have been replaced by halogenated hydrocarbons like R134A, R123, and R11. They are synthesized from hydrocarbons of the methane and ethane series, which, due to their safety advantages, they modernly constitute the refrigerants for most refrigeration installations. And from the literature review, we could see that the maximum heat flux obtained with the refrigerant R134A in a single tube was approximately 700 kilowatts per square meter. And taking this context into account, this paper presents new experimental data for heat transfer coefficient with high heat flux using tubes with 1.0 and 1.1 millimeters inside diameter. They are stainless steel tube and the orientation was horizontal. The experimental results were compared against one predictive methods from the literature. The experimental setup is comprised of refrigerant and water circuits. In the refrigerant circuit, starting from the condenser, the test fluid flows through the filter, passing by a Coriolis mass fluorimeter to the pump. Downstream of the pump, a bypass piping line containing a needle valve is installed so that together with a frequency controller on the pump, the desired leak flow rate can be set. Just upstream of the preheater inlet, the enthalpy of the liquid is estimated from its temperature by the thermocouple located at an adiabatic position on the outside tube wall, and its pressure by an absolute pressure transducer. In the reservoir fluid, the fluid is heated up to the desired saturation pressure. In the test section is heated by applying direct DC current to its surface, and it's thermally insulated. Once the liquid leaves the test section, its temperature is determined from a thermocouple located on the external tube surface, and the fluid is directed to a tube-in-tube type heat exchanger where it's condensed and subcooled. The test section is made of aluminum 100 mm long, and there were two tubes that were used in this experiment, one with 1 mm and other with 1.1 mm inside diameter. The wall temperatures are measured through 6 thermocouples fixed along the outside wall of the test section, as indicated with these symbols. The experiments were conducted first by setting the temperature in the refrigerant tank, and once establishing the saturation pressure in the refrigerant circuit, the mass velocity was set through the frequency controller acting on the pump. Heat flux was then applied to the test section to initiate evaporation, and power was applied in the test section, implemented in small steps, always controlling other parameters to keep them constant. For the test tubes performed in this experiment, the measurements were made by increasing the heat flux until the thermocouples located at the end of the test section show sudden overheating. And such a procedure was used to avoid failure of the test section due to wall temperature oscillations. In order to calculate the heat transfer coefficient uncertainties, heat losses to the environment were neglected, and single-phase flow experiments were performed to assure the accuracy of the estimated vapor quality and to evaluate the effective rate of heat transfer to the single-phase refrigerant. The formula is shown here, and where the P is the electrical power supplied by the DC power source to the heated section. The figure shows that the energy balance results under turbulent subcooled liquid flow conditions. And according to this test, the heat losses during the single phase experiments were below 10%. In the section, the experimental points obtained with two-phase flow are described. The results of heat transfer coefficient and local vapor quality are shown for different values of mass velocities and with increments of heat flux. As you can see through these figures, it's clear that the heat transfer coefficient increases with increasing heat flux, and the charts show that the mass velocity increases. Now, as the mass velocity increases, we can obtain higher values of heat transfer coefficient, increasing the value of heat flux. With exception for the mass velocity of 6,000, the higher heat transfer coefficients were obtained with intermediate heat flux because it occurred dry out in higher quality for those higher values of heat flux. The maximum heat transfer coefficient of 67 watts per square meter Kelvin was obtained with the 1.0 millimeters tube with the combination of the highest value of heat flux, this point here, and the mass velocity of 10,000 kilograms per square meter seconds. And based on our literature review, we could obtain record levels of heat transfer coefficient for the refrigerant R134A. And to show the distinct behaviors that can happen when changing tube diameter, this figure shows the comparison between the experimental results for tubes of 1.0 and 1.1 millimeters. As shown, the heat flux value of approximate 600 kilowatts per square meter in the tube of 1.0 millimeter presents higher values of heat transfer coefficients than the 1.1 millimeter tubes. In addition, it was possible to provide a higher heat flux value for the 1.1 millimeter tube, in giving a slight increase in the heat transfer coefficient for this tube. This figure shows the comparison between the experimental results and the predictions given by the correlation of Tbilisi et al. Made in 2017. There is an median average error of 21.7%, and 79% of the data were predicted within the error band of 30%. Besides, the accuracy of the predictions seems to be almost uniform for most part of the heat transfer experimental range. The correlation is written below, and it uses fluid properties like the density, viscosity, and surface tension, and flow properties as mass velocity, and geometric parameters of the tube as the inside diameter. And to conclude, this paper has presented and discussed new fluid boiling heat transfer coefficient data for the refrigerant R134A using 1.0 and 1.1 millimeters circular channel. The experimental results reached high values of heat flux as close to 700 kilowatts per square meter, and the goal of obtaining record heat transfer coefficient values was achieved due to the combination of high mass flow rates and high electrical power. Beyond that, higher values of heat flux will be obtained in the future work. And the experimental results, when compared against the predictive methods, it provides a good accuracy, predicting the database with a mean absolute error that it's not that big. And we thank the funding agencies, CAPES, CNPq, and FAPESP. Here we have some references of this work, and I thank you. And if you have any question, let me know.
Thanks, Andre. Excellent work. We had a bit of discussion in the chat, but it was like for the previous presentation. Sorry, Bruno, I missed your question, but Thiago just answered. For this presentation, nobody asked questions yet. So anybody in the chat, in the meeting room, wants to ask questions?
Hi, Marco. Carlos here. Yeah, I've seen the slide that the heat transfer coefficient decreased by, it seems apparently 1 order of magnitude when you change the diameter from 1 millimeter to 1.1. And I found this very surprising. Can you speak a little bit about why this happens, Andre? Thanks.
Hello, can you hear me?
Yep.
Okay, it's because we had an increase in 10% of the diameter, passing from 1.0 millimeters inside diameters to 1.1 millimeters. And with the increase in the inside diameter, the heat transfer coefficient usually decreases. And that's what happened.
Okay.
That's very interesting, but it's just because of the surface of contact, you think?
I think mostly it's because of the size. Yeah, when we increase the inside diameter, as it happened, we have more surface to the fluid to exchange heat, and that's why with this bigger surface, the heat transfer coefficient made a drop.
Yeah, well, it's a fact, it's a measurement.
Yeah.
Thanks.
Yes, thanks.
Any more questions for Andre? If nobody has it, I have one. Andre, one of the main conclusions of your work is the high values of the heat transfer coefficient. So what did you do different from the literature that resulted in such high values?
It's because the literature it didn't want to achieve such a higher values of heat transfer coefficients with this fluid. The mostly experimental works that were made for critical heat flux was with water, and to making critical heat flux with this fluid, it's something that is kind of new. But what we kind of made that we could achieve those levels of, it was to increase the mass velocity. We used a mass velocity really high, like 10,000 kilograms per square meter, and the other authors usually use like 400 kilogram per square meter seconds.
Okay. Yep. Any more questions? I don't see anything in the chat. Oh, here is one. Andre, what is the main impact in the heat transfer coefficient when the fluid change from, let's say, R134 to R290, such as in the previous work?
The impact in the heat transfer coefficient comes with the change with the properties, like the enthalpy of vaporization changes when we change the fluids. So it depends of the fluids. Some fluids has less or higher enthalpies of vaporizations. And that will change the...
Yeah, that's very interesting. So I guess we are in the end of the questions session. Good job, Andre. Excellent work.
Okay, thanks.
So right now we have the keynote speaker. Is she already in the meeting room? Not yet. Okay. It's probably very early for her now in Australia. She might be waking up. Hi, everyone. We are still waiting for Dr. Fatemeh. We're going to wait for 10 minutes to see if she shows up. If she doesn't shows up, we're going to cancel this keynote speaker, this presentation for today, and we're going to end the day. So stay tuned. In the next 5 minutes or so, I'm coming back. Hi, everyone. Sorry about the delay. I think we're going to have to cancel the keynote speaker for this afternoon. We had some problems contacting the speaker, but we are planning on rescheduling this presentation for tomorrow afternoon. So hopefully we're going to have a better luck tomorrow.
Thank you, Marco, Zanoni. Thank you. Great job.
Thanks.
Thank you, guys. We close this session today. I see you tomorrow morning, 8:30 for the first section. Have a good night.
Have a good night, everybody. Thanks for having me. It was a pleasure.
Thank you, Marco. Bye.
Bye.